Dynamic programming is the toughest and most important part of any DSA interview question, and I have decided to make a full course on that. By the end of this course, I can guarantee you that you will become master in all dynamic programming questions. And in this course, we are going to discuss what is dynamic programming, brief history, what are the different ways to use dynamic programming, recursion, tabulation, memoization, all the characteristics, when to use dynamic programming, what are the most effective ways, and we will learn 20 most asked, most like, and most popular dynamic programming questions. And trust me, these questions have been asked by hundreds of companies thousands of times. So without any delay, let's get started. The term dynamic programming has the reputation of being a scary term, but it's not that complicated. Actually, this dynamic programming approach is nothing but a problem solving technique. And this technique involves you of taking a bigger problem and then start breaking into bunch of different smaller sub problems. Now for each of the sub problems that you are already calculating the results, you are also going to store this result, and this is going to be the important procedure in this whole dynamic programming scenario, that because you are storing the results, whenever you need to recalculate or refine the same value, you can simply quickly look up in the stored values, and then you would be able to find the answer for that, and eventually you would be able to find the correct solution for the item that you are looking for using dynamic programming. Now in order to achieve that, we are going to use bunch of things like recursion or memoization or tabulation, but let's try to understand dynamic programming with a very simple example of a Fibonacci series. This is the simple equation of for any Fibonacci series, and we are given the first two values of the Fibonacci sequence, where Fibonacci of 0 is going to be 0 and Fibonacci of 1 is going to be 1. Based on these two values and this function, we can calculate any particular Fibonacci number. We can calculate number for even Fibonacci of 100, and that is going to be sum of Fibonacci of 99 plus Fibonacci of 98. Now let's try to understand that if we have to calculate or find the value for Fibonacci of 5, how we are going to be able to do it without using dynamic programming. And for simplicity, we are going to be using recursion to solve this problem. Logically, Fibonacci of 5 we know is going to be sum of Fibonacci of 4 plus Fibonacci of 3. Now same way, subsequently, now notice that in order to calculate Fibonacci of 4, we will have to do all of these calculations, and same way in order to calculate Fibonacci of 3, we will have to do bunch of different more calculations. But notice over here we are calculating the value for Fibonacci of 3, over here we are calculating the value of Fibonacci of 3, over here we are calculating the value of Fibonacci of 2, once again Fibonacci of 2, and once again Fibonacci of 2. So we are doing lot of repeated work, and for problems like these, dynamic programming would be the correct and most efficient approach. Because now notice the scenario that what if we just simply create an array where we are going to store the result of every single Fibonacci value starting from value 0 all the way up to 5, and all we need to do is store those results, and whenever we need to calculate the new value, we can always look up in the previously stored results. So let's try to understand this with an example. We know the base case Fibonacci of 0 and Fibonacci of 1 is going to be value 0 and 1. For value Fibonacci of 2, the value is going to be sum of previous two elements, so this is going to be 1. Same way Fibonacci of 3 is going to be sum of previous two elements, so on and so forth. We can keep on repeating for every single value, and we would be able to generate Fibonacci of all the way up to million values in very quick fashion. Now notice the difference between two approaches. Without dynamic programming, we are doing bunch of repeated work for our recursion call, and the time complexity in this case is actually going to be big of 2 to the power n, which is very expensive. Like trust me, this is very expensive, and most of the computers cannot even compute more than 100 numbers. For this approach, dynamic programming approach, time complexity is actually going to be big of n simply. So you can compute billion values and still computer would be able to run very efficiently. And this is the true power of dynamic programming. Dynamic programming was originally invented in actually 1950s, as part of the way to calculate some complex problems where we are already storing the results, and we would be able to recalculate that in bunch of other places. Now computers were not popular in 1950s, but the underlying concept allowed computers to quickly look up the previously computed values and come up with the answers. This was actually developed by a very popular mathematician called Robert Bellman. And yes, this Robert Bellman is the same Robert Bellman from our very popular Bellman and Ford algorithm. And if you know, Bellman and Ford is a great algorithm if you want to find the shortest path amongst any graph where you have negative values as well. So which is like a much better approach compared to Dijkstra's, which only works with non-negative values. So now coming back to our problem of understanding what dynamic programming is. Now we know that we'll have to deal with three distinct terms while speaking about dynamic programming. First one is a recursion. Well, it is nothing but a simple way for you to take a bigger input, start breaking this bigger input into smaller input and smaller input and again smaller input until you reach to a case where it is very easy to calculate. And once you have this result, you would be able to build the next result, then you would be able to build next result, and so on and so forth. You would be able to solve this problem completely, and this is the simple recursive approach. Next category is memoization. So memoization is actually very closely related with recursion, where for recursive call, whenever you are making and whenever you are doing any sort of computation, whenever you find some result, you start to store that result in some fashion, and you are actually memoizing these values. So say in future, if you have to make another recursive call for any particular item and then you need to make that calculation, you already have those values stored in the result, and this is called memoization. So recursion and memoization would always go hand in hand in any dynamic programming approach, and combination of these two is actually going to be called top down approach. Now why it is called top down? Remember how recursion works. For recursion, you are going to start with the top most or most largest or extreme value, and then you are going to be taking on smaller and smaller sub problems, and once you reach at a base case, then based on that you would be able to start making calculations. So there would be a recursive call stack that you are going to take care of, and which will store all the results. Now the third term associated with dynamic programming is going to be called tabulation. So tabulation is slightly different compared to our recursion plus memoization approach. Now even in tabulation, we are storing the result of items that we are calculating, but the different part is that let's say that we are currently given a problem size of this, and where we need to store the value for something associated with term 50 or value 50. As part of dynamic programming tabulation, we are actually going to start calculating results starting from value 0 all the way up to value 50, and this is going to give us the result all the way up to all of these values which we would have stored. So notice that instead of starting at the biggest value, we are actually starting at the smallest value, and then we are building our solution with bigger and bigger values, and eventually we would calculate the results for all 50 values. So logically, this is also a dynamic programming technique that is going to be opposite of the top down approach, and that is called bottom up approach, where you are starting at the bottom and then you reach at the very top. And both of these ways can be used in different scenarios. Many times you can also use them interchangeably depending on the problem statement, but there are some scenarios where it makes sense to use either top down approach or bottom up approach. So let's understand those scenarios as well. Logically, let's say that if you are already given that the problem can be easily solved recursively, it makes sense to use a top down approach, because the recursion goes hand in hand with memoization and dynamic programming. It is going to be a less coding approach, and you can also simplify your implementation and understanding of it. Next thing is, you will also have to keep track of the recursive call stack. So that is something that you need to be aware of, and also understand that how the time complexity is going to affect. The other thing with recursive approach or top down approaches, that many times you don't have to do all the calculations. So if you only need to do selective calculations in order to generate the result, then it would make sense to use top down approach. And there can be many examples of this, but one common example is a problem called unique paths, which you are going to solve in this subsequent lead code problems that we will do. Same way, let's understand some of the benefits of bottom up approach. If the problem can be easily completed in a bunch of different sub problems, then it becomes a good candidate. If you have a good base case, and based on the base case you can build on top of that base case for all the other subsequent value, then it makes sense to use bottom up approach. If you need to do all the calculations for all the sub problems and store all of those results, which means you are not doing selective calculations and you are not doing sparse calculation, but you are doing dense calculations, then it makes sense to use bottom up approach. And remember that this is going to be an iterative approach, so you don't have to worry about keeping track of any different type of call stack, so it works perfectly fine. And these are the two common differences. Now I know we are at the very beginning of our dynamic programming journey, so it's tough to understand all of these statements, but I can guarantee you that after completing our 20 lead code problems, you would be able to very easily identify the difference between bottom up approach and top down approach, and when to use which one, and how to use memoization, recursion, and tabulation. So I guess I gave you like good introduction of what dynamic programming is, what to expect. Basically take a bigger problem and make bunch of different smaller problems, or do like a recursive approach and try to come up with like a smaller and smaller sub problem, and eventually store those results, and after storing these results come up with the solution. So that would reduce your time complexity significantly. And now without any delay, let's get started with the most important piece of our problem, and that is the 20 lead code problems. And I cannot emphasize enough on importance of doing these 20 questions, because I can guarantee you after this you would become a master in dynamic programming questions. The lead code problem we are going to solve now is called climbing stairs. We can see that this one is an easy problem and also a very well-liked problem. The statement is quite straightforward, that we are trying to climb a staircase that currently has n steps to reach at the top. Now, each time we have the option to either climb one step at a time or two steps at a time. Now we need to determine that in how many distinct unique ways we can reach to the top of the staircase. So let's try to understand this with an example. Suppose we are only dealing with just one single step. How many distinct ways we can reach to the top? Well, obviously there is just one way we can reach to the top, by taking one step. So in this case we need to return 1 as the answer. Let's say for the same example, instead of 1, what if we have 2 steps and now we are trying to reach to the top? What are the distinct ways? So first is distinct ways, take one step and then again one step, and second distinct way is to take 2 steps directly. So in this case we need to return 2 as the answer, that these we have 2 distinct ways to reach to the top. Same way, if we have 3 distinct 3 steps, how many distinct ways we can reach to the top? Well, we can continue by taking just one step at a time, so that is going to be our path number 1. Second path, we take 2 steps and then we take one step, or third path, we take one step and then we take 2 steps. So overall now we have 3 distinct ways to reach to the top. So this is what we need to return as part of the answer. Now let's try to understand the most common brute force approach to solve this problem. Well, the idea is quite straightforward. Let's say that we are currently dealing with 5 different stairs. Now at any given moment, starting from position 0, we have 2 options. First option is either we take one step, or the option is we take 2 steps. So let's make a decision tree based on that. Currently we are at step 0. What are the options we have? We can take one step and reach to step number 1, or we can take 2 steps and reach to step number 2. Same way, at 1 we can take one step and reach to step number 2, or we can reach to step number 3. Same way, we can reach to step number 3, or we can reach to step number 4, and over here we can reach to step number 4 and we can reach to step number 5. Now the moment we reach step number 5, this is one of the unique paths. So we will note this path down and keep on iterating with our possible choices. So once again over here we will have two choices, 4 and 5, and once again we will have here one more choice. But now notice that there is a big issue with this one. Why? Because at every single position we have two distinct different ways to choose from, and whatever path we take, depending on that, we are once again going to be dealing with two more positions. So in this case, the time complexity is actually going to be 2 to the power of n, which is a very expensive time complexity, and we will have to find ways to do things smartly. So that's where the most beautiful concept of the entire computer science come into the place, and that is called dynamic programming. Now notice over here that we are doing bunch of repeated work for the same amount of thing that we are calculating. We are calculating that what are all going to be all the different options from 2, and same calculation we are doing it over here. We are calculating that what are going to be all the different options from 3, and same thing we are calculating over here. So why don't we just memoize or store the information that we have already calculated and use it whenever we need to use it sometime in the future? And that is the whole idea of dynamic programming. So in order to do that, or in order to achieve dynamic programming, we will have to understand two things. What is going to be the base case scenario, or the minimum starting point for us to understand or start building the solution, and second one is what is going to be the dynamic programming correlation amongst different parties. So first let's understand the base case. Well, base case is quite straightforward. Let's say that if we are given 0 steps, how many different ways we can reach to the 0 steps? So we can only have one distinct way to reach to the 0 step, because where we are not taking any steps. Let's say if we are only given one step, how many different ways we can reach to the top? We only have one way to reach to the top, that is by taking one step. So these two are going to be our base case scenario, where dp of 0 is going to be defined as 1, and dp of 1 is also going to be defined as 1. So now these are the most common entries that are always going to be true and that we can calculate very easily. Now let's understand that what is going to be the dynamic programming recurrence relationship between or any given two parties. So for that, let's try to understand the scenario. We are currently dealing with these 5 steps, and we are trying to determine how many unique ways we can reach to step number 5. So the most simplest logic you can think of is that whenever you need to reach to step number 5, what are the ways to reach to step number 5? Well, one way is that either we reach to step number 4 and then take one step, or second way is that we either somehow reach to step number 3 and then take 2 steps. Now you must be thinking that there is one more way where we can take one step from step number 3 and then take one more step to step number 4. Well, we already covered this case when we first mentioned that whenever, like, all the different ways you can reach to step number 4 and then take one step. So overall we only have 2 unique ways to reach to step number 5, that is through step number 3 and step number 4. And once we are at either one of these locations, we are guaranteed to reach to step number 5. So all the ways we can reach to step number 3 are all the unique ways we can reach to step number 5. Same way, all the ways we can reach to step number 4 are all the ways we can reach to step number 5, and this is going to be sum of these two unique ways. So this is going to be our recurrence relation. Why? Because we have the liberty to choose from one or two steps, and if we do it like reversely, we can just calculate that, okay, we need to calculate all the ways to reach to step number 3 or step number 4 and do the sum, and that is going to be our recurrence relation. Based on that, we can actually create a mathematical formula that at any given moment dp of I is going to be dp of I minus 1 plus dp of I minus 2. And based on this equation, now we can solve all our problem very easily. Let's say that now we are trying to solve for the answer n is equal to 6. We already know that this is the formula we are going to use to solve this problem. On top of it, we already have the first two values being filled out. Why? Because dp of 0, 1, 2, 3, 4, 5, and then this is going to be the value number 6. Now for dp of 0, we already know it's 1, and dp of 1, we already know it's 1. So say based on this equation, dp of 2 is going to be 1 plus 1. So now we can notice that if we have to reach to step number 2, there are 2 unique ways to reach to step number 2, and same way has been proven by this equation as well. Same way for step number 3, the sum is going to be 1 plus 2. So we can do it 3. Same way, step number 4, we can do sum of these two values, so it is going to be 5. For step number 5, the sum is going to be 5 plus 3, so it is going to be 8. And for step number 6, it's going to be 8 plus 5, so answer is going to be 13. So there are going to be 13 unique ways to reach to step number 6, and the solution becomes quite easy and simple. And notice what we just did is, we first establish a base case, then we established that what is going to be the relationship, and then based on that we kept on populating further and further values. So even now, if we have to calculate for n is equal to 100, you can do it very easily and very quickly. So logic is quite straightforward. Now we can do one more improvement over here. Because we are only dealing with two previous values, instead of using an entire array to store all the values, we can just have two variables, previous one and previous two, and for every single value we can just resolve these values and keep on updating for subsequent current values. So we'll see this in code that how this can work, but basically this is the whole idea, and based on this you can solve this problem very easily and very quickly. If we see time complexity, it is going to be big O of n, and for space complexity, well, if you use a full array it would be big O of n, but if you just use couple of variables like this, it is going to be big O of 1. So now let's try to see the coding solution for this one. Now the coding solution is quite straightforward. First we are going to take care of the base cases, that if given n is equal to 0 or 1, we can simply return 1. If that is not the case, we are going to initialize two variables to keep track of the previous two steps values, and the initial values are going to be 1 and 1 for step 0 and step 1. Then we are going to iterate over the given loop, starting from I is equal to 2, or from the third step all the way up to the n. And for any particular current step, the number of ways we can climb up to that step is going to be sum of previous two elements. So we will add that, and then we will simply swap the values between previous two and previous one. So previous one is going to become the current value, and previous two is going to become the previous one value that we had before. And after we keep on updating that, in the end we can simply return previous one as the answer, and that would be the total number of ways to reach any particular nth step. So let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code beats 100% of all the other solutions, which is pretty awesome, and that is because this runs in 0 milliseconds. But anyways, this is a beautiful solution and a good introduction towards the dynamic programming. Hello friends, so now we are going to solve a very popular LeetCode problem called minimum cost to climbing stairs. This is the subsequent question to another popular LeetCode problem called just climbing stairs. So let's understand the problem statement. Basically, we are given an integer array called cost, where every single value inside this array represents the cost of to reach to that particular step in a staircase. Now, once you pay the cost, you can either climb one or two steps. The question is that we can either start from the very first step or the second step, so the 0th index or the first index, and we need to return the minimum cost to reach to the top of the floor. So let's try to understand this with a couple of examples. First example is that let's say that we are given an input array like this that contains three entries, 10, 15 and 20. Now we can see in this case that if we take one jump straight to the 15, now again from this 15 we have two options. We can either take a jump that directly goes to 20, or we can take a jump that directly goes above 20. So basically we are able to reach to the top floor. So in this case the answer is quite obvious, that if we are able to reach to 15, we can reach to the top floor very easily without paying any extra cost. So 15 would be the minimum cost that we need to pay in order to reach to the top floor. Let's take one broader example. Now we can see that this staircase has 10 different entries, and every single step contains a different price. The idea would be, if we decide to take two jumps in this case, which would be the greedy approach, it wouldn't work because we would incur a cost that is 100. Rather than, it would make sense for us to take one jump at this position number 1 with cost 1, and then take two jumps. Now once again, when we are at this position, once again it would take sense to take two jumps, because once again the cost incurred would be 1, and once again taking two jumps. Now after taking two jumps, Once again, it would not be wise to take two jumps directly because we would be encountering cost 100. Rather than that, we can actually take one jump and incur this cost 1, and through this 1 we can also skip over this 100 and take two jumps and reach to 1. So in total we are only taking 6 jumps, with each jump costing us 1 unit. So in this case, the minimum cost we need to pay in order to reach to top would be 6. So this is what we need to return. So the very first approach that comes to our mind is a very simple brute force approach. The logic is quite straightforward, that we actually calculate every single possibility. So we calculate a possibility like this, then we start to calculate the possibility like this, that taking one jump and then two jumps and three jumps, and then we calculate the possibility like this and then this and then this, something like this. So overall, across all the possibilities, eventually we would find a pattern that contains the minimum cost. But this is a very inefficient approach. We can clearly see why, because we are doing repeated work lot of times in order to comprehend the solution. We can solve this problem in n square time using the brute force approach, but this is still very inefficient. So let's try to see a better approach there where we can actually solve this problem. So now to solve this problem, we are actually going to use the most beautiful thing in the computer science and one of my favorite topics, that is dynamic programming. Why we are choosing dynamic programming to solve this problem? Well, first let me give you a very clear logic. If we have to choose any particular value, we will have to make the decision based on the previously calculated values, and based on that we would be able to define that what is going to be the minimum cost to reach to this step. Now currently what I'm suggesting is that we use a bottom up approach. So we go from the very first entry to the very last entry, and at every single step we simply calculate that if we have to include this step, what is going to be the minimum cost associated with this step. And let me show you what I mean. So currently we have no choice but to calculate that what is going to be the minimum cost to reach to these two values, and it's quite straightforward. We can always directly make jump to this very first step or very second step. So we can create a dynamic programming array, and the purpose of this array is going to be that we will calculate that what is the minimum cost it takes to reach to any particular element. And we know that for sure the minimum cost is always going to be these two values for the first two entries, because we can either take one jump or two jump. So let's just mark these two. But now when we come to this position, we have two options. Either we take one jump at this step number 5 and then two jumps directly to step number 3, or we take one jump directly to this step number 1 and then take one jump over here. So if we have to calculate the dynamic programming of this value, so let's say that this is currently index position 2, so this is 0, 1 and 2. Okay, so the dynamic programming equation is going to be quite straightforward. That dynamic programming of 2 is simply going to be cost plus dp of 1, or cost of that this cost defines the current cost of this index. Okay, cost plus dp of 0. So in this case, and whichever is the minimum value, we will pick that. So this equation is going to give us a lot of interesting results and build our dynamic programming array. So let's try to see our solution for the minimum cost it takes to reach to this step with value number 10. One option is that we do cost plus dp of 1. We know that dp of 1, the value is 1, so this is going to be value 11. And second one is cost plus dp of 0, so this is going to be 15, and whichever is the smaller, we are going to pick this. Which means if we have to use this step 10, then the minimum amount of work we will have to do is going to be 11. There is no other option, so we will just fill that value up. Once again, with this value number 2, we are going to repeat the same operation, and basically the logic is once again going to be quite straightforward. That cost at 2 is going to be dependent on these two entries, so 2 plus 11 or 2 plus 1. So 2 plus 1 is 3, so obviously it makes sense for us to give the answer as 3 and not 11. So we'll mark this entry. And once again, this is the top position, so once again the top position, the value is 1. Now if we have to include this one or not to include this one, the once again the logic is quite straightforward. We are going to compare the values of the previous two entries which we have already stored, and that is 3 and 11. So once again, if the total is going to be 4, that is the smallest entry we need. Now notice that we have the option to choose the minimum cost amongst these two entries. So whichever is the smaller value amongst these two is the one we are going to pick for the answer, because you can go to the top from this 2 step as well, and you can go to the top from this 1 step as well. So once again the minimum of these two is going to be 3, so we are going to return 3 as the answer in this case. And this is the whole logic I'm suggesting to solve this problem. Now ideally I created this dynamic programming array to solve this problem, but you actually don't need to have an entire array dedicated to solve this problem. You can actually just store all the entries in 2 variables, so you can also save so much time, so much space in terms of space complexity as well. Now let's try to calculate that what is going to be the time and space complexity for our optimal approach. Time complexity is going to be big O of n because we are iterating over the given input array just once. And space complexity, well obviously if you decide to use a dynamic programming array, then it's going to be big O of n, but if you just use 2 pointers, it can also be big O of 1 as well. So now let's see the coding solution for this one. So the coding solution is quite straightforward. First, we are checking for 2 edge cases, that if the given input only contains 1 or 2 stairs, then we can simply return those values accordingly. If that is not the case, we are just simply using 2 variables, first and second, and we would be updating these 2 variables continuously. Now we are starting our loop starting from the third step, or I is equal to 2, to the very end of the given array. And we are simply doing a very simple calculation. We are checking that what is the current cost for the current step or current ith value we are at. For that we are defining a new value, and we are simply calculating that what is going to be the minimum value of the first or second plus the cost of the current value, cost of I. Then based on that we are updating the values of our first and second. So now our first value is going to become the second value we had, and our second value is going to become the current value we had, which is quite straightforward, quite simple to understand. And after the end of our loop, we are simply checking that what is going to be the minimum value amongst first or second, and we can return that as the answer. So let's try to run our code. Seems like our solution is working as expected. Let's submit this code. And this is beautiful. We beat 100% of all the other solutions, and that's because this problem actually runs in 0 milliseconds. So no surprises there. But important thing is that look at the time complexity we are saving, or sorry, space complexity we are saving, where we are beating almost 90% of all the other solutions. So our solution is one of the best solutions on LeetCode. That's because we are using 2 variables. So once again, the solution of this code is present in our GitHub repository. Feel free to go ahead and check it out. Thank you. Hello friends, we are still not employed by a FANG company, so let's not stop lead coding till we get there. Today we are going to work upon a very important dynamic programming problem, coin change, and which in my opinion everyone should do it at least 2, 3, 4 times until you get a real grasp of the concept on how to solve it. And let's understand the problem statement. We are given an integer array of coins representing coins of different denominations, and we are also given an integer amount that represents the total amount of money that we want to generate. Now we need to return the fewest number of coins that we can use to make up to the amount that has been provided over here. And if the amount of money cannot be reproduced, we need to return -1. Let's try to understand this by an example. So in the given example, the number of coins we are given is 1, 2, and 5, and the amount we are given is 11. So based on the example, we can clearly see that the most optimal way we can create this 11 is by using 5 plus 5 plus 1. So in general, this sums up to 11. And if we see the number of coins, we are actually using 3 number of coins to generate this value. If we look at the second example, basically we are only given one coin, the value number 2, and the amount we are given is actually 3. So no matter how many times we use the number of coins 2, we cannot generate this amount 3. So in that case we need to return -1, while in this case we would be returning 3 because we are using these 3 coins. So once we have this clear, now let's try to understand that what could be the different approaches we can take to solve this problem. The first approach that comes to our mind is actually to use a greedy approach, where whenever we are given the number of coins, so let's take one of our own custom examples, and we also need to keep in mind that whenever you are solving or giving any FANG interviews, make sure to have your own custom inputs, because FANG companies really like this kind of stuff, and that shows that you are able to think outside of the box and you can also create test cases on your own. So suppose we are given an input like this, and the amount we need to create is actually 8. So in our greedy approach, basically we at any given moment for the given amount, we will take the biggest coin that is smaller than this amount and keep repeating till we reach this amount. Now let me show you that why this approach won't work. Because if we see here, the amount we have is 8, and the biggest denomination of coin we can create that is lesser than 8 is 6. So if we take this, so let's create our answer where we keep track of how many coins we are using. So we use 6 over here, we take 8 to 6, so we subtract 6 minus 8, we get the remaining value is 2. So since the remaining value is 2, we cannot use these 3 coins anymore because they all are greater than 2, and if we were to subtract this coin from 2, our result would actually become negative. So we cannot use that, but we can still use value number 1. So if we do that, and if we use the coin number 1, because this is a greedy approach, so we will add the coin number 1 to our answer as well, and so now the remaining value will be 1. So again we cannot use these 3 values, but we can still use 1, so we will use 1. The remaining amount is 0, which means that we have reached our total amount of 8, and we would add the value number 1 over here. Once we do that, essentially if we calculate in the answer, we are using 3 separate coins to reach the amount 8. So our answer would be 3 in this case, and we would return 3. But notice that this answer is actually not the lowest number of coins we can use. Actually, if we just use the coins 3 and 5, we can simply create this value 8, and our result in this case should actually be 2, not 3. So greedy approach doesn't work at all. Now let's see what could be the next approach we can take over here. We are given an input like this, and we need to reach out to a particular amount 8. So at any given point, if we basically start calculating from 0, and we will keep on making choices based on the number of coins we have until we either reach to this value 8, or our choices actually becomes greater than 8. Until these two things happen, we can keep on making choices given our coin denominations, and based on that we can actually create our own decision tree. And in the decision tree, whenever we reach at value number 8, we will keep track of the value, keep track of the path, and based on that path we can calculate that what are the minimum number of iterations we have to make. So initially we are at 0th position. So from 0th position we have 4 options that we can take. So let's make these 4 decisions: 1, 3, 5 and 6. Now at every single decision we still have 4 more decisions that we can take to reach out to this value 8. So again at value number 1 we still have 4 more decisions we can make. So let's do that. And again at every single iteration we still have 4 more decisions, and with every decisions we come closer to this value number 8. So initially over here complete 8 were remaining. Over here we are only dealt with creating the value 7 because we already used one coin. The remaining value would be 7. So over here the remaining value would be 1. Over here the remaining value would be 2. Over here the remaining value would be 4, and over here the remaining value would be 6. And suppose we continue on this path again, we would still have 4 choices. And notice that the remaining value we wanted to create was 6, which we are able to achieve over here. So the sum for this particular path, 1, again 1, and then again 6, is actually 8, which means that we have found a potential route. And if we see the number of coins we had to use 1, 2 and 3 coins. So current amount, current answer we need to return is actually 3. And since we have found this route, all the other routes, if you see, the values would not reach to 8, and we can cancel out these values. And basically because if we keep going on, we will still have to make more decisions, and the number of route will definitely be greater than 3. So we can start eliminating these routes, and we have one potential route over here. Again, if we keep on going down this path of 3 and keep making more decisions, we would end up with a result that would be greater than 3, or we would not reach 8 at all. So we can ignore this. Again, we can ignore this from 5, and at 6 we would still find a route something like this, where, because notice even at 6 we still have 4 decisions we can make. So we can choose either 1, 3 or 5 or 6, and notice that only 1 is remaining over here, and we can select this one. So we would have another potential route starting from 1 going to 6, and then again going to 1, that sums up to 8. But again, for this route as well we need to use 3 coins, so our answer will still remain 3 and it won't be changed. But this is where we find another answer. And now we have exhausted all the possibilities from value number 1, so we can just ignore all of this. Let's get rid of it, so we have something that is more clear and not so much congested. Now let's try to see that what could be the possibilities from this value number 3. So even at value number 3, the remaining amount we have would be 5, and at value number 3 we still have 4 more possibilities that we can choose from: 1, 3, 5 and 6. And notice that in all of these these 3 possibilities we would not reach 8. So we would not reach, basically the remaining value would not be 0, which means, but if we get down over here 5, over here only 5 is remaining, and we directly have a coin 5 present at the decision tree 3. And if we calculate the route would look like 1 and then 2. So basically we are only using one coin over here, and we are using second coin over here. So we are only using 2 coins to reach to this value 8. So we can simply update our answer, that we have found a new minimum value that can come up as our answer, and we can set the value as 2. Now we can continue to search and keep on making more decision trees, and even for those nodes we will continue to making further down decisions to see if we can find a better answer. But we won't be able to find a better answer than 2, and eventually we would have to return this value. So this solution, in a way, it works, and it works as expected. At least we are getting the answer. But the issue with this approach is that time complexity is actually so bad. It's not even in polynomial time, it's simply in exponential time. And the time complexity, suppose the amount we are given, if we consider it as m, essentially until we reach this amount m, we are at every time keep on making multiple decisions based on the number of coins that are given. So we can compute the time complexity as big O of m to the power of n, where m is the given amount and n are the number of coins that are present at any given moment. This is such a bad time complexity that we, even if we ask NASA to run this command, they won't be able to do it more than up to a certain values, and we need to find a better approach. And in the optimal solution, we are simply going to use just two golden words: dynamic programming. And let me show you how we can solve this via dynamic programming programmatically. And we are just like a rational person. We are just going to think it in terms of intuitively, that if we are given this problem just to solve on a pen and paper, how we are going to do it. And one approach is that we can basically start from the value number 0. We can keep on reaching towards the amount we want to reach out to, and for every single element that we have found, we will find that for 1 2 3 4, how many number of coins it took us to generate that particular amount. And once we are sure with this value, whatever value we have generated, the amount for 1 or amount for 2, we would be able to use this later down the road. And let's take an example. Let's continue with our example and see how can we achieve that. So we are given the example 1 3 5 and 6, and the amount we want to generate is 8. So initially we would create an array of amount from 0 all the way up to amount of 8, and we will initialize all the values by any value that is higher than 8. So let's say 8 plus 1, and now we will start with our solution. So far all the values are actually 8 plus 1 in this amount array, and this represents that these are the number of coins that are needed in order for us to generate any particular value. Now if we just want to generate 0 coins, how many number of coins do we need? Well, answer is pretty trivial actually. We simply need 0 coins, and this becomes our base case. So now let's say for the second value, amount of 1, that if we want to generate value number 1, how many distinct coins we need. So whatever value is, we will check first of all in our coins for all the values that are given in the coin, to see if we can directly use, if the given coin is lesser than the value we are trying to achieve, can we use that coin. So since the value is 1, we can clearly see over here that this 1, if we just use one coin, we would be able to generate this value 1. So the answer in this scenario becomes pretty simple, that if we just use one coin, we would be able to generate this value. And notice that for value number 1, we cannot use any of these 3 coins because they are all greater than our value 1. So there is no point in using them. Now let's repeat the process for amount 2. So for amount 2, if we want to generate the value 2, how many minimum number of coins we need? So first of all, let's check with the first value. Okay, so coin is actually less than 2, so we can use this coin. We will use this coin. So if we use that coin, basically we have already used one coin so far, and since we use coin number 1 and we want to achieve value 2, we can say that now the value we are trying to generate is actually 2 minus 1. So again, value number 1. Now we want to generate value number 1, and if we can do either two things. Either we can go back to all these coins, again we try to generate that value, or notice this beautiful thing over here, that we have already calculated that if we want to generate amount 1, how many coins we are going to need. So why are we being so picky, and why are we doing all this extra work, and why are we making our lives miserable, our CPU's life miserable by doing all these additional calculations? Why can't we just store this somewhere? And if we have stored it, we can simply use it over here. So in this case, we can say that we have already used one coin in order for us to generate this one. And now once we have generated this one, we know that the number of coins that are needed to create value 1 is already computed. So we will do 1 plus amount to generate one coin, and this would be the answer if we want to generate the value 2 from the given coins, and this would become 1 plus 1, so 2, and this would be our direct answer. And these are the minimum number of coins that we can use to generate value number 2. The reason I'm emphasizing so much on this is because this exactly is the core concept of dynamic programming, and we have just hit a very big hammer to its head. Basically, we have said that, hey, I'm going to take this dynamic programming all the way, I'm gonna chew it, swallow it up, so it becomes a second nature to me. And now let's continue with our example. This is going to be a really long video, and I recommend that if you just understood at any point, I would just suggest you to go ahead and start skipping over. So now the value for amount 2 is actually 2. Now let's calculate for amount 3. If we look at for amount 3, we have two options. Either first of all we can start with this value 1. We'll take value 1, then again the remaining value would be 2, and we have already calculated that what is the amount that is remaining for value number 2 over here. So if let's take that approach just for the sake of understanding. So first of all, we use coin number 1. So we use coin number 1, and plus the amount that is remaining is actually 3 minus 2. So we still have amount 2 that needs to be computed in order for us to achieve this value 3. So we can say that for this one, the way we can do it is one coin that we already used plus whatever the amount 2 that we need to use. And notice amount 2 has already been computed over here. So we can say that 1 plus 2 equals to 3. So if we choose one of these coins and we try to achieve the value number 3, initially we would be able to find our answer by using minimum of 3 tokens. Now again we notice that now since we have computed this coin, we notice that value number 3 is actually less than or equal to this given coin 3, and we can use it to our advantage. So now we know that we want to achieve value number 3 over here. If we just use this one coin, we would be able to achieve this amount number 3, and current minimum amount that we have calculated that is that we need minimum 3 coins in order for us to achieve value number 3. So why are we using 3 coins? Because our aim is to use the minimum number of values. So we can simply just say that if we just use one single coin that is of denomination 3, we would be able to calculate the result as 3 for this amount 3, and we won't be able to do anything with these two because they are already greater than 3, so we can't make 3 with those denominations. Now let's move forward with our with the next value, amount of 4. And if we generate the amount 4, how many number of coins we need? So basically, if we just take this first coin, we know that we have already used one coin, and plus we have the value remaining as amount 3. Amount 3 is already computed. We are using the best knowledge of computer processing we can, and based on that we can simply determine that, oh, and by the way, this would be 1, not 3, my mistake. So we can just simply say that if we want to generate amount 4, we can do 1 plus amount 3 is already 1, so we can use 2, and this would be the minimum solution, that even if we use the first coin as 3, we would use second coin as 1, and still we will get the same answer. So I'm not going to do whole computation, but you get the idea. So for amount 4, we can say that 2 are the minimum number of coins we need in order for us to generate amount 4. If we want to do amount 5, how many coins we need? And the answer is pretty simple. We already have this 5 present over here, so we can just simply write 1. And notice that we are going to check all the coins, and when we get to 5, we will be able to say that this is the minimum number of coins we can use. Next is amount of 6. If you want to generate amount of 6, again the answer is 1, because we are already given a 6 over here, and we are going to check through all the coins that are less in the value of whatever the amount that we are trying to calculate. Now let's calculate for amount of 7. If we are calculating for amount of 7, and if we check for the first coin, the first coin is actually 0. So basically we can just simply say that the first coin is actually 1. So basically we can just simply say that we have already calculated the 1 coin, plus now we need to calculate the amount 6, because 7 minus 1 is equal to 6, and we already have the result for amount 6. So we can just simply write that we need at least 2 coins in order for us to generate the value number 7. And now let's try to calculate our output that we have already given that we need to calculate the 8. So if we want to calculate amount 8, and based on this table, it becomes pretty simple. Initially, so first of all, we will calculate this with value 1. So basically we would be doing the calculation something like 1 coin that we have already used plus amount of 7. And we know that amount of 7 from our previous computation is actually value number 2. So we will do 1 plus 2 equals to 3 for this amount 8 that we are trying to calculate. But can we do something better? And remember that we are going to check all the coins. So because we are going to check all the coins, when we get to coin number 3, our solution would be that we have used 1 coin, and that is the coin value is 3. And because we have used 3, now we need to generate the amount 8 minus 3 equals to 5. So we can say that we used 1 coin to generate the value 3, and now we need to generate value 5 in order for us to achieve this amount equals to 8. So if we do 1 plus amount of 5, what is the answer? And the amount of 5 is already calculated over here as 1. So we'll just simply use that value, and we'll do 1 plus 1 equals to 2, and we will carry on with our computation with this value 5. Again we will find the answer 2 because we will do 5 plus 3, and when we get to value number 6, we will again find the answer to generate the amount 8 as 3, because we will do like 6 plus amount of 2. So the minimum number of coins that we can find in order for us to generate value number 8 is actually 2, and we can simply return this value 2. Now notice that we also have to take care of the scenario where we cannot create the amount based on the given coins, and if we cannot create the amount at the end of our computation, the value for amount would amount of any given, let's say 8, that we cannot compute in this case, would actually be the value 8 plus 1, so equals to 9. Because notice that at the beginning of our array, this is how we initialize the values to. And if after all the computation we found that the value of amount is actually the original by default value that we set, which is amount plus 1, if that is the case, we know that we are not able to generate this value, and we are not able to make any impact with our solution because the coins cannot generate this value. We will simply return -1, and this solution would work perfectly fine. This is a really beautiful solution, and if you go through with this approach in your interview, you are gonna just be very impressive candidate, and all the FANG companies would want to hire you. So let's calculate the time and space complexity. So time complexity for this one would be actually big O of n times m. Now why n times n? Because we are running the loop to calculate the value n, and n is actually the value of this amount or whatever is given. So we are going through a loop n times, and m are the number of coins. Because notice that over here for every single element we will have to go through all the coins in order to generate the value. So the time complexity would be big O of n times m, and the space complexity would be big O of n, because we are creating an additional data structure array to store all these values, and the values we are storing up to is actually the amount, whatever amount we are given. So we can say that the space complexity would be big O of n. Okay, so let's create an array amount, and its size would be amount plus 1. We fill out all the values inside the amount as amount plus 1. This would help us determine that whether if we cannot create the value, we need to return -1 or not. And now we will set up the initial value for amount of 0 would be 0. Now let's create our loop. So we will start with I equals to 1, because we have already calculated the value for amount 0, and while I is less than or equal to amount. Now notice that for every single value of I, we need to calculate for all the values of coins. So we will have another loop that would iterate over coins. And first of all, we'll check that if our present I is actually greater than or equal to whatever value of coin that we are comparing it with. So if this is true, then only we will check that whether what is the amount for any given j, any given I. So we'll do a minimum value of either the value itself, so whatever value we already have, or we will take one coin of any j and we'll do an amount of I minus j. And yep, this is the main logic, because in this logic we are calculating all the amounts, and we are using it further down the road as well. So after this iteration, we just need to check that if for any given amount, so amount of amount, if that is less than the value amount plus 1, which means that we have been able to generate this amount. So in that case, we would return whatever the value we found, else we can simply return -1. Let's try to run this code. We made a silly mistake. Again. Oh, we need to check with coins of j. Yeah, looks like our code works. Let's try to submit this. And yeah, our submission is actually pretty efficient compared to others who have submitted. So I hope you like this video. It took me a lot of time to make it, and I know it was a really long video, but it was, believe me, it's equally informative. Once you master dynamic programming, you are almost guaranteed that you at least have a foot in the door for Fang. And yeah, we are not gonna stop till we clear Fang. See you. Hello friends, we are still not employed by a FANG company, so let's not stop lead coding till we get there. Today we are going to do a very important lead code problem, Decode Ways, and this problem has been asked in a bunch of different FANG companies like Amazon, Google, Facebook, Microsoft, Uber, Lyft, Apple. So I highly recommend that you focus full attention to this problem. This is the breakdown that we are going to do for this problem. We are simply going to understand the problem first. We are going to see a brute force solution. Based on the brute force solution, we are going to see that how can we create an optimal solution, and eventually we will write the Java code for that. And this is a lead code medium problem, and we are given a note that basically a message containing letters can be encoded into numbers using the following method. So A is 1, B is 2, and up until that, if we keep doing that, Z is actually 26. And we are given a string of S that contains digits, and we need to return the number of different ways we can decode it. So let's understand this with an example. Suppose our given input S is equal to 12. We can decode this in two ways. So one way to decode this would be to consider 1 and 2 as separate elements, and 12 by itself as a single digit. So this the value for 1 and 2 would become A and B using this logic, and the value of 12 would become the letter L. So we don't need to return these values, we don't care about them. The thing is, we need to return that how many different ways we are decoding this given input string, and in this case the answer would be 2. Let's take another example. So suppose our given input S is equal to 226. How many times, how many different ways we can decode this one? So one way to decode this one is 2 and 26. So that's one way. The second way to decode this one is 2 or 2 and 6. So that is second way. And the third way to decode this one, 22 and 6. And if we check out the values, so this would becomes B Z, this would becomes B B F, and this would become V F. So over here we can see that there are three ways we are decoding this given string. So in the answer we will return the value as 3. Now let's consider one more case. Suppose the value 0 would be a special case, and there could be multiple possibilities where 0 can appear. So suppose our given input S is something like 0 1 1. So in this case we won't be decoded in any manner, because remember that our range starts from this value number 1 up until 26. So 0 is not part of the range, so we cannot begin our string with value 0 at the beginning. So this won't work. Second possibility, that 0 could be somewhere in the middle. So suppose our given input S is equal to 1 0 1, something like this. So in this case we cannot decode this in 1 and 0 1. We can't do this. Why? Because we can't decode this 0 1. Because remember that in this scenario, if 0 comes at the beginning, we can't decode it. The way we can decode this is, we can consider this as 10 and this as 1. That value of 0 can appear at the end. So our input string S can be something like 2 0 0. So in this case we can decode this value 2 0, but we can't decode this 0. So we won't be able to return anything. Or our value S can be 5 2 0. So in this case we can decode this. We can decode this value 5 and we can decode this value 2 0, because 2 0 is again between 1 to 26. But if we are given something S is equal to like 5 7 0, we can't decode this, because we can decode this 5 but we can't decode 7 0, because 7 0 is not part of this 1 to 26 range. So when value 0 comes in, it becomes a little bit tricky and we have to just take care of it. For brute force approach, let's take a custom example. Suppose our given S is equal to 2 1 2 3, and we need to see that how many different ways we can decode this one. So brute force approach is pretty simple. We just take all the possibilities starting from the first value and keep moving and keep building our solution, and when we reach at the end at any given path, we consider it as a one way to decode it. So initially we can decode this as 2 and whatever the remaining value 1 2 3. We can decode this further into 2 1 and whatever value remaining, again same thing, 2 1 2 and this 3, and in the end we can decode this as 2 1 2 3. So this would be one way we would be able to decode this. So where if we treat all the values as separate entities. Now let's see. Let's go back and see that can we have more possibilities. So over here we cannot have any more possibilities because this 2, 1 and 2 are already being decoded, and this 3 we only have one possibility to decode it by itself. So we don't have any possibility over here. So we go back further up. Do we have any possibility over here? So yes, over here we still have possibility that we can decode this 2 and 1 the same way we have decoded over here, but this 23 we can decode it as a single value. So of course we reach at the end of the loop. So this is one more possibility on how we can decode it. Now let's go back. So for this value 123, of course we still have more possibilities, because over here we are considering this value as 2 and 1 separately. So over here we will consider this as 2 as already being decoded, and rather than considering this as 1 as separate character, we can also consider it as 1 2, and then we can decode 3. So this can also be another way. So we'll just mark it. Okay, now we have exhausted all the possibilities over here, considering this value. If we start from this value number 2, so we come back at our main point, and let's see that what are the more possibilities we can have over here. So we can do, rather than choosing 2, we can choose 2 1 and whatever the remaining stream. So remaining is 23. Okay, now let's see that how many different possibilities we can have over here. So we can have two possibilities now. We can do like 21 2 and 3, so that is one option, or we can do 21 and 23, so that is second option. And yeah, both would be separate ways, and apart from these we cannot make any other possibilities. So essentially we can say that there are 5 different ways to decode this 2123 string, and those 5 ways are mentioned over here. Uh, what is the problem with this brute force approach? Well, the problem with brute force approach is that actually we are doing a lot of repetitive work. How we are doing repetitive work? If you notice over here that we know that we need to calculate that for this 23 how many different ways we can compute this one, but this 23 we have already computed it over here. So since we have already computed it over here, it is not very fruitful to compute the same thing twice, and in brute force we are not doing it. So that is why our path will keep on growing and growing until we reach to our all the possibilities, which means that we are actually doing exponential work for this brute force approach. So of course the time complexity would be big O of 2 to the power n, which is really bad, and we should avoid it in all cases. And actually it can be avoided pretty simply if we just use memoization. If we just create an additional data structure, something like an array or something, where we store the value of calculations that we have already done, and if we at any point come back to the same calculation that we have already computed, we can simply return that value. So we can use something like an array or hash map. I think hash map would be more efficient in this case because we are able to look up things in constant time. And if we only apply that, we can actually implement this solution, this brute force solution, in very effective manner. We can actually use recursion because remember, at every single moment we are repeating a sub problem. So we are repeating a sub problem and we are computing that. So if we just use memoization with recursion, so for this approach, we can actually achieve the answer in time complexity of big O of n, rather than this 2 to the power n, and that would be really efficient. Okay, before I go into the optimal solution, I want to show you a few observations. Suppose our given input s is equal to 7. So how many different ways we can decode it? Of course, only one way. We can just use 7. Suppose our input is 7 7. We can still only decode it one way using like 7 7, and that would be the only way we would be able to decode it. even if our value is 777, 7777, whatever the value we have, all of these can only be decoded just one way, because all of these values, they are forming a value where we can only use individual characters. Now, what is the scenario where we can use the characters that are not individual and we can collectively use the pair of elements? Okay, now let's take one more example. S is equal to 2, 1, 2, 3. And now let's try to see that how many different ways we can decode this one. This is the same one we have used in our brute force approach. So we know that there are 5 different ways we can decode this one. The thing is, we are going to do things a little bit differently over here. We are going to decode all of these values. So first we'll start with value number 2. How many different ways to decode this one? Only one way, and that way is 2. Now let's consider the second value, 21. How many different ways to decode this one? Well, of course, two values or two different ways, and those ways are 2, 1, so that is one way, and second one is 21 by itself. And let's take the third value, 2, 1, 2. So there are actually 3 different ways to decode this one. So let's consider the next value as 2, 1, 2, 3. So we know that for this one, there are actually 5 different ways to decode this. And the 5 ways are, okay, you must be thinking that why am I writing all these letters? Because the thing is, there is actually a very important relationship that exists whenever we find out, whenever we add a new value to our calculation, and if that value that is being added, if the previous value of that with that particular value, if that falls between this 10 to 26, actually something interesting happens. So notice over here that this 21 came in. Okay, we are checking for this value number 21. Now the thing is, just for a second, imagine if this value was actually 27. So how many different ways would we be able to decode this one? Well, only one different way, and that one different way would be 2 and 7. So treating both values as separate values. Same goes for 28, 29, and any value above. But the thing is, because this value falls between this 10 to 26 portion, we are able to do something interesting. So notice that whatever value we append over here, there will always be one way to decode it. I'm not talking about the value 0. Forget about 0. Apart from 0, if there was any other value, the way to decode it would be to whatever the way we have been decoding the previous value. If we just add that value, then that would be the way to decode it, which is over here. That 2 and 1, we are already decoding it with whatever value we were decoding before, and we were using that way. But the thing is, over here, this 21 by itself falls under this 10 to 26, which means it is a letter by itself. So we are able to add it to our decode list, and that is why we have 2 over here. Okay, but now the interesting part comes in. Okay, now over here we are adding one more 2, and this 2 falls between the values 10 to 26, because the appending value becomes 12. So this 12 falls between this 10 to 26. Now let's see that how many different ways we are creating the pairs. Actually 2, 1, and 2. This is same from whatever the pair we had before, just one iteration before. Okay, now this 2, 1, we already had a 2, 1 over here, and we are just appending this value 2 over here. So that is also okay, because we can append it, right? So whatever the ways we were decoding before, we are still using those ways. But the thing is, over here something interesting happens, because this 1, 2 by itself is a way to decode. We are actually able to create this 2, 1, 2 pair, which we were not able to generate over here. We are not able, I mean, we are using this 2 over here, but the thing is, we are using it for 2, 1, but we can't do anything further than that. We are already also using this 2, 1, 2 over here. And how can we say that we are using this 2, 1, 2 over here? Is because this value is basically 12, falls between 10 to 16. But the thing is, this 2 actually comes from the first value, this one. And why? Because at any given moment we find out that there exists a pair with the new value being added, and that comes between this 10 to 16. We can actually do sum of previous two values that we have calculated so far, and the sum of these two would actually give us the number of different ways we can actually decode this one. If you still don't believe me, let me show you with another example. Let me clean this up a bit. Now over here we are seeing that 5 distinct pairs are being made, and we are adding a value 3 over here, and we know that this pair 23 exists between this 10 to 26. So that is all okay, right? We know all of these stuff. Now let's see that how many different ways we are generating the pair. So one way is 212, and we are just appending 3. This would be the case even if the value was 2129. If the value was 2129, we would still be able to use this way, because apart from this 3, there would be a 9 over here, but that's not the case right now. But the thing is, we would still be do it. And if you look over here, this is the same path we were taking, and we are just adding one more node, so no impact on the number of results. Second pair we are making is actually 21-2, and we are appending 3 over here. Again, that is the case over here, that we already had a 21-2 and we can append 3 over here, so that gets taken out over here. If we had the 21-29, we would be appending 9 over here, so that still remains common. Okay, there are no issues with that. Now next pair over here is 2 and 12. So we also have a 2 and 12 pair, and we are adding a 3 over here, which means that even if we had this 9, we would still be adding 9, and that would be it. We don't care about it. But the thing is, if we had this 9, we won't be able to generate these two pairs, because notice in these two pairs we are actually creating an additional value by the value that has added over here. And if this value was not between this 10 to 26, this value would not be able to be generated. Okay, now the question comes that we have already exhausted all the possibilities over here. So where does these two additional values comes from? Well, actually, if we look above over here, this one is actually 2 1, right? So we are also using 2 1, and we are creating a new decode node 23, and we are appending it over here. Also notice over here that this one is 2 1 and this one is 2 1, so we are appending a node over here 23, which means that at any given location, if we want to see that how many times we can decode it, if we know the information of previous two elements, and if we do sum of those, we can actually generate it. So that's why the value for this 2 1, this can be decoded 2 times. This value 212, this can be decoded 3 times. So for the value 2123, actually this 23 falls between 10 to 26. That is okay, that is perfect. If that is the case, we simply do an addition, and if we do an addition and we just find whatever result we have calculated, and we can simply return this. This is a very effective solution. Now what could be the other case? Well, the other case could be that the new value we are adding, that does not fall between this 10 to 26. So suppose over here the new value we are adding, suppose the new value is 2128, something like this. So after adding this new value, this becomes 28. It does not fall between this 10 to 26. Because it does not fall between this 10 to 26, actually we don't need to do addition over here. We simply need to, whatever the route we can make before this element, that would be the only possibility we would be able to decode this one as well, because that I just showed you over here, that over here I was adding a 9, and because I was adding a 9, I was only able to make the new decode paths for these 3 elements. I won't be able to generate these 2 values, and this becomes our recurrence relationship, and this actually becomes our dynamic programming solution. Now let's try to solve this dynamic programmatically. we know that we care about the two previous elements. So suppose our given input is like 2 1 2 3. We initialize two values before that as 1 1. Say we have these two as 1 1. Now we check at any given location that whether the value we have, does this value with its previous value, does it fall between this 10 to 26? Okay, in this case this 2 does not fall between 10 to 26. If it does not fall between 2 to 26, we just need to take whatever we had from the previous element. So previous element over here we had 1, so we'll just take 1. Okay, now we have this 1. So again we check with its previous element that whether the value falls between this 10 to 26, the value becomes 21. It falls between this 10 to 26. So we do whatever the previous two elements were, we do sum of it. So the previous one element is 1 and the previous second element, this one is also 1. So we do 1 plus 1. So we can put 2 over here. Now we have new element. This falls between this 10 to 26. That's good. So we do sum of two previous elements. Sum of two previous elements is actually 2 plus 1. So we can put 3 over here. Now we have this 3. Now it creates the value 23. Again falls between this. So we can do sum of 2 plus 3 and that becomes 5. And this 5 would be our result. So this is a very important dynamic programming solution. And at any given moment, if we find out that suppose over here we have an value 8. Now this 38 does not fall between this 10 to 26. So it becomes simple that for this pair, the number of ways we can decode this will still be 5, because we'll just take whatever value we have calculated over here. This solution works perfectly fine, and the time complexity for this case would be big O of n, because we only need to do one iteration across all the strings, and the space complexity would in this case would actually be big O of 1. We would be able to complete this in constant space and time, because remember that at any given location we only need to keep track of just two elements. We don't need to keep track of this whole entire array. We just need two starting elements, and we would keep on iterating them over different values. So this is a very good solution. And okay, first of all we'll check that whether the first element is 0 or not. If this is the case, we can simply return 0. Okay, so we will create two parameters, 1 and 2, and we will initialize both to value 1. Let's run a for loop. We'll start the loop from first position and we will go up until the length of the given string. We are running it from I equal to 1 because we already checked for the 0th position. First of all, we create a value current to keep track of the current element, and now we check that if the current if the new character that we are trying to add, if that is not equal to 0, we can assign the value of 1 to current. Now we also need to check that after we are adding the value at ith position, are we getting the 2-digit value between 10 to 26? So first of all, let's create a new variable called value, and we will try to calculate the 2-digit value. We check the condition. So if value is greater than or equal to 10 and value is less than or equal to 26, which means we need to update the current value is current plus whatever the value of 2 we had, because remember the value at current we are already adding it as 1. Now we need to update the values of 1 and 2. So 2 would become whatever the value of 1 we had, and 1 would become whatever the value of current we had. And yeah, I think this would be our solution. So at the end of the solution we need to return the value of whatever the current value we had, but since we are initializing current inside, we'll just return the value as 1, and let's try to run the code. Oh, we can initialize the current as 0. Let's try to run the code. Okay, looks like our solution is working. Let's try to submit the code. Okay, our solution works pretty fast and pretty efficiently. So I'll be posting the solution in the comments. You can check it out from there.
Friends, I'm a cloud solutions architect who like to solve lead code problem, and today we are going to solve a very interesting lead code problem called Pascal's triangle. Now, if we see some of the popular companies who have already asked this question, there are companies like Amazon, Bloomberg, Google, Apple, Microsoft, Goldman Sachs, TCS, Uber, Facebook, and Infosys. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a lead code easy problem and also a very well-liked problem. Basically, we are given an integer array called number of rows, and we need to return the first number of rows of a Pascal's triangle. Now, the biggest question in this problem is what the heck does this Pascal's triangle means? They have actually drawn a diagram over here, and you can try to understand it using this. But I'm actually going to show you an animation that what a Pascal's triangle is. Okay, so now we are actually trying to create the Pascal's triangle, and for that I found a definition online. If we read through the definition, this is saying that, okay, in order to build the triangle or Pascal's triangle, basically we need to start with 1 at the top, and then we need to continue placing numbers below it in a triangular pattern. Okay, that's a given fact. Second thing it says is that each number in the numbers is the combination of the two numbers above it added together. Let's try to understand this with an example. So over here we are trying to build a Pascal's triangle with 6 different rows, and I have drawn 6 rows over here. After marking their numbers, based on this definition, okay, first value has to be 1. So we are starting the first value as 1, right? Now what it says is that every single number is the number that is combination of two numbers directly above it. Now if we see this first box is only connected with one box at the top. So definitely the sum of this value is going to be that value by itself. So this is also going to be 1. Same with this value is also going to be 1, because both of them are only connected with one box above it. That is the key phrase, that one box above it. Same way, if we try to take a look at this box, this is also connected with just one box. So because of that, we are also again going to add 1 over here. But when we reach to this particular middle box, things become interesting. Because if we see this above part is actually connected with 2 different cells. So because it is connected with 2 different cells, we are actually going to do sum of these two. So 1 plus 1 is going to be 2 over here. And again, remember, this 1 plus 1 is coming by sum of these two values. Why? Because this particular cell is connected with both of them. Now, if we go back, okay, this one will always be 1 because there is only one element. Now again, this is also going to be 1 because it's only connected with just one element. But in this case, this particular element is again connected with 2 elements. So we are going to do the sum of it. So if we do sum of it, we get the value 3. Again, this is also connected with 2 elements. So sum is going to be 3. And this is only connected with one element. So sum is going to be 1. Same way we keep on repeating for the row number 5. So again, this is going to be 1. Now this is going to be sum of these two, which becomes 4. Now this particular element is going to be sum of these two elements, which is going to be 6. This element is going to be sum of these two, which is again going to be 4, and then again 1. Keep on repeating the same process. And this is how all the rows are being formed. And this is a Pascal's triangle. So in this case, we created a Pascal's triangle with 6 different rows, and we need to provide this as the answer. So as an input value, we are only given this element, that how many numbers of rows we need to create, and in the answer we need to return this one. And now the answer for these is needed to be written in a specific format so that our program can understand. And the format looks like a list of lists. So first we create an array list, and every single value represents all the values inside this particular row. So currently the first row only has one element, so we are only going to add one element over here. Now for the second row, it has 2 elements, so we are going to add 2 elements over here. Again, for the third row, it has 3 elements, so we are going to add all 3 elements over here, and so on and so forth. We keep on adding all the values, and in the end we return the answer. And this is the answer that is expected in this case, right? Now basically I think this makes understanding much more clear that what a Pascal's triangle is. So now I have created a Pascal's triangle that is needed for like 7 rows, right? And for 7 rows, definitely I already showed you that how we are populating all the answers. That first this value is 1, this value is 1, 1, then again this value is 1, 2, 1. Okay, so this is the Pascal's triangle that we can create for 7 rows. But if you observe the answer, basically first of all we need to define that how the answer is being generated over here. The answer for any single cell is dependent on its like further value. Same goes for any single possible cell. That cell is made up or comprised of the 2 cells that are exactly above it that it is being connected to. Now that is okay, that is one property. Second property is that in order to generate any single cell, how can we find its value? Well, we can simply find its values based on that if we have some way to store the value of the previous row. If we have that value, definitely we can able to generate the answer. And the thing is, because any single result is based on the results of its previously computed values, we are actually reusing the same value that we have already used, which means we are actually going to use the most beautiful concept inside the computer programming, which is dynamic programming in this case. Now for this dynamic programming, what we need a base case. So base case, what is going to be, that is already given in the definition of Pascal's triangle, that the first triangle is always going to be 1. So that is okay, that is a given fact, right? That this becomes our base case. Now based on this base case, I just showed you that we are able to generate any single triangle of any single length. In this case the length was 7, so we were able to quickly generate that. So the logic we are going to use in this case is that okay, first we calculate the first value, we get the answer as 1, right? We store that answer. Now for the second column, okay, first what are the things we know about the second row? The thing we know about the second row is that there are going to be 2 elements, right? Now for this 2 elements, what is the thing we have? The thing we have is that we have one element that is present before that. Okay, so in this case, the first element is only possible to be connected with just one element. So since we have already saved that answer over here, we can simply leverage that, and same goes for the second element, that can only be connected with one element. So we can also store that answer over here. Okay, now we are at the third position. Now for the third position, what is the logic? So the first value is always going to be 1. So we can by default mark the first value to be 1, and also the last value will always be 1 as well. So we can also mark the last value to be 1 as well. Now for the middle values, what we are going to do is, okay, so currently if we see the index position of this middle value, the index position is going to be 1. Why? Because there are 3 elements. So in a typical array, the index position is going to be like 0, 1, 2. So this is like the first index position. Now we already know we are trying to populate this third value. And for the third row, first one value is 1. That is a given fact, right? Now for the second value, or the value located at index number 1, how can we calculate that? We can simply calculate that, okay, this is index number 1, right? So this index number 1 has to be connected with the previous value of index 0 and index 1. Then that you can see over here, that this was connected with like index value 0 and this was in an index number 1, and that is how this is connected. So all we will have to do is just do the sum of them, and that we can clearly found from the answer we have already stored over here, so which is 2, and again the next value we will get is 1. Now we need to create the fourth row. Okay, so for the fourth row, I'm not going to show you in the triangle, I'm just going to show you in the answer that how we will be able to generate that. So first value is 1, that is a given fact. We are trying to find 4 elements in this case. Now for the second element is located currently at like first index position, right? So because the index position is first, which means we will have to do sum of 0 and first index position, which is these 2 values. So in this case, the answer is going to be 3. Again, now for the second element, so this is like the third element inside this fourth row, and the second element in terms of like index value. So okay, the index value for this one that we are trying to find is 2, which means we will have to do sum of 1 plus 2. So okay, what is the value located at index number 1 in the previous value, which is this one, 2. Okay, and what is the value located at index number 2 in the previous value, which is 1. So 2 plus 1. So we get the answer as 3. And since we are only trying to populate 4 values, the fourth value has to be 1, because that is we already established that. So this is basically the simplest logic that we are going to use in order to populate our answer using dynamic programming. If you still don't understand the concept, I suggest you try to draw like any single Pascal's triangle. It's pretty easy to draw, and then you would be able to calculate the values. And basically, using the dynamic programming, this problem can be solved really easily. If we see time and space complexity, in this case, the time complexity is actually going to be big O of n square, where n is the number of rows that are given, and that is the best we can do. First of all, we are going to create a list of lists to store our answer. Now, we are going to create our base case. So base case is that always the first value is going to be the 0, like the 1. And so what we are going to do is we are going to add a new entry over here. Now we have created our base case, right? Now as an input, we are given the number of rows we need to perform. So what we are going to do is we are going to run a for loop, and inside this for loop, we are going to run up until the we are going to start from row position number 1, and we are going to go up until the point where we reach to the number of rows that we need to reach to. Now for every single row, we will have to create a new array list that we need to input. Also at the same time, for any single list, we will actually have to require the previous list that we have calculated, right? So we are also going to create a new list to store the previous list, and we are going to name it as previous list. Now we have our value set up. Now first of all, for the new row that we are trying to add the entries, we are actually going to assign the value 1 into it. And now we are also going to run another loop. For this another loop, okay, let's just name the parameter integer j, and we are going to start it from position number 1. Why we are starting it from position number 1? Because we already filled out one value over here, and this is going to run until we reach to the value of this row that we are trying to reach. And now the core logic is actually quite simple. All we are going to do is for this current row, we are actually going to add the value, and we are going to add the value based on the result of the previous list that we got. And we are actually going to like get it using the j minus 1 value, and plus we are going to get it like the jth value. And basically this is the whole core of every single thing that we are trying to achieve. Now once we get out of this loop, remember the last value also needs to be 1. So again we are going to do that. In the end, all we need to do is just add this new row, that new list that we have created in our answer. So let's do that. And in the end, once we get out of the loop, basically our answer should have been populated, so we can simply return the answer. Now let's try to run this code. Seems like our solution is working as expected. Let's try to submit this code. And our code runs pretty efficiently, and it beats almost like 82% of the cases. Also in terms of memory consumption, it beats a lot of cases. Now I forgot to mention the space complexity for this one. The space complexity is actually going to be constant space. Why? Because anyways we are creating like a new answer list to store the answer, and we are only creating like couple of temporary lists over here. We are not doing anything extra, so that's why the space complexity is going to be constant space. And again, as always, I will be posting this solution in the comments, so you can check it out from there. Thank you.
Hello friends, we are still not employed by a FANG company, so let's not stop lead coding till we get there. Today we are going to do a very important lead code medium problem, word break. Let's understand the problem statement. So basically we are given a string s, and we are also given a dictionary of string word dict, and we need to return true if s can be segmented by all the words that are given inside the word dict. So if we look at the example, suppose our s is lead code, and the word dict we are given is first set is lead and second set is code. We can clearly see that this lead code we can generate from whatever the values we are given in this dictionary, so we will return true in this case. And we are also mentioned that we can use the same word multiple times. So suppose if this problem was lead code something like this, we would still return true, because or whatever words are, we can still make it through this dictionary. But if we were given some wording like this, that lead code LEE, so up until this point we have the words that we can make from this dictionary. The thing is, this LEE, there is not a specific word given for that. The word we are given in the word dictionary is leet, so it does not match. So in that scenario we would return false, otherwise we would return true. Okay, let's try to understand that what would be the brute force approach. Suppose we are given S is equal to ESPN, and the dictionary we are given is E, S, P and N. So we can clearly see that all the words are present in the word dictionary, so the answer should be true. And in the brute force solution we are going to use a bottom up approach. So and in this video I'm going to show bottom up approach all the way, even for the optimal solution. So this can also be solved as a top down approach, so let me know if you want to make a separate video on that. And there is also one more thing to consider. Suppose we are given something like S is equal to null value or empty string, and in the word dictionary we are given some elements like a b blah blah blah. So this case we can clearly return as true. Why? Because this empty element will always be there, though it might not be showing. But the thing is, if there are no elements in our given string, we can always return true, because the emptiness is also exists in this word dictionary. So we are going to use this logic, and let's see that how we can build our brute force. So we are doing bottom up, so we are starting from the lowest value and eventually we are going to make the whole world. So the first value we need to, so we are at the 0th position. The first value we need to make is simply the word break of a value E, and the word break of value E is very easy to calculate. We only need to check that whether the word break of empty string and the value E exist in this given word dictionary or not. So basically, and we know that if there is an empty string scenario, this will always be true, because I just explained it to you how. So we only need to see that whether this E exists in this word dictionary or not. If this exists, we can clearly say that this is true, and we can denote the value of word break of E as true. Now the second decision we can make over here would be to see the word break of two elements, so E and S. And how can we determine the word break of E and S? Well, again, it's simple. So we need to we have two ways to determine that. Either we can do a word break of empty string, and we can check that whether this ES value is present in this word dictionary or not, or we can do a word break of value E, because we know that this is always true. The word break of empty is always true, so we can do a word break of E, and we can check that whether the value S is present in this given word dictionary or not. And word break of E, we already know how to do it. For this word break of E, we need to do word break of empty, and we need to calculate the value of to see that whether this E is present or not. The third option over here we can have is, and you guessed it correctly, the word break of three elements, so ESP. And for this three elements we again have three more possibilities, so word break of empty string, and we need to check that whether ESP, all these three exist in this scenario, or we need to check that whether the word break of this E and SP exist, and the word break of ES and P exist. And yeah, so these are the three ways we can determine that whether the word break of ESP exists. The next option we have is the final scenario, that whether the word break of ESPN exists or not. And to check that, we will have four possibilities. So first one is that we check the empty string, and we check whether the ESPN, the whole word, is present in this word dictionary or not. Or we can check that whether the word break of E is present and SPN, these three values are present or not. Or we can check that word break of ES is present, and we can check for PN, or we can check word break of ESP, and we can check the value n. So these would be the 4 cases where we need to calculate all of these, and for every single one of them. So even in order to calculate this word break of E, we will use this method. To calculate this word break of ES, we will calculate this whole method, and yeah, so this would be the brute force solution. Eventually we would find that whether we are able to make this ESPN or not, and whatever a result we get, we just need to bring it upwards and we would be able to find the solution. So this solution works, but it works in a very horrible way, because at every single location we have two possibilities to make: whether we want to keep that element or not, and our decision tree keeps on growing and growing and growing, and though we will come to the correct solution, but it's gonna take us a lot of iterations to achieve that, because over here you can see that we only had these 4 elements that we need to consider. We generated such a big tree, and over here most of the values we did not even completed the whole sub iteration for them, because I would be running out of space. So the time complexity, as you have guessed correctly, for this approach is actually big O of 2 to the power n, because at every single location we are making 2 decisions, which is pretty bad. And why it is 2 to the power n? Because we are calculating everything at the same time. So see that, do we have a room where we can save whatever we have calculated before, and can we use it further down the road? Of course we can, because notice over here this W word break of E, we are using it over here, but we have already calculated its value. So why do we need to calculate its value again over here? Same goes with this word break of ES. We have already calculated the value over here. So why are we repeating this whole process? There are a lot of repeated effort. This is repeated, this is repeated, this is repeated. We have already calculated all these values. So somehow if we just create a cache, we store that whatever the values we have calculated so far, and keep track of that cache, and whenever we need to encounter that whatever value we are calculating right now, we can simply check that whether that has already been calculated, and using that we can actually come up to a better solution. Since you guessed it correctly, that because we are using something that we have already calculated in past, we are keeping a track of it in some form, and we are using it further down in our next iterations. So basically we are using the most beautiful thing in the computer programming, the dynamic programming approach. In the dynamic programming, we are going to create a single array of size whatever the given input string is, and based on that particular array we will calculate all the values that have been calculated so far. And because this is a bottom up approach, we are going to start filling up array from the 0th position, and we will reach at the end, and in the end, after all the calculation, we will just simply return whatever the value we have calculated over here. So let's see that what would be the optimal solution. Suppose again we are considering the same example. S is equal to ESPN, and the word we are given is ESP and N. And now let's create a new data structure called DP of an array that is of size 4, and there would be 0 1 2 3 4. Now we know that this 0th position would always be true. And why it would be true? Because this indicates that for DP of size 0, which means that for string of size 0, does the word dictionary contains this particular element or not? This is what this DP is representing, that at every single location, whether the value of that length of the character, is it present in this word dictionary or not. So DP of 0, we know that that's an empty string, and if it is an empty string, we can determine the value as true. So this would become our base case, and this is very important to identify in a dynamic programming problem, that we need to have a base case. And initially we would set up all the other values as false, and we will run our iteration. So let's see that what each of these values are going to represent. And you guessed it correctly, that this value represents a word break of 0, this represents the word break of 1. So in this case it would be the value E. This represents the word break of value ES. This represents the word break of value ESP, and this one represents the whole word, so word break of the value ESPN. And yeah, so at the end, whatever result we find over here, if we just return that, that would be our perfect solution. So example we are going to take is the same one that we have been discussing. So the S is ESPN and the value of word is E, SP and N. And we know that our dynamic programming of value 0, this is our base case, that is true. So what we are going to do is we are going to iterate over, starting from single element, we are going to keep on increasing the size of our element. Depending on the size of our element, we are going to fill up this DP array, and at the end we will just return the value. So initially we will calculate just for value E. So DP of 1 would be calculating the word break for value E. So let's see that whether this value E is present in this word dictionary or not. So the value is present, so we can say that the DP of 1 is true. Okay, this is good. Now let's check for the second element. So for DP of E2, this would be calculating the word break for ES. Now we know that we can break down this word break for ES in two parts. Either we can do like an empty string and we can check for this value ES, or we can do the word break for the value E and we can check for the value S in this given word dictionary. If we go for this one ES is not present over here, so we are left with the second approach. In the second approach, we know that word break of E, which means this DP of 1. So DP of 1 is already true. So we can say that, okay, this is true. Now we only need to check that whether this S is present or not. So S directly is not present in this word dictionary, which means that this condition is not satisfied, this condition is not satisfied. So we can say that the value for DP of 2 is actually false. So we will just mention it over here that this is false. Okay, let's try to calculate the DP of 3. So DP of 3 means word break of elements ESP. Word break of ESP means three things. First one is that we can directly calculate to see that if ESP is present or not. This is not present, so this condition won't work. Second one is we can check that whether the word break of E is present and the word SP is present or not. And third we can check is whether that word break of ES is true and the P is present. Now the thing is, we already know that this condition is not true, the ESP is not present, which means we need to check these two conditions. Now let's check this bottom condition first. So word break of ES, this word break of ES is actually in the dynamic programming array, it's the second position. So DP of 2, we need, so DP of 2 and the value P. Now we know that DP of 2 is already false, which means that this condition will also be false. So we don't even need to calculate, and we don't even need to check for this element P in the word dictionary, because we know that since this DP of 2 is false, we can just ignore this case and let's focus on this one. So word break of E, which means that DP of 1, so DP of 1 is true. If DP of 1 is true, which means that at least this condition is true. Now we need to check that whether SP exists in the word dictionary or not, and SP also exists in the word dictionary, which means that DP of 3 we can consider this as true. Let me also put this one on this side. Now let's calculate the DP of 4, which means word break of ESPN. So again, this will have 4 conditions. Now I'm going to write this in a different manner. So we can also say that this is dp of 2 and pn, because dp of 2 represents this es, and we can also say this as dp of 3 and n. And yeah, these are the 4 conditions we need to check, and if any of them are true, we need to return true over here. So let's check the first one. Does espn exist in over here? No, it does not, so this is false. So wb of e is true, so at least one is true, but spn does not exist over here, which means this is also false. Now dp of 2, this is already false, which means we don't even need to calculate and check for this pn. Now the last one is dp of 3. dp of 3 is true, so this is good. Now we need to check whether n exists over here or not. So n exists over here, which means this is true. So we find one case that is true, so which means that over here we can mark this value as true. And remember that this given string, this is of length 4. So because this is of length 4, we simply need to return whatever value we find as dp of 4, and that is true. So in this scenario we'll just return the answer as true, and that would be our solution. This is a very good solution, because notice that we are already calculating what we need so far. We are keeping track of it at every single position. Because we have calculated these values, we are able to use it effectively and come up to the result. Let's calculate the time complexity. So we are iterating over all the elements at least once, so that is an n. Then we are also creating substrings. So for every value n, there can be n minus 1 substrings, which means that we need to do additional n work. So the time complexity would be big O of n cube. So this is also pretty high time complexity, but if you compare it with 2 to the power of n, this is actually way lesser. Because this time complexity, that can still be calculated, and this is a polynomial time complexity. But the thing is, this one is exponential, and yeah, we need exponential salary but not exponential time complexity. So let's code up the solution. Okay, let's create a boolean array to store our cache, and we'll name it as dp. We'll assign its length to s.length plus 1, and we know the base case where dp of 0 would always be true. Also for this word dictionary, this is a list, so we are going to create a hash set that will store the strings, and we will store this word dictionary over there, so it becomes faster for us to access the word dictionary. We'll just name it word set. Now I think we are all set to start our loop, so we'll create the 2 loops. Notice we are starting our loop from I equal to 1, because we don't need to we already have the value for I equal to 0, and we are going to start the second loop from 0th position, and while j is less than I, because we only need to go up to ith point. Now inside the loop, first of all, we will check that whether the dynamic programming for the jth value exists or not, and this is what I already explained in the solution explanation, that if this is true, then only we check that whether the word set contains the substring. So we'll use a substring method, and we'll provide the parameter as j and I, because j is less than I. And if this is true, basically we just need to assign the value of dp of I as true. And yeah, I think that's it. We don't need to do anything, and at the end of the loop we can simply return the value of our dp of s.length. And Yeah, also when we find this value dp of I is equal to true, which means that we can break out of this inner loop, because there won't be another pair that we need to calculate, because even at any moment if we find a single true, that's sufficient for us. So let's try to run this code. Okay, looks like our solution is working. Let's try to submit this. Yeah, our solution works. It is accepted by LeetCode, but notice that this solution is actually pretty slow. It is taking a lot of time, and it is not as fast as our other solutions. So there is one trick we can do is, rather than going from from j equal to 0 to I, we can actually go in reverse. So we can start the position of j equal to I minus 1, and we can see that whether j is greater than or equal to 0, and we will do j minus minus. That way we would be able to find this a little bit faster. So let's try to run the code first. Yeah, this works. Let's try to submit it and see the significant difference. Now our solution is much faster, and even if you see over here, previously this one was running in 13 milliseconds and this one is now runs in 4 milliseconds. Basically we are just eliminating and breaking out of this inner loop faster. We are not doing anything special. So yeah, this is just something to keep in mind. And yeah, I hope you liked it, and I will be posting this code in the comments. These are the top companies that have asked this problem recently. And if we see from past 6 months to a year, it's eBay, Google, Goldman Sachs, and these companies. And pretty recently, Amazon has asked this question 20 times in its interviews. Facebook has asked this question 18 times in its interviews. So I highly suggest you to take a look at this problem, understand it completely, and then practice it as much as you can. This is a medium problem, and we are given a distinct integer called candidates, and we are also given a target integer, and we need to return all the unique combinations of candidates where we can reach up to the target value. Now this is a little bit tricky part to find all the unique combinations for this target candidate, because let's try to understand this with an example. So over here we are given the candidates as 2, 3, 6 and 7, and we need to reach the value number 7. So we can clearly see that 7 is already present over here, so we can return this one. The thing is, we need to return all the unique combinations. So one unique combination is 7, second unique combination, and also one more thing, we can use the same number from the candidate unlimited times. So if we apply this theory, then we can find another value that can reach to the sum of 7, then that would be 2 plus 2 plus 3. If we do that, this also sums up to 7. So we need to return a list where the two values are 2, 2 and 3, and the second element is just 7. And this would be our solution for this given problem. Okay, let's try to understand this problem with a custom example. And it is really important to create your own custom examples, because it shows that you have the ability to think outside of the box, and you can create test cases on your own. It is a really important skill to have for any engineer, and especially FANG engineers. So we are given 3 candidates, 2, 5 and 6, and we need to see that what are all the combinations we can get out of these candidates to achieve the target value 8. Now just by looking at it, we know that the two combinations we can create is 2, 2, 2, 2. This is one combination, and the second combination we can create is 2, 6, and this would be our answer. The thing is, let's see that what would be the most basic solution we can come up with, and what would be the intuition behind it. And based on that, we would be able to create an algorithm that would solve this problem. So initially we are at this position 0. Now at this position 0, we have 3 possibilities from which direction we can go. We can either go to this value number 2, we can go to the value number 5, or we can go to the value number 6, because these are the 3 candidates that we are given. And also we should not forget that the target value we want to achieve is 8. Okay, so keeping this in mind, we need to go and pick a side where we need to go further, and keep going. So again, let's just go on one direction for all the cases we can. So over here we are at 2. Now remember that we can use same element infinite times, which means that there can be one possibility as 2 2. Of course there can also be one possibility as 2 2 2. Of course the thing is, uh, notice that we need to put a constraint for the number of decisions we are making, and the constraint is that if at any point the direction where we are fetching all the candidates, if the sum of those can either be less than target, they can either be equal to target, or they can be greater than target. These are the three possibilities we can have. If it is less than target, which means that there is still room for us to find the potential combination, which means we can keep further going on that direction. If we are already at value number 8 or whatever target we can directly put this value in the result. But if we and which means that we have found the combination, so there is no point in going further after we have already found the combination, because all the elements, they are only going to add up to whatever combination we have, which means that we won't be able to find another combination with the same numbers that were used to achieve this equal to. And the third option is that the value could be greater than 8. If it is greater than 8, why are we keep on going or to do more iterations and putting more strain in our computer? There is no point in doing it, because we could have infinite options, and if we do it, this would be like the most was this would be like the best way to deplete the resources of our company. So we don't want to do that. So now, since we have kept these things in our mind, now let's see that how can we use them over here. So far the sum we have found up until this point is only 2. But the thing is, over here we have 2 candidates, and the sum we have found so far is 4, which is still less than 8. This is 6, again still less than 8. Now over here we can have one more possibility as 2 2 2 and 2. And if we do the sum of this is 8, which means that this is actually equal to whatever the target value we had. So we can add this to our result combination. We would have that we have already find one value in our result, and we will just add it as 2 2 2 2. This is one combination that we have found so far. The thing is, we are not done yet, because we still have other candidates that we need to look at, and we need to check the possibilities. But the thing is, we have concluded at least one thing so far, and that thing is we can't go further down on this path, because all the values would be greater than 8, and which is not what we want. So the only way we can go is actually we can go back and see that have we missed out on any combination. So over here, the next possibility we can get is we have already used 2 as our candidate for this value 2 2 2. So the next possibility we can have over here is it could be 2 2 2 and 5, or it can be 2 2 2 and 6. So let's do sum of all the combinations. So some of these combinations would be 11, and some of these combinations would be 12. Notice that both are actually greater than the value of our target, which means that we can't go further down at any of these positions, and we have exhausted all the possibilities up until this point. So since we have already exhausted the possibilities up until this point, the only way we can go is we can go back. At this position 2, we have exhausted all the possibilities there can have. One, we found the answer, and the other two we found that it cannot be part of the combination, which means that we have already exhausted all the possibilities for this value 2 to 2 as well, which means that we can't go down, but we can go up. So over here, have we exhausted all the possibilities so far? No, there are still room, there are still other possibilities that we can check. So let's do that. So one possibility we can have over here is 2 2 2, which we already checked. The next possibility could be 2 2 5, and the next possibility would be 2 2 6. So sum of these values is actually 9, and sum of these values is actually 10. Again, both are greater than whatever the target value we had, which means that we cannot go down. So we will go back. We went back. over here we check that we went through all the possibilities, which means that we are done over here. So we can't go down any further on this path, but we can go up. So if we go up, we ask ourselves a question that have we explored all the possibilities at this position? No. The possibilities we could have is 2 5 2 6. So let's take this value first. So at 2 5, the current sum we have is 7. 7 is less than whatever value we have as our target, which means that we still have possibilities. The possibilities we can have is 2 5 5 or 2 5 6. Notice that over here we only had two possibilities where we can calculate it from. We did not had the possibility of 2 2 5. Why? Because we already calculated it for this portion over here. Remember, in the previous iteration we already calculated for this scenario, which also shows one very important property, and their property is that out of our candidates, whatever the candidates we are given, if we are at any particular position or any combination of positions, so whatever value we have as last, we can only use that multiple times, or we can use the values that come after it. We cannot go backwards because we have already exhausted those possibilities in an iteration before this, as I showed you earlier, that this we have already explored over here. And this 2 to the 5 2 5 we are exploring at this position 2, which means that the only combinations we can make up after this point is either 2 5 5 5 something blah blah blah, or 2 5 6 6 6 something like this. But we can't make like 2 2 2 5 because we already checked that over here. So, and this is a very important property that we are going to use. Okay, at this point the sum we can have is 12, which is greater than 8. So we can terminate over here, we can't go down any further. And over here the sum would be 13. Again we can terminate over here, we can't go down, which means we have to go back. So we come back at 2 5. We say that okay, we have explored all the possibilities over here. We go back to value number 2. Now the thing is, at value number 2, have we explored all the possibilities? No, there is still one possibility pending, which is 2 6. So at 2 6, this value, the sum would be 8. Again, this is really critical because we have found a pair that equals to whatever target value we had, which means that we will add this combination to our result list. So over here we will add another entry 2 6, and after adding this, we have explored all the possibilities after this point, which means that we would go back. Now at this position 2, we have explored all the possibilities it could have, and because we have explored it, we will again go back to our 0th position. The thing is, we are still at 0th position, so can we stop now? No, we can't stop because we still have a whole lot of possibilities that we haven't touched so far. Because remember, over here we still have this 5 and 6 pending. So let's see that what could be the possibilities over here. Now at 5, again we can only have two possibilities. As explained earlier, we could have either 5 5 or we could have 5 6. So let's do the sum of these values. So 5 5, the sum is actually 10, and 5 6, the sum is 11. Both are greater than 8, which means that we can terminate over here. So that concludes that at this position 5 we ran out of the possibilities. We went up, at this position we are done. So again we go back at 0th position. We check that do we have any other options where we can explore, and yes, currently we are at value number 6. So 6 is again less than our target 8, so we can go further from 6. The thing is, at 6 we can only do 6 6. We can't do any other combination because those we have already checked so far, which means that 6 6, the value is 12. So 12 is already greater than 8, which means that we can't go further from this, which means we can't go further. We go back. At 6 we see that have we explored all the possibilities? Yes, we have explored all the possibilities, which means again we go back to this position 0. So at this position 0 we check that now have we explored all the possibilities. Yes, initially we check all the possibilities for the value 2, again we check for value 5, and again we check for value number 6, which means that even at 0th position we are done. So our base case has satisfied. Now whatever we have stored in our result result list so far, we can simply return this, and this would be our final solution. And this is actually the optimal solution that we can achieve. Notice over here that we were doing lot of repetitive work. At any position we were calculating the different possibilities we can have. We were picking a possibility, we were exploring in that direction, depth first search. We kept on exploring. Once we found a terminating case, once we found a terminating case, we would go back to a point where we can still explore for more possibilities. Over here again we would further go down to additional possibilities. We would find a terminating case, again we would come back, and eventually we would come back to the 0th position from where we started, and after the calculation we will return our result. So this, where at any point we are coming back from where we originally started. This is actually called backtracking. This is a really important concept in computer programming, and I just showed you that how can we use it. And that is why, because this concept is really important, it has a lot of very practical applications. And that's why you see that why all those big companies like Google, Facebook, Amazon, Goldman Sachs, they were interested in asking this question to their candidates, because they want to know that are you familiarized with very important things that are really critical, and can you go down that path. And yeah, so since we have found our optimal solution, I did not mention explicitly that I was showing you the optimal solution, but the thing is, I told you that this is the intuition behind it. And once we knew the intuition, we just need to find a way to implement it in computer programming. The way to implement this, you must have guessed it correctly, that we were doing so much repetitive work again and again, and we were using it somewhere, and we had some terminating conditions that either if the value is equal to or greater than our target, we would terminate, which means that we were using recursion at its best over here. So yeah, this is basically our solution. So let's calculate the time and space complexity. That time complexity for this one would be big O of n to the power t. Now first let's determine that what this n and t means. N is actually the number of candidates and the least value for this one, and t is actually the total amount. Because imagine that what could be the longest sequence we can have at any given position. Well, suppose our target value is 8 and our candidate is 1, which means that we would do 1 plus 1 plus 1 up until 8 times till we get the value 8, which means that we need to go in one direction 8 times. And at any position we can have multiple options, or we can make multiple decisions, and from further down we can go ahead, which means that we need to do this work n to the power t times until we find the solution. So that's why this is the time complexity. So first of all, we'll create our result list, and now we'll create a list to store the current combination. Okay, now we'll create a backtrack method, and in this would be our recursive method. So initially we are going to provide the target result combination 0 as the starting point, and the candidates array. And after whatever the result we get back from that recursive call, we simply need to return whatever we find in this result list. So let's create the recursion method, Okay, so first of all we are going to create the terminating cases. So if target is equal to 0, which means that we have find a combination that sums up to the target value. So we can just simply return it to we can simply add the combination to our result. If this is not the case, we need to return, we need to check that whether the target is less than 0, which means that we have already surpassed our target and we need to break. So we can just return null. If both cases are not true, which means we still need to look for our combination. So we'll start by checking in our combination from the position start, and we'll go until we still have candidates. Now inside the loop, first of all, we will add whatever candidate we are currently looking for in our combination list. Okay, after that we can do our recursive call. And as a target, we will have target minus whatever candidate value we found. And start would be ith position. And I think that would be it. Yeah, one more thing, we will have to remove the entry from our combination list, because we will be doing backtracking when we move towards the next value. And I think this would be it. Let's try to run the code. This should have worked, but I don't know why it's not working. So we'll just enter the value manually. Oh, it should be candidates. Okay, our solution seems to be working. Let's try to submit the code. And yeah, our solution works perfectly fine. And I will be posting this code in the comments. You can check it out from there. Hello friends, we are still not employed by a FANG company, so let's not stop lead coding till we get there. The problem we are going to do today is actually asked in a lot of top tier IT companies, and if we look at the recent data, it has been asked in Amazon 20 times, Apple 8 times, Facebook 2 times, Google 6 times. So needless to say that this is a really important problem. So I hope you provide your utmost attention. This is the outline on how we are going to solve this and the things I'm going to cover in this video. So first we'll understand the problem statement. I will be creating a brute force solution. Then we will build an optimal solution with dynamic programming. And at the end, I'm going to show the Java code for this one. This is a lead code medium problem, but in my opinion, it should be a lead code easy problem because it's not very difficult to understand. But the thing is, its concept is really important. That helps you build the conceptual knowledge of dynamic programming, which you can use in bunch of different problems. And a lot of FANG companies loves to ask this kind of questions. So if we understand the problem statement, basically we are a professional robber and we are planning to rob houses in each street. Now the thing is, the way houses are mentioned in the street is that every single house has some amount in that particular house. But the only condition we have is if we rob one house, we cannot rob the house that is exactly adjacent to it. So suppose we decide to rob this house. If we rob this house, which means that we cannot rob this house or this house. And we can again, if we want, we can again drop this one. So that option we have, and our aim is to maximize our profit. So basically we are given an input array nums that shows that for every single house how much amount of money is presented over there, and we need to see that what route can we take which maximizes our input or the amount of money we can steal, and we need to show that in the output. So let's try to understand this with an example. So basically over here we are given the values as 1, 2, 3 and 1. So notice that the maximum amount we can steal is basically if we go down this path. So if we start with the first house, and then notice, then we can't rob the second house, but then we rob the third house, and the sum of these two would actually become 4, and this would be our answer. So for the brute force, we are going to solve the same problem. Basically, one way to understand the brute force approach is that at every single position, initially we are at 0th location. So if we just make all the possible pairs which we can create where we can rob houses, basically that would be our solution. So let me show you how. So initially at 0th position, now we have two options. Either we can select the value number 1 or 2. So either we can select the first value or second value, and these are the subsequent values. Now at this position 1, we again have two options. Either we can rob the third house from here, or we can skip the third house and we can also rob the fourth house if we want. So the two choices we have over here is either we go down this path or we go down this path. And at this house number 2, we only have one option. We can't rob this 1 or we can't rob this 3, so we can only rob this 1. So the only choice over here we have is actually 1. And now we just do the sum of all the values. So for this path, the sum we would get is 4. For this particular path, the sum we would get is 2. I just put it in a box so it's easier to differentiate. And down this path, the maximum sum we can achieve is 3. So if we compare these three elements, we can clearly see that 4 is maximum, so we simply return 4. Now brute force solution works, but the problem with this one is that we need to create every single pair, and in order to generate pair, essentially at every single position we have two options, that whether we need to keep this value or we do not need to keep that value, and that eventually would bring a lot of different values in our graph, and on the number of decisions we can make, which means that the time complexity for brute force approach would be, you guessed it correctly, 2 to the power of n, where n is basically whatever the number of inputs given over here. And you guessed it correctly. Also, I already gave it away, but we are going to use dynamic programming over here, and let me show you how we can use dynamic programming to solve this problem. We are going to use a custom example, and I have already mentioned it a bunch of times that it is really important to have your own custom examples. That shows that you can think outside of the box. So over here initially, we are at this position, value number 2. Okay, so what we can determine is that initially at this position, if we were given only one house, what is the maximum amount of value we can steal from this particular house? Of course, the answer is pretty simple. We can only steal whatever we are given, right? Because we are only given just one house. So initially at this point, suppose if we create an additional data structure that keeps the track of what is the maximum amount of money we can steal up for any element, then our decision making will become easier, and we would be able to choose that what path we want to take. So let me show you by an example. So initially at this position, value number 2, the maximum amount we can rob will only going to be 2, because there are no other values before that. So this is the maximum amount we can rob so far. Okay, now this at value number 4, the maximum amount we can rob is actually, up until this point, it's only 4, because we can't use 2 when we are robbing 4. When we, if we choose to rob this second house, if we choose to rob this one, we can't use it. We can't basically use this first house. So we know that for the first two values, these are the maximum amounts we can rob. Now we are at this position number 3. So at this position number 3, we have two options. Choices are pretty simple. Either whatever the value maximum we have so far over here, which means that so far the maximum value we have is 4, or whatever the previous maximum value we had plus whatever value we currently are at. Because remember, if we decide to rob this house number 3, basically we still have the option to rob house number 2. We can't rob house number 4. So up until this value number 5, the maximum we can rob so far is actually 5. Why? Because we check that, okay, up until this point, what is the maximum that previous element has robbed? Basically, like one house before this house has robbed, and that maximum value is 2. So I can do 2 plus 3. So maximum I can rob up until this point is actually 5. So okay, we have this knowledge, and up until this value, the maximum we can rob is 4. Now let's forget about this one for now, because anyways at any given time we are only concerned with the house that are adjacent to each other. Now we are at this position number 9. So what is the maximum value we can rob up until this point 9? Well, the answer is quite simple. We check that, okay, what are the two values before this 9? So this is 5, which means that if we decide not to rob this house, the maximum we have robbed so far in this sub array is actually 5. But how do we decide that whether we want to keep this 9 or not? Well, we just need to apply the same logic. The house that is adjacent to 9, before that, what is the maximum amount we have found? So the maximum for that is 4, and we do 4 plus 9. So 4 plus 9 is 13, which means that up until this point, the maximum we can get, the amount is 13, which is definitely greater than 5. So it is in our interest to keep this pair so far. Now we can forget about this 4 because we already calculated its value over here. And now at this next value, value number 11, again we have two choices. Do we want to keep 11 or not? So again we do the same thing. We compare 11 with whatever value we have over here. We do, first of all, we do sum of 11 plus this 5. So we do 11 plus 5. Okay, this one is 16. So which is greater than 13, which means it is in our interest to keep the value 11. So again, we are going to have 16 over here. We can forget about this one because we already calculated its value. And yeah, so we are at, now the two choices we have is 16 and 13, and this value number 2, we need to check two items. So value before that, this is 16, and this one is 13. So we do 13 plus 2, 15. So far, if we decide to keep this value number 2 in our list of houses that we are planning to rob, the maximum value we can achieve so far is 15. But the thing is, we have already found a better option than this 15, and which is 16, where if we decide to rob these 3 houses, we will get the optimal answer. And notice that we were able to complete this whole iteration in just single we were able to complete this whole calculation in just a single loop, because we were keeping track of whatever the elements we have calculated so far, which is the exact use of dynamic programming. And we are not using more than one element at any given moment, which means that our solution is actually quite helpful and very perfect. So let's calculate the time and space complexity, and basically this would be the optimal solution. So time complexity, as you have guessed it correctly, it's actually big O of n, because we are completing everything in just one single iteration. We don't need to do multiple rounds of checks. And the space complexity we have is actually big O of 1. It's actually constant time, because notice that at any given moment the maximum value we were keeping track of is just couple of elements, and we kept on updating our elements, that whatever we are keeping track of, which means that we are not using that much space. We are not creating an additional array to store all the values. Okay, let's create two elements. We'll name it rob1 and initialize it to 0, and we'll create a rob2. We'll also initialize it to 0, and we'll have another variable. We'll just name it max to keep track of maximum element that we have calculated so far. And now let's run a for loop. Inside the loop, first of all, we'll calculate that whether we have achieved the maximum value or not. So max would be whatever value we have at rob1 plus whatever value we are currently at. So this is one option, or whatever the value of rob2 we have, because notice that the rob2 element is actually right adjacent to this ith element. And now we need to update the values of rob1 and rob2. So rob1 will actually become whatever value of rob2 we had, because we are updating it every single iteration, and rob2 will actually become the maximum value we have found so far. And yeah, I think this should be our solution, and at the end we will return the max element. So let's try to run this code. Okay, our solution seems to be working. Let's try to submit it. Oh, okay, yeah, our solution is actually runs in 0 millisecond, and it's 100 times faster than all the other solutions. But the thing is, this is not true, because we are given a limited number of test cases. We are computing everything in just constant time, so that's why it's showing us 100% faster. So I'm not gonna claim that my code is greater than everyone else's. We have really smart people in LeetCode community who writes way better code than me. So hope you like the video. Hello friends, we are still not employed by a FANG company, so let's not stop lead coding till we get there. Today we are going to do a very important problem, House Robber 2, and this is actually an extension of original House Robber problem. I have already solved the House Robber problem over here, so you can check out that video, and I highly recommend that you check out that video before coming on to this problem. Typically, in any interview, this problem is actually going to be asked as a follow-up question after they have originally asked this house robber problem. And that is why if we see the number of companies that have asked this question recently, it's actually quite small compared to what we are used to seeing for the other companies. But the thing is, still Amazon and Google have asked this recently. Even Microsoft asked this just a little bit sometimes back, and also a few other companies have asked this. So this is a LeetCode medium problem, and basically the problem statement is saying that we are professional robber and we are planning to rob houses along a street. Now the catch over here is that all the houses in this given street are actually arranged in a circular fashion, and also there is one more constraint, that we cannot rob two houses that are adjacent to each other. If we rob two houses that are adjacent to each other, basically police is going to be called and we will be caught. So this is a constraint that we have to look into, and our motive is to collect or gain or rob as much money as possible without being caught. So let's try to see a pictorial representation. So basically all the houses in the street are actually placed like this. So suppose if we consider that this is our first house, actually the first house is also neighbor of the last house in the given street, because all the houses are stored in a circular fashion. And now since the houses are stored in a circular fashion, that is one more thing that we need to consider. And also we cannot rob two adjacent houses. So suppose if we decide to rob this house, we cannot rob this house or we cannot rob this house. So the first example we are given is the houses are placed like this, and these are the amount of money that is at each house. So basically, since there are only three houses, we can only rob one house, and we need to select the house with maximum money. So it's pretty simple over here that if we select this house, we get the maximum money, and if we rob the house with value number 3, we can't rob these two houses because they are adjacent to each other. In the second example, the houses are stored like this: 1, 2, 3, and 1. And the most amount we can collect over here would be if we rob this house and this house. So in that case, the amount of money we would collect would be 4, and we won't be able to rob these two houses because they would be adjacent to each other. So we already know the brute force approach. Basically, the brute force approach is to make every single pair and check out all the possibilities to see how we can find the answer. But the thing is, there is no point in exploring brute force approach over here. I'll directly go to the most optimal solution that we are going to achieve using dynamic programming, because this is an extension of house robber 1. If you want to get more information about the approach, you can check out that video first. So for the optimal solution, we are going to use a custom example, and this is very important to use custom examples because it shows that you can create test cases on your own, and this is a really good skill to have in actual computer world. So suppose the number of houses we are given over here are in this fashion, and let's try to draw them in a circular manner. Now basically we can use the same solution we were using in house robber 1, because remember in house robber 1 what we were doing, we were just simply going through whatever the input we had, and we were just keeping track of what is at any location, what is the maximum amount of money we can rob up until this element by checking the previous values. We are essentially going to do the same thing over here, but just in a little bit different manner, because in the house robber 1 problem we were considering the whole thing because they were all the houses were placed in a straight line, so we were able to consider them like that. The thing is, over here the additional constraint is that whatever the last amount or the last house is actually neighbor of the first house, which we can see over here that these two houses are neighbors of each other, which means that if we at any point decide to rob this house, we cannot rob this house, or vice versa, that if we decide to rob this house, first house, we need to make sure that we do not rob this house. So the answer is actually quite simple. Rather than treating this as a circular street, why don't we just run two functions? So basically during the first loop, during the first iteration, we are going to check the first sub problem, and let me show you what I mean. The additional constraint we have over here is that if we consider this house, it is guaranteed that we cannot use the last house, or if we use the last house, it is guaranteed that we cannot use the first house. So since we know that this condition exists, we are simply going to do calculation twice. In the first calculation, we are going to check between these houses that what is the maximum amount we can rob, and during the second loop we are going to check that amongst these houses what is the maximum amount we can rob, and then we just need to compare that what is the maximum value we have found across both the loops, and whatever the maximum value we find, we just we just submit it as our answer. So let's iterate over the entire problem. Okay, so these are the two loops that we are going to iterate over. So let's calculate the result for the first loop. So at the first position, the maximum amount we can rob so far is only going to be 1. And at the second house, the maximum amount we can rob is only going to be 2, because we cannot rob the first house. Now for the third house, we have two options. either we keep whatever the value of 2 we have, or we keep the value of 1 plus the third house value, and we see that whatever is the maximum value amongst these two, we are going to keep that. So 1 plus 15 is going to be 16, and of course 16 is greater than 2, so we are going to say that up until this house number 3, the maximum amount we can rob is 16. Now we are at the fourth position. Now over here, the maximum amount we can rob is actually two. We have two options: either we can rob on 16 units, or we can do 2 plus whatever value at house number 4 we have. So 2 plus 11 is actually 13, which is less than 16. So even up until this point, the maximum amount we can rob is still going to remain 16 and not 13, because definitely 16 is greater value, so it is in our interest to keep this value 16. Now again we are at this position 3, and also notice that at any given location we are only considered with values that are of previous two houses that we have calculated over here. We don't need to consider all the values because we are already adding them up and we are only keeping the maximum values. So this works in our favor. So at value number 3, the maximum we can achieve is either 16 plus 3 or 16 by itself, which is this 16 or 16 plus 3. So of course 16 plus 3 is going to be greater, so we are going to store 19, and we don't care about these values anymore because we already have the latest values so far. Now at value number 6, the maximum we can find is going to be 16 plus 6 or 19. We need to select whatever is greater. So 16 plus 6 is 22. This is the greater value, so we are going to keep this and we don't care about 19. So we can see that at the end of this first loop, the maximum value we have found so far for this particular set of houses is 22. Now let's repeat the same process for the second loop. So in the second loop, for the first position, the maximum we can rob so far is 2. At the second house, the maximum we can rob is 15. Now over here, the maximum we can rob is either 2 plus 11, which is 13, or 15. So of course 15 is greater, so we are going to keep 15 over here. Now at this position number 3, we can either do 15 plus 3 or compare it with 15. So 15 plus 3 is 18, so we are going to keep 18 over here. Now at this position, we consider these two values. So either we do 15 plus 6, which is 21, or we check with 18. So 21 is greater, so of course we are going to keep this one. And now at this last position, we check that whether 21 or 18 plus 10. So of course 18 plus 10 is 28, so we are going to keep that, and we do not consider about 18. So after this entire loop, the maximum value we have found so far is 28, and the maximum value we had found over here was 22. So our job is pretty simple. We just need to see that whichever value is actually greater, we simply return that. And in this case 28 is greater than 22, so 28 would be our answer, and we just return that value. This is a very good solution. We are building it on top of whatever we have solved for house robber 1, and because we are basically using the same solution, we are just changing the scope of up until what points we are using this solution. So just keep that in mind. And if we calculate the time and space complexity, the time complexity for this one is going to be big O of 2n, because we are running two loops, 0 to n minus 1 and n 1 to n. So if we generically mention this, it actually becomes big O of n. And if we calculate the space complexity would be big O of 1, because we are, apart from storing couple of parameters, we are not using any additional space. So that's why we are able to run this in a constant time. Constant space. Okay, let's start creating parameters. So we are going to need two parameters, rob1 and rob2, and we are going to initialize both to 0.
We will also need two parameters to store two maximum values, so we'll name them max1 and max2, and max1 will initialize it to the 0th house, and max2 we can actually initialize it to 0, because we are not going to consider the first house, and we are keeping the max1 as 0 because in case we are given the condition where we only have one input, so we can simply return that. Now let's run a for loop starting from the first house, so I equal to 0 to I is less than length minus 1, I plus plus. Okay, over here we are going to calculate max1, so max1 would be maximum value amongst rob1 plus the current number we are at, or the value of rob2, and we also need to update the value of rob1 and rob2, so rob1 would actually become rob2, and rob2 will become the maximum value we have found so far. Now once we are done with this loop, we need to reset the values of rob1 equal to 0 and rob2 equal to 0, because we are going to use them again in the second loop, and we are going to create another for loop, I equal to 1, and we are going to set up I is less than, so nums dot length I'll plus plus. Okay, and essentially we are going to use the same conditions. By the way, this would be max1. We are going to use the same condition, so we can just reuse the code, and we are going to, rather than calculating max1, we would be calculating max2. So let's do that, and after the second loop, we simply need to return whatever the maximum value we have found amongst max1 and max2. And this should be the solution. Now notice that I am running two loops over here. The thing is, an efficient way to do this is to create a function, and function would intake the parameters like start and end value, and you can just repeat this process. So that would be an efficient way to do this code as well. Let's try to run this. Okay, seems like our solution is working. Let's try to submit the code. Okay, and our solution works in constant time in 0 milliseconds, so that's why it's 100% faster than all the other solutions. I would be posting this solution in the comments, so you can check it out from there, and hope you like the video. If you have any more suggestions, feel free to let me know, and hello friends, we are still not employed by FANG company, so let's not stop lead coding till we get there. Today we are going to do a very important lead code problem, unique paths, and as you can see that this question has been asked in Google, Facebook, Amazon, Apple, Microsoft, Bloomberg, all huge gigantic IT companies. So I highly urge you not to miss this video, and try to understand the problem as thoroughly as possible. This is going to be the framework for the video. We are going to understand the problem. We are also going to find a primitive approach. We are going to find the optimal solution, and we'll write a Java code for the optimal solution. This is a lead code medium problem. We are given that there is a robot in an m cross n grid, and robot is initially located on the top left corner. Now robot tries to go to the bottom right corner, so this is the last place where robot wants to reach, and at any given moment robot can only make one move. It can either go down or it can go right at any point in time. No other ways it can make. So in the problem we are given this m and n, and we need to find that how many distinct unique paths can robot take to reach to the bottom right corner or its final destination. So suppose our given m is equal to 2 and n is equal to 3. If suppose our m is equal to 3 and n is equal to 2, this is one of the test cases. So if we draw it on the board, it would look like this. This is where the robot is initially, so I'll just mark it as R, and this is the destination that robot wants to reach, the bottom right corner. Now we know we need to find that how many unique paths exist. So let's see that how many unique paths can we make, and at any given moment robot can either go on the right side or down. It cannot make any other steps. So let's see that what are the possibilities.
So this is one possibility. So this is one path. I'll just mark it somewhere. Now this is second path. I'll also mark it somewhere. So this is second path. So have we exhausted all possibilities? No, there still exists a third path, and the third path is like this. 1, 2, 1. And apart from these, we cannot make any more paths. So essentially, we are exhausting all the possibilities, and we can return that for this given m and n, the number of unique paths can be 3. Now I hope that this makes problem statement more understandable. Over here, initially we are given an example of m is equal to 3 and n is equal to 7. And the number of unique paths they get is 28. But the thing is, this would be such a long example, so I'm not going over it. Okay, let's understand this with a custom example. So suppose our m is equal to 3 and n is equal to 3. So we would have a grid that looks like this. Over here, this is our robot, this is our destination. Now we are going to calculate that in order to reach to any element, how many unique paths we can take. So suppose if we want to reach to this element, how many unique paths we can take? We can only take one unique path, and that would be to take this right step from here. We cannot take any other step. Same goes for this element, that we can only have one unique path, and that would be to take 2 right steps from here. We cannot reach to this point any other ways. Same happens for these two elements as well, that we can only take one step down or 2 steps down in order to reach to these two elements. The thing is, there cannot be any other unique path if we want to get here. But the thing is, when we get to this middle points, something interesting happens. And the interesting thing is, suppose we want to reach to this point, how many unique paths we can take? Well, we can take 2 unique paths. We can take one unique path to reach over here and then over here, or we can take one unique path to reach over here and then again reach over here. So we can say over here we took 2 unique paths. But the thing is, if we just see that what are the entry points to get to this point, actually there are only 2 entry points to get to this point. One entry point is that if we somehow get to this point, we just take one step downwards, we come over here. Or if we somehow get to this endpoint, if we take one step on the side, we reach over here. Which means that whatever the unique paths we have at these two locations, if we just sum these two up, it will give us the number of unique paths we can take to get to this point. So let me show you by another example. Now again, let's consider this element. So in order to reach to this element, there are only 2 ways we can reach to this element. We can either take one step from here, or we can take one step from here, which means that whatever the number of possibilities we have over here, that once we get to this point, we will be able to come to this unique path. Okay, so that is a given. Same goes over here, that no matter how many number of possibilities we have to come to this point, if once we are at here, we are guaranteed that we can come to this point. So in order to reach to this point, the only possible ways are this one and this one. So if we sum these two, we will find the number of unique ways we can reach to this element, and in this case it would be 3. If we continue down the same path, for this point, we can take 3 distinct paths to reach over here, and in order to reach to this destination D, we can take 3 plus 3 6 unique paths to get to here, and this actually becomes our answer. Okay, so based on our previous explanation, we know these things. So if we see, now we need to see that how can we use dynamic programming to solve this problem. And the reason we are choosing dynamic programming is because at any single location, we are computing that whatever the previous 2 results that we have already calculated, and we are using them to calculate the next values. So that pretty much indicates that we need to use dynamic programming over here. Now let's take a 2 by 2 matrix, and we'll just provide the index values. So index values would be 0 1 2 0 1 2, and we would name this matrix as DP to refer dynamic programming. Now the thing is, if we want to find out the value at this position, we know that it would be sum of these two elements. So mathematically we can write them like this, that DP of 1 1, because this is 1 and this is 1, is actually equal to dp of 0 1 that we have already calculated, which is this value, plus dp of 1 0, which is this value, and sum of these two will give us this value. So generically we can actually write them like this, that at any given location dp of m and n would actually become dp of m minus 1 n plus dp of n and n minus 1, and this would be our recurrence relation for dynamic programming. And I already explained that why are we choosing dynamic programming, and our aim is to find that how many distinct ways we can reach to this destination. So this destination would actually become dp of 2 2 over here, and if we compare it with whatever m and n is given, this actually becomes the value over here. This would become the dp of m minus 1 and n minus 1. So we start our calculation like this, and eventually we would reach to this point, and we just need to return whatever we have found over here, and this would be our solution. So we can just create two loops, one loop iterate over the column, one loop iterates over the rows, and eventually we will reach to this endpoint. We return this becomes our solution, and this is a very efficient dynamic programming solution. Any FANG companies, Facebook, Google, Amazon, whatever, they would be happy to hire you immediately. So now let's see that what would be the time and space complexity. So time complexity would be big O of m times n, because we need to iterate over this entire grid, so that's why it's big O of m times n. And space complexity, remember that we are creating this additional dp array, which is 2 by 2 matrix, and we are giving the size as m and n, so space complexity would also be big O of m times n, and this would be our solution. Now let's move on to coding. Okay, first of all we'll create a two-dimensional array and we'll name it as dp, and we'll provide the length as m and n. Now we'll have to create our base case, so we'll fill our two-dimensional array, and this is the way to fill a two-dimensional array. And over here now we'll create two for loops, and we'll start with I is equal to 1 and j is equal to 1, because we already have cases for 0. While I is less than m, I plus plus, j is equal to 1, j is less than n, okay. Now we will provide our recurrence relation. So dp of I and j at any location is equal to dp of I minus 1 j plus dp of I j minus 1, and yeah, this is pretty much it. This should be working. So now let's return dp of m minus 1 and j n minus 1. Let's try to run this code. Oh, it should be arrays.fill, small error. Looks like our solution is working. Let's try to submit the code. Okay, our solution is actually runs in 0 millisecond. It's 100% faster than all the other submissions, which is pretty good. And I'll be posting this in the comments. You can check it out from there. Thank you. Hello friends, I am a cloud solutions architect at Microsoft who like making these videos, and today we are going to solve a lead code problem called generate parenthesis. Now if we see some of the popular companies who have already asked this question, there are companies like Amazon, Facebook, Microsoft, Apple, Bloomberg, Uber, Lyft, Google, ByteDance, Spotify and Nvidia. So that's why I am paying my utmost attention. I hope you also enjoy the video. Okay, so this is a lead code medium problem and also very well like problem on lead code. Basically, we are given an input number n and now we need to generate n pairs of parentheses. So basically we need to write a function that generates all the possible combinations of well-formed parentheses. Now these round parentheses, I think they are called well-formed parentheses. Now we can try to understand these two examples, but I'm actually going to take it one step further and I'm going to show you 4 different examples to understand that what this problem is asking us to do. Okay, now in this first example we are basically given n is equal to 1 pair, which means we need to make one possible pair and all the combinations of this well-formed parentheses. So obviously the answer is going to be quite simple. We simply need to return like just one possible pair that we can make out of this one. Now suppose n is equal to 2. So now for n is equal to 2, we have the choice to take like 2 of these and 2 of these, right? We need to take 4 values. So basically the number of possibilities we can make is that we can actually make a parenthesis that looks like this, and we can also make a parenthesis that looks like this. These are the only 2 possibilities we can have, and this is what we need to return as the answer. Now things becomes a little bit interesting when we reach to n is equal to 3. So when we get to the point where n is equal to 3, the possibilities we can make is, so these are the 5 possible pairs we can make when n is equal to 3. Now notice that over here for every single piece we are using like 3 opening brackets and we are also using 3 closing brackets, but we are just putting them in different pairs so that they generate like the well-formed parentheses. Same way, if we try to do it with n is equal to 4, the answer is going to be pretty huge. So let me just draw it over here. So these are all the possible pairs we can make when n is equal to 4, and basically we are using 4 opening brackets and 4 closing brackets and arranging them in different sizes. So this is a very interesting problem. Now let's see that what are going to be the different approaches to solve this problem. So now the first approach that comes to our mind is a brute force approach. In the brute force approach, what we can do is, suppose we are given n is equal to 2, right? If we are given n is equal to 2, there is one thing guaranteed. We need to have 4 characters inside every single block of our answer. Why 4 characters? Because we are generating 2 pairs of parentheses. So 2 pairs of parentheses is basically going to be 4 characters at least, right? So what we can do is, now we have 2 options to choose from. Either we can choose an opening parenthesis or we can choose a closing parenthesis. So what we are going to do is, basically we can take every single possible pair that we can make of size 4 using these 2 characters, and only the valid pairs we put them in the answer. So suppose we are given n is equal to 2, what are the different pairs we can make? Let me make just a few pairs. So these are just some of the few examples that we can make for 4 characters using like this opening and closing parentheses for n is equal to 2. And over here we only need to find the legitimate pair. So okay, we can find one legitimate pair and we can find another legitimate pair, and I think this is going to be the answer that we need to return. So we will put these 2 in the answer and then just return them. But if you see, this brute force approach is extremely inefficient. If we see like time complexity, the time complexity goes sometimes into like 2 to the power of 2n something multiplied by n just to check that whether the pair is valid or not, and that is disastrous. So no one is going to accept that. So we will have to find a way to do something better. So what we are going to do is, we are going to do things smartly. How we are going to do things smartly? First, let's define our purpose. Our purpose is to generate 2 pairs of opening and 2 pairs of closing brackets, and they has to be well informed or valid. Now we need like 2 opening brackets, so that is a given fact. We need 2 closing brackets, that is also a given fact. Now there are some properties that we can use at our advantage, taking consideration the definition of being valid. Now what is the definition of being valid? So basically, if we are given n is equal to 2, there has to be 2 opening parentheses and 2 closing parentheses. So that is one definition. Second definition for being valid is that we can only put a closing parenthesis if there exists an opening parenthesis before that. Again, I'm repeating myself. We can only put a closing parenthesis if there exists a closing parenthesis before that. We cannot start our answer with a closing parenthesis because that wouldn't be valid. Third thing that we need to consider is that we can only have that many number of open parentheses that is equal to the number of n. Now you are saying that why am I repeating myself? Because this is going to be the very important property that we are going to use. So now once we know all of these things, let's try to make some smart decisions on how we can actually generate the answer for valid parentheses. Basically we are given n is equal to 2 over here, right? Now we have option to choose like 2 opening parentheses and 2 closing parentheses. So okay, now what we are going to do is for our answer generation, always we will have to start with us an opening parentheses, right? Now we created the opening parentheses that starts with this one. Now we are going to keep track of few values. First value we are going to keep track of is the number of opening parentheses, right? So number of opening parentheses that we have used so far is 1. And what is the maximum we can use? Maximum we can use is 2 because that is the value of n. We are also going to keep track of the number of opening parentheses. We already know that is 1, right? We are also going to keep track of number of closing parentheses, and so far we haven't used any closing parentheses, so that this value is 0. And we can only add a closing parenthesis if the number of opening parentheses is greater than the number of closing parentheses, because we already proved that over here. Now using this logic, let's see that what is the sequence we can make. Okay, so first we start with this value. When we start with this value, number of opening parentheses is 1, number of closing parentheses is 0. Now over here we have two options, and those two options are we can either add one more opening parentheses or we can add a closing parentheses. So let's see options in both of the cases. The number of opening parentheses is going to be 2, and we can have this value to be 2 because we are given n is equal to 2, and in this case the number of closing parentheses is still going to be 0 because we have only used 2 open parentheses over here. Now in this case the answer is going to be a little bit different, because the number of opening parentheses is going to be 1 and number of closing parentheses is also going to be 1, and this is also valid. Why? Because the number of closing parentheses can be 1 because we already had 1 open parentheses. So far both of the cases are legitimate. Now again at this position we also have 2 more choices. So over here we have the one choice to open and we have one choice to close. Now let's see both the options. If we try to go one choice to open, what will happen is number of opening bracket is going to be 3, but that is not valid. Why? Because we are given n is equal to 2 explicitly. So in this case we cannot go down this path. So if we cannot go down this path, we will actually backtrack and come back to this position. Now from this position we can only go towards the path of closing. So if we go towards the path of closing, so far the number of open brackets we had is 2 and the number of closed bracket we had is 1. So that is still valid, that is still legitimate. Now again from this position we still have 2 options. We can either open or we can close. If we try to open, we cannot do that because number of open is going to be 3, so we are not going to go down this path. If we go down this path, basically the number of open bracket is going to be 2, number of closed bracket is going to be 2 as well, and this is the exact condition we need because we are given n is equal to 2. So which means that there has to be 2 open brackets and 2 closed brackets. So we can put 2 conditions, whether we can put like the combination of open plus close is going to be 4, that is going to be the double of what is n, or we can have like O is equal to 2 and C is equal to 2, both of them equal to 2. So this is also good. So now we have reached this condition, which means that whatever the path we actually make can make ourselves into the answer. So what is the path we took? So first we started with taking the opening bracket, then again opening bracket, then again closing bracket, and then again closing bracket. So let's put this value in the answer, right? So we are going to create a new variable answer over here, and over here let's put one entry that okay, 2 open, 2 close, that is good. Now let's start following the other path. I'm going to clean this up a bit so it does not become any more distraction. So now in this case, okay, currently we have one open bracket, one close bracket. Now again we have 2 possibilities. So first possibility is we can open one more bracket or we can close one more bracket. Now let's analyze both the possibilities. If we try to open one more bracket, basically the number of open brackets we are going to have is 2. Let me clean this up a bit more. And over here number of closed bracket we had so far is still 1. So okay, this is valid, we can put this one. Now if we try to put one more closed bracket, the number of open bracket we have so far is only going to be 1, but number of closed bracket is going to be 2, which is a big no. Why? Because we cannot have more closed bracket than the number of brackets we have opened, because that would defy the possibility of having a legitimate scenario. So we cannot go down this path, so we won't. And now again we have two choices at this position. We can open one or we can close one. If we open one, then the number of open is going to be 3. That is not valid, that is not good, so we are not going to do anything with this one, and we will not go down this path. If we go down this path, then over here number of open brackets we have so far is 2, and number of closed bracket we have so far is also 2, which is also the legitimate scenario. So which means that this path is also going to be a path that we can add to our answer. And let's see. Okay, so currently we have, okay, we have one open bracket, one closed bracket, we have also have one open bracket and one closed bracket, and that's it. Now initially, remember, we only started with this one opening bracket, and then we had two possibilities, and we actually exhausted both the possibilities, so we cannot go down further anymore. Now because we cannot go down further anymore, we can conclude that whatever the values we find so far, this is the complete answer, and we can return this as the answer. And basically this is the whole crux of the finding the optimal solution. Now you must be asking that hey, what we actually did was we did something very important. First we identify, okay, the one value, then we had the final case. So final case was that whenever the number of opening is equal to n and number of closing brackets is also equal to n, this is our final case. And then at every single position we had two options to either choose an opening bracket and closing bracket and keep on repeating the same process until we reach to the end, and we had some parameters in mind. So if you see, we are actually using dynamic programming at its finest, because at any single previously computed value, that is being used to calculate that which path we need to take and whether we can take that path or not. So we are basically using dynamic programming plus backtracking to solve this problem, and this is going to be like an amazing way to explain this problem. Logically think that in the brute force, what a disastrous result we were having, and we actually brought it down to such like beautiful answer, and then we are just presenting it. So this is the whole power of using any like computer language. So before we start implementing the generate parentheses method, first we are going to create our backtrack method. That is going to be our helper method that we are going to use recursively. Now for the backtrack method, it is not going to return anything, but it is going to add all the values towards the answer. And inside the method, we are actually going to create a list of lists that is going to store the answer. We are also going to have a string builder to keep track of the current values we have, and the number of opening and number of closing brackets, and also the maximum number of values we can generate. Okay, so now first let's create the acceptable scenario. So if basically the current length is actually going to be maximum times 2, which means that we have reached to our answer and we can add it to our answer. So this is the legitimate scenario. Now let's see, say for an example, we find out that we have not reached the answer. Then what could be the possibility? Well, first possibility could be the number of open brackets that could be less than the number of maximum brackets that is allowed. If that is the case, basically for the current string builder, we can actually append an opening bracket. So let's do that. And after adding the opening bracket, basically we will have to call the backtrack method again with a reduced value of one open bracket. So let's do that. So in the backtrack method, we are going to call the answer, and we are also going to call the current string builder list we have. But for the open, we are actually going to add one value, and for the number of close brackets, we are going to keep it as it is. The max is also not going to be changed, and that is awesome. Now there is also one more important thing we will have to do every single time we make a backtrack call, and that is to delete one character that is located at the current length -1, because it is going to add an extra character. So let's do that. Okay, now same way, say for an example, if the number of closed brackets and they are less than the number of open brackets, if that is the case, basically we can also add one closed bracket to our self as well. So let's do that, and we are also going to call the backtrack method, and everything else is going to remain the same. And basically this whole logic sums up our backtrack method. Now all we need to do is, from our main method, we simply need to create a list of list called answer. So let's do that, and then we are going to call our backtrack method. Now inside the backtrack method, we are going to provide the value of answer. We are also going to provide a new instance of a string builder. going to provide the number of opening brackets that we have used so far is 0, number of closing brackets is also 0, and the maximum number of opening and closing bracket we can have is going to be the value of n. And after getting the answer from the backtrack method, we can simply return the answer to be return the answer that we got, and basically that's it. Let's try to run the code. Okay, seems like our solution is working as expected. Let's try to submit the code. If we submit the code, our solution beats a lot of other solutions. It is really good in terms of time complexity, and it is also really efficient in terms of space complexity as well. So yeah, I'm going to be very satisfied with the approach, and now I would be posting this solution in the comments so you can check it out from there. Thank you. Hello friends, we are still not employed by a FANG company, so let's not stop lead coding till we get there. Today we are going to do jump game problem. Recently this problem has been asked in Amazon, Facebook, Apple, Google, Oracle, TikTok, all these gigantic companies, and they are some of my dream companies. So I'm going to do my utmost focus for this video, and I hope that you find it enjoyable. This is going to be the framework for the video. First we are going to understand the problem, then we will come up with a brute force approach. We'll improve our brute force approach. We'll find the optimal solution, and then we'll write the Java code for the optimal solution. This is a medium problem, and we are given an integer array nums, and we are initially positioned at the first index, so 0th index. Each element in the array represents that that is the maximum jump we can take, and if that is true, can we reach to the last position? So if we are able to reach to the last position, we would return true. If we cannot reach, we will return false. So let's understand this with an example. Suppose our given input is like 2, 3, 1, 1 and 4, and initially we are located at this position. This is the same example over here. So we can see that if we over here we can take maximum 2 jumps. So either we can take 1 jump and reach over here, or we can take 2 jumps and reach over here. Let's get the greedy approach, and we'll take the maximum amount of jumps. So over here if we take 2 jumps, we end up over here. Over here the maximum jump we can take is only 1, so we'll reach over here. Again the maximum jump we can take is just 1, so we'll reach over here, and this is our last position. So since we have reached over here, which means that we can conclude that we can solve this jump game, and we can reach to this end position. So we'll return true in this case. Now let's take one more example. So suppose we are given input like this: 3, 2, 1, 0 and 4, and if we check for the possibility, so over here the maximum number of jumps we can take is 3 jumps. So if we take 3 jumps, we reach at 0. From 0 we can't move anywhere forward. So let's, rather than taking 3 jumps, we'll try to take 2 jumps. So if we take 2 jumps, we end up over here, and over here the maximum we can take is just 1 jump. So again we end up at 0. And lastly, rather than taking 2 jumps from here, we'll just take 1 jump. So we'll end up over here at this position number 2. Now at this 2, the maximum jumps we can take is 2. So again we end up at the 0, which means that in any circumstances, if we start at this position number 1, we cannot reach to this last position. So over here we would return false. This is basically the problem statement. I have given a custom example that we are at any position. We are going to first of all see that what is the maximum jump we can take. We'll try to make that jump. We'll try to see that using that jump, if we can reach to this end index. If we cannot reach to the end index somehow, we will backtrack. We will go back to the position where we initially took the jump from, and we'll try some other possibilities. So let's see that in action. So over here we are initially at this position number 2. The maximum jump we can take is at value number 2. So that jump will bring us over here. Now over here the maximum jump we can take is at this position 0, which means that we can't move any further. So we will backtrack. We will come back over here. Now again we are at this second position. Now let's, rather than taking the 2 jump, we will reduce our jumping possibility and we will just take jump of 1 step. So now we reach at this value number 3, and over here with this value number 3 we can take maximum jump of 3 steps, which means that we can, if we take 3 steps, we will end up over here. So 1 2 3, and at this position 2 the maximum number of steps we can take is 2, which means that even if we take 2 steps we will cross our last entry, which means that in any case we would be able to reach to this last element and we would return true in this scenario. Now this approach seems sensible on pen and paper because we are dealing with a small number of things, small number of input, and we are able to clearly see that how the pattern is going on. So let's take another example. So these are the values. Let me also denote the index values for these. Now with every single iteration I'm going to note down the index value transition we are making. Okay, so initially we are at this position number 5. The maximum jump we can take is a 5 step, which means that we would end up over here. So initially we would do something like this. So 0 to 5, this is one step we take. We are at 0 position, which means we can't go forward, which means we have to backtrack, which means that again from 5 we will come back to this 0th index. Now from 5, rather than making a jump of 5 steps, we will make jump of 4 steps and we would end up at this position 4. So from 0 we would end up at this position 4. Now from this 4 the maximum jump we can make is 1. So again we will take 1 step jump and we would end up at this position 5. Again from we are at 0, we can't do anything, so we will have to backtrack. So in order to backtrack we will go back to this position number 4. Again we have to backtrack from this position 4, so we will end up at 0. Again we will, rather than making a jump of 4 step, we'll make a jump of 3 step and we'll end up over here. So we end up over here, and so on and so forth. So you can see that this in this approach all we are doing is just we are going someplace, we are coming back. Again we are going, and then again we are coming back. Again we are going to some next element, we are going to some next element, and we are coming back. And suppose this keeps repeating multiple times, you are essentially depleting your resources, because if you see the time complexity at any single iteration or at any single value, we have two possibilities: whether we want to keep this value in our current transition, or we do not want to keep our value, keep this value in our current path that we are calculating. Which means that the input, if we make decision tree, the decision tree would keep on growing and growing with addition of every single value, which means that we are basically making a lot of decisions, and the time complexity in this scenario would actually be big O of 2 to the power n, because at every single position we are making two possibilities. This is a very bad exponential time complexity which we cannot allow in any scenario. Okay, so the issue in the brute force approach we had is that we were doing a lot of repetitive work, because at any point we found out that we are not able to make any progress from this point. We were still ending up at that point. So let's see that how can we counter that with a better approach. Suppose we create an additional data structure over here. So we create a dynamic programmatically additional data structure over here. Let's create an array, and in that array we are going to define that at any position can we reach to this endpoint, and if we identify that yes, we can reach to this endpoint, we would basically fill that position as true. And let's see that how it can help us. So if at any point in time we are at this final position, we know that this is the main terminating case, which means that we can put true over here. So this final element we can always put true, and this would actually become our base case. Now we have a base case. We are going to start iterating on from right to left manner, and we are going to start filling up our DP array to see. And in the DP array, the only thing we are mentioning is that at any given location, if we are able to reach to this endpoint or not. If we can, we'll just mark it as true, otherwise we'll mark it as false. Okay, so now one step over here, this is this value has potential to make two jumps, and it only takes one jump to get to this last point, which means that if we end up at this fourth position, we can reach to this fifth position, which is what we want. So over here we can also fill this as true. Now we are at this zeroth position. From the zeroth position, can we reach to this fifth position? No, because we cannot, we can basically can't make any jumps. So we'll just fill this as false. Okay. Now from this one, can we end up at this fifth position? So we are going to, now the interesting part comes. Now we are going to check that, okay, this has possibility of only doing one jump, right? So with one jump, we can only end up at this third index. Now we only need to check that in this DP array for this third index, if the value is true or false. So in this case, this is already false, which means that the maximum we can get to is this third place. From this third place, we can't go anywhere. So we don't even need to check these values. We can only check this DP table, and we can conclude that no, we can't go anywhere forward. So we will put a false over here as well. Now we are at this third position. Now from this third position, we will again do the same check. But the thing is, this has potential to do three jumps. Okay. So let's do one jump at a time. So first we take a jump. If we take a jump of one step, we end up over here. We check over here that this is false, which means that this is false, right? Now we take second jump. With the second jump, we end up at this third position. We check in this DP array. This is also false, which means that we can't do anything. Now from this third position, we still have one more possibility, that we can take a jump of three values. So if we take a jump of three values, we end up at this position, value number, this index number 4. So for this index number 4, we see that the value is true. If we find any true, which means that we can say that from this second, this index number 1, we can reach to this last endpoint. And now for this position, we need to check that it has potential to do two jumps. We will only check for one jump. So with one jump, we will end up at this first index. That one is true, which means that we can fill true over here as well. And in the end, we just need to return whatever of DP of 0 we found. So in this case, we can determine that this is true, which means that we are able to come to final endpoint. So this solution is very good. It works perfectly fine. Okay, so the time and space complexity for this approach would be, so the time complexity would be big O of n square, because notice that we need to do one iteration to go on the for every single element, and sometimes for any given element we might have to do multiple jumps, like we did in this case of 3. So in the worst case, we might have to solve this in big O of n square time, and the space complexity would also be big O of n, because we are creating this additional DP array. Now this is still much better than our brute force approach, but our aim is to go into companies like Google, Facebook, Amazon, Apple, and whatnot. So those companies expect the best out of the best solutions. And is this the best out of the best solutions we can do? Actually, no, there is still a better optimal solution, and let me show you how we can get there. Okay, and this optimal solution is actually based on the dynamic programming solution that we just saw. So in dynamic programming, what we are doing is we are creating an additional DP array, and we are storing that whether we can reach to this last element or not. But the thing is, what if rather than storing this value at any position, when we find out that, suppose from this position, we found out that yes, we are able to reach to this last position. So why do we need to check that whether we can reach to this last position or not? If at any point amongst these values, if we end up at this position, we would still be able to guarantee that we can reach the last element, because we have already checked this condition. So rather than checking for this whole thing, if we just check that, okay, from here, if we can reach to this element or not, and if this is true, we can simply return true at that moment also. And let's see that in action. So let me clean this up a bit. Let's mark all the index values. Okay, initially we create an element called final, and this final element represents the last value in the given input, and initially we set it up to this index number 5, right? Now our aim is that at any point we found out that amongst these values, if anyone can reach this final element, then that element by itself becomes this final. So rather than storing all the values of at any given location, we are actually shrinking down our boundary of search. Initially the final is at this 5th position, now we are at this 2nd position. So all we need to do is to check that whether our current index I, our current index and this current value, if sum of these two is actually greater than whatever final we have. So currently the final we have is this 5. So this is the final we have. Current sum of these two values becomes 4 plus 2 is equal to 6, which is greater than 5, which means that we can update the value of our final. So now this becomes our new final, and we basically don't care about this value anymore. Now we are at this 3rd location, and we try to see that the index plus its value. So this becomes 3 plus 0. Is it greater than our final? No, this is not greater than our final, because this is 3 and this is 4, which means that we can't do anything over here. So we drop this calculation and we check with the next element. So over here we have this 2 and we have the value 1. So 2 plus 1, is this greater than 4? So greater than final? No, this is also not true, which means we can't do anything over here. We again go back. Now this is 1 and this is 3. Now 1 plus 3, is this greater than or equal to value 4? Yes, this is greater. This is actually equal to 4, which means that we, from this point, we can come to this point. This is what this concludes, and which is what we want, right? So now we know this information, which means that we can update the value of our final again. So now the value of our final would become 1. So at this value, and now at this 0th position, we need to check that whether we can reach to this 1 or not. So over here the sum of these two value becomes 0 plus this is 2. So 2 is definitely greater than the final amount we have is 1, which means that we can reach over here. So the final element would be shifted to this point, and our at the end of our iteration the final would be 0. So now the final is 0. After the end of the iteration, we only need to check that what is the value of final. If final is 0, we return true. If final is anything other than 0, we return false. And this is a very good solution. The whole thing runs in the time complexity of big O of n. And if we see the space complexity, we are only storing one additional parameter. So we are essentially using constant space, and we are solving this problem. So this is a very efficient solution. Let's create a variable called final. Oh, it's Java, I can't use final. Let's call it final with an extra L, and we'll assign its value as nums.length -1. And now we will run a for loop, and we'll start it from I is equal to number of length nums.length -2, because we already know the result for the array length, and we will run it up until we reach to this 0th position. We'll do I minus minus, and inside the loop we are only going to check one condition, that if the current value of I plus nums of I, if they are greater than or equal to whatever the final value we have, we can update the value of this final parameter to whatever the ith value we have. And yeah, that should be pretty much it. Now we only need to check that if the value of this final character is 0 or not. So if it is equal to 0, we can return true, else we can will return false. Okay, let's try to run the code. Seems like our solution is working. Let's try to submit the code. Okay, our solution works 100% faster than all the other solutions. This is really good sign, and this is not constant time, but because we are basically shifting our boundary, we are essentially reducing the number of work we can do. And also, if you see the memory usage, we are actually better than 86% of all the other solutions. So this was a very small line of code, but this small line of code actually requires huge set of understanding. So see you in the next video. Thank you. Hello friends, I am a cloud solutions architect at Microsoft who like making lead code videos, and today we are going to solve an awesome problem called Jump Game 2. If we see some of the popular companies who have already asked this question, there are companies like Amazon, Google, Goldman Sachs, Bloomberg, DoorDash, Uber, Microsoft, Apple, Tesla, TikTok, Snapchat and ByteDance. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a lead code medium problem and also very well like problem on lead code. Basically in this problem we are given an array of integer called nums as an input, and we are told that we are initially positioned at the first position inside this given array. Now our aim in this problem is to return the minimum number of jumps required to reach to the last position. Now you must ask that how are we going to make these jumps? What are the criteria for that? So the criteria for any jump is that any given value that is presented inside this given array represents the number of values it can jump. So basically if this one is represented 2, we can say that it can reach it can either take like one jump or it can take 2 jumps and reach to these positions, and our aim is to reach this last position, and basically we need to do this in the minimum number of jumps that is required. Now if you are confused, don't be. I'm actually going to show you a couple of examples to understand that how things work. So basically over here we are given 5 different values, and for these 5 different values, as I mentioned earlier, every single value represents the maximum number of jumps it can take. So this value number 2 has two possibilities. It can either take one jump and reach to this position number 3, or it can take 2 jumps and reach to this position number 1. Same goes with value number 3. It has 3 options. It can take like 1 jump, 2 jump or 3 jumps, and then do that. And our aim is to reach the last position from the first position in the minimum number of jumps possible. So if we see in this example, the answer is actually quite evident. We start our position at this value number 2, and if we just take like first jump to reach to this value number 3. Okay, so currently the number of jumps we have taken is 1. Now from this value number 3, if we take another jump of the size 3, basically we would be able to reach to the end position, and in total we are only taking 2 jumps to reach to the end. So basically we need to return 2 as the answer in this case. If we try to understand the second examples, things are a little bit different. So in this case we can only take one jump. So okay, so currently the number of jumps we have taken is 1. Now from this 1 we need to take one more jump to reach to this position. So again the number of jumps we have taken so far is 2. Now from this 2 we have two options. Either we can take one jump and reach over here, but that is not the most optimal way. Most optimal way is we take a jump of 2 steps and reach to directly to this end point. So basically the answer in this case is going to be 3, that we need minimum 3 jumps to reach to this last position, and in this case we need minimum 2 jumps to reach to this last position. So this is what the problem is asking us to find, and I know it can look tricky, but it's really simple to do it. And let me show you a couple of different approaches to solve this problem. Okay, so the first approach that comes to our mind is a brute force approach, and in the brute force approach basically we are just going to use the simple logic. The logic is that at any single position we will try to see that how many jumps it can take, and try to explore all the possibilities and try to find that how many jumps it takes to reach to the end element, and also have like a minimum variable in mind that whenever we find minimum number of jumps we will keep on adding it over here, and eventually when we compute all the calculations we should have a result. So in this case what we are going to do is that okay, this value is 2. So first we will consider the possibility of just taking one jump. So in this case, okay, if we take one jump, we reach over here. Again, we have three possibilities over here, but we are only going to take one jump. So again, we reach over here. Again, this only has one possibility. So we reach over here and then we reach to the end. So in this case, we took in total 5 jumps to reach to the end. Now secondly, we are going to take like different things. So first we will take 2 jumps. So we took 2 jumps and now we take one jump every single time and try to see how when we reach to the end, and so on and so forth. We keep on repeating the same process with different combinations. Now just by the explanation, you can imagine that how complicated it's gonna make things, because for every single time you will have to calculate different permutations and combinations of sums, and eventually it's gonna lead to very disastrous results. Like if we see time complexity in this case, it's gonna be in the order of n factorial, because for every single element we will have to compute the process for all the other elements, and that is going to be in the order of big of n factorial, which is really bad. So we will have to find a better solution, and the better solution is actually quite simple. So let me just directly go to the optimal solution. And now for the optimal solution, we are actually going to use a very interesting concept called greedy concept, and basically we are going to try to make the biggest jump possible every single time and try to see that where does that leads us. Now being greedy is not good in real life, but in computer science it is like the must thing, so you have to do it. Now for the greedy approach, we are actually going to keep track of 4 different variables. So first variable we are going to keep track of is the index value we are currently at. So let's just name it as index. Again, we will also have to keep track of the number of jumps we have made so far. Also we will need a variable to keep track of current maximum variable that we have been able to reach, or current maximum value we have been able to reach. And also from the current index, we will have to keep track of that what is the current end value we can reach at. So there are 4 variables. Let me go over them again. First one is the index value. Second one is the number of jumps we have made so far. These two are sensible. Third one is to keep track of that what is the current maximum value we have achieved so far, and we will only update it when we find like a better maximum value. When we go through the example, everything will make more sense. And the current end defines it is in correlation with the index value, that where does the current end lies, and if we are at the index value, then we will have to make some changes. So now let's look at the example, and currently let's initially assign the values. So initially the number of jumps are 0, current maximum is also 0, and current end is also 0. Now we start our journey. So first we come up at this first index. So whenever we are at the first index, okay, the index value currently is 0. Now the index value is 0. Now let's just keep on updating these values, right? So currently this has value number 1. So if this has value number 1, which means that this 0th index has the potential to reach maximum at the first index, which means the current maximum value we can achieve is that, okay, this current value is 0. Now over here it says that it has maximum potential to reach index value number 1. So 1 is definitely greater than 0. So because it is greater than 0, we will update the value of current maximum to 1, that okay, this is the maximum value we have been able to achieve. Now the interesting part comes. The current end we were at, the current end was 0 because we were at the 0th position, and also the index value we were at was also 0. So because both of these values were same, which means that in order to get ahead to the next index, which is not the last index, again remember I am repeating, in order to get ahead from the current index, which is not the last index, we will have to update the current end, because currently the current end was also here and the maximum value was also here, but this has the value 1, so we have the ability to go to the next, which means the current end needs to be updated. And whenever both of these are at the same place, that means if we are updating the current end value, we will only update the current end value in the condition when we are making the jump. So again, let's just go back to our analysis. Because the index value and the current end both were same, so because these two values were same, we can define that we need to update their values, which means we are taking a jump. So okay, so we made a jump, so we will do jump plus plus, so currently this value becomes 1. But the thing is, where do we update this current end to? We will always go this current end to the whatever the maximum value we have been able to find so far. So current maximum we found is 1. So again, we are going to include this value number 1 over here. Now let me clean this up a bit. So now we are at index position number 1. So we will update our index value. So our current index value is 1. Now at this position, what is the maximum it can travel? Maximum it can travel 3 points. So 3 is going to be 1 plus 3, so that is 4. So now this is the current maximum we can achieve, that is 4. So we will compare 4 with the current maximum we had. Current maximum is 1, so 4 is definitely greater than 1, which means it is sensible for us to update the current maximum. So current maximum becomes 4. Now we will also have to check that what is the current end. Now current end is still same as the index value, because this was the current end, so which means that anyways we will have to make a jump. So because we are making a jump, we will update the value over here. So currently the number of jumps we have made so far is 2, and we will also have to update the value of the current end. So max current end we can reach is position number 4, because we already established that that is where the maximum number of jumps we can take. So okay, we are good up until this point. Now again let's make the changes. So now we are at index number 2. So let's see that what story happens at index number 2. Now index number 2, the maximum we can take jump is 1. So if we take one jump, we reach at index number 3. But the thing is, if we check the current max is already 4, and the maximum we can reach is 3. So 3 is actually less than 4. So in this case we don't need to update the current max. Okay, awesome, we are not updating the current max. And now we check, okay, current end is 4 and the index value is 2. So these two are not same. Because these two are not same, we don't need to update the current end or the number of jumps that we are taking. Now okay, now our index value keeps on updating, because we are checking this for every single index value. So now we are at position number 3. So now at position number 3 we have maximum 3 possibilities, right? So if we go to 3 steps, we reach to the index number 6. So our current maximum will become 6, because definitely 6 is greater than 4. Now we updated our current maximum. Now we also need to check few other things. Okay, so current end and index value, these two are not same, so we are not going to do any changes for now. So now our index value becomes 4. So let's update this. Okay, so this becomes 4. Now we are at this 4th position. This only has possibility of 1, so this will reach to the maximum of 5, but 5 is actually less than 6. So in this case we will not update the current maximum. Now in this case the index value and current end is both of them are same. So because both of them are same, we will have to do the update. So now when we do the update, okay, we are going to mark the current end as 6, because that is what the current maximum we have been able to achieve, and also the number of jumps we are going to take is going to become 3. Okay, now again we keep on repeating the same process. So again our index value becomes 5. Now because with the 5 index value, the maximum we can take is 1, so that is going to lead up to 6, but we already have current maximum at 6, so we don't need to do anything. And these two values are not same, so we are not going to do anything. Now the index value is at position number 6. Now at position number 6 we are actually able to reach to the end with just a single jump. So we are going to do that. Okay, now we reach to the end of this jump, but the thing is we are just going to, for the sake of simplicity, go ahead with this calculation. So the current maximum we have been able to achieve is going to be 7. That is the end. Now current end and the index value, both of these are same. So because both of these are same, we will have to update our number of jumps that we need to take, and also we need to update the current end. So current end in this case is going to be 7, and we are going to check that if the current end reaches to the last position or the size of the array, that means that is the answer, and we can break out of the loop, and whatever the answer we have been able to find, we can simply return this. So in this case, for this example, the answer is going to be 4, that we can return simply. And this is the most beautiful approach of the greedy solution that I have seen so far. Now if we see time and space complexity, in this case the time complexity is so good because we are only going through every single values and calculating, keeping track of 4 different variables. So time complexity is actually going to be big O of n. So notice that from big O of n factorial we were able to bring it down to big O of n, and all due to the greedy approach that we took. If we see space complexity, in this case the space complexity is actually going to be big O of 1 or constant space. Why? Because we are not using anything else apart from like these 4 values. So that is also a wonderful news. Okay, so let's initialize three variables that we need. That is going to be jump, current end, and current maximum. And initially all the values are going to be 0. Now notice that I'm not using the index value over here, and that is because we can actually use it from our loop directly. Now let's run a for loop to iterate over the given input array. So now every single time we will check that what is the current maximum we have been able to achieve. So we are basically going to compare the maximum value amongst the existing current maximum value or the value of I plus whatever the value of nums of I for that particular I is, and whichever is maximum we are going to put it in the current maximum. Now we are also going to check one very critical condition, that if the given I is actually equal to the current end we are at. If that is the case, which means we will have to update the value of the jump. So we will do jump plus plus, and we will also have to update the value of the current end. So current end is in this case going to become the current maximum that we have been able to achieve. And believe it or not, but this concludes the whole solution. After we get out of the loop, we can simply return the jump that we have been able to find, and this should be it. Let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And if we submit it, this is beating like almost 99.99% of the solutions in terms of time complexity, and in terms of space complexity, this is also very efficient. So this is a very good solution. And if you see, we are just only using a single loop and just like few lines of code to solve this problem. And I would be posting this in the comments, so you can check it out from there. Thank you. Hello friends, I'm a cloud solutions architect at Microsoft, and my aim is to empower every single person to be better at technical interviews. Keeping with that goal in mind, today we are going to solve a very interesting lead code problem called race car. And if we see, this has been one of the most popular problem at Google. Though not many companies have asked this, but the companies that did, they are really popular companies. So Google, Amazon, and Microsoft, they all have asked this question, and Google literally loves this question. So let's start understanding the problem statement. So this is a lead code hard problem, and quite justifiably this is a hard problem. Basically, we are given a car that is currently located at position number 0, and the initial speed it has is +1. Now we are dealing with two factors here. First factor is that we have the ability to accelerate the car, and second factor is that we have the ability to hit the reverse button or reverse instruction in the car. And we are told that car can go infinitely in a number line, and car can go in like positive direction or negative direction, and basically it follows whatever the instructions we are providing. So what does these accelerate and reverse instruction means? Basically, whenever we hit the accelerate instruction, car is going to change its position. So car is going to change its position based on whatever speed it had previously, and then its speed is going to double. So what it means, I'll explain it to you just in a second. Also, if we see the instructions for the reverse button, basically, whenever we hit the reverse button, whatever the speed of our car was, if it was positive speed or if it was going in the positive direction, basically the speed is gonna turn to -1, or if it was going in the negative direction, the speed is gonna turn to +1. So basically car is gonna change its direction, and also speed will come back to 1, but the car's position is gonna remain same, which means car will only move when we hit the accelerate button, but this reverse button is there to dictate that which direction the car moves into. Okay, so now I have drawn a numbers line over here, and now we will see that based on different instruction, how does our car proceed, and what are the different changes it happens. So we have few factors that we need to consider in this case. First factor is instructions that we are providing. Second one is what is the current position, what is the speed, and what direction the car is going into. So let's start with this one. Let's start filling up with the initial positions. So initially, car is located at position 0 and initial speed is 1. These are the two factors that we are given by default. Now, as for the instructions, suppose we provide the instructions to accelerate car. What would happen is,
Initially car was located at position number 0, which was this one, right? So previously car was here. Now we provided the instructions to accelerate. And also one more thing I forgot to mention, the direction, currently we are going in the positive direction because the speed is positive. Now the position is going to become position speed plus speed. So 0 plus 1, it's going to become 1, and speed is also going to update to multiply by 2. So now this is the new position of the car, and the speed is 2, but that will come in effect when we provide the next instructions for the acceleration. So let's do that. If we add one more instructions for acceleration, what is going to happen is that, okay, currently the position was 1, but now we are providing the accelerate instruction. So basically it's going to be 1 plus 2. So now position is going to become 3. So currently our car ends up at position number 3, and the speed is going to become 4 because speed multiplies by 2 every single time. If we add one more instructions for accelerate, basically our car is going to end up at 3 plus 4, it is going to be 7. So let's just clean this up a bit. So now the position becomes 7, our speed becomes 8, and car's position is 7 currently. So this is what happened after 3 instructions that we provided. That initially our car was at position 0, then it came to 1, then 3, and then 7. But notice all of these are just accelerate instructions that we have provided. Let's try providing a reverse instructions. If we provide a reverse instruction, basically currently the speed is plus 8. So this is a positive speed. We are told that if the speed is positive, speed is going to turn negative. So this is going to become -1, which means that direction that previously we were going in the right side of direction, now we are going in the left side of the direction. We are going to proceed negatively. Remember, car's position is not gonna change because that is what we are told that the definition of this instruction right is. So now currently car is still located at this position number 7. Now let's try to put one accelerate. If we put one accelerate, what is going to happen? Well, position is going to change. Position is going to become 7 plus whatever the speed is, and speed in this case is -1. So 7 plus -1 is going to become 6, which means that now the position of car is going to end up at this position number 6, and speed is also going to double. So now speed was -1, so speed would be -2. Let's add one more accelerate. If we add one more accelerate, basically this is what this is going to do is that current position is 6. So 6 plus -2, this is going to end up at position number 4. So now car ends up at position number 4, and the speed will become -4 for the next iteration. Say for example, we decide to add one more reverse over here. If we add one more reverse, basically nothing is going to change in the position. Position is still going to be at value number 4, but the speed that was originally minus a negative value, now it is going to become +1. So if it becomes +1, which means that the direction now on is going to go on the right side. And this is the whole logic of this accelerate and reverse instruction means, and this is what happens on the number sequence. So after understanding this, let's see that what does the question is asking us to find. Basically in the question we are given a target value, and we are told that we are initially starting at the position number 0 and with the speed 1. So we need to see that what is the shortest sequence of instructions that we can provide that will get us there, and we need to return the length of those instructions. So let's try to see what does this mean and see a couple of examples that what this is asking us to do. So I made some changes, and we also added one parameter target that we need to consider. So say for an example, suppose we are given the target value to be 3. So we need to reach at the position number 3 inside our linear distance that we are given. So let's see that what is going to be the shortest set of instructions. So if we provide one accelerate, which means position is going to become 0 plus 1, it's going to become 1. Now speed is going to become 2 for the next step, and our car is going to end up over here. Now let's add one more accelerate. If we add one more accelerate, basically our original position was 1, so 1 plus 2 is going to become 3. This 3 is critical because this is what the target is asking us to find. So we have already reached the target value, and speed, like, it's going to become 4, but this is not going to be of concern because we already hit our target value. So since we hit our target value and this is the shortest possible way to do it, it took us 2 instructions to reach to the target value 3. So in this case, as the answer, we are going to return 2 that we need minimum of 2 instructions to reach to the target value of 3. Say for an example, we take one more consideration. So in this case, we provide the first instructions of A. So in this case, our position is going to become 1, our speed is going to become 2, our car is going to end up over here. We add one more accelerate. In this case, our car is going to end up over here, our position is going to become 3, and our speed is going to become 4. Let's put one more A. So our car is going to end up over here, and we are going to, the position is going to be 7, the speed is going to be 8. The thing is, we were intending to reach to this position number 6, but this 7 is actually greater than 6, which means we have already surpassed it. So we need to come back, which means we will have to change the direction. So previously the direction we were going is in the right side direction, we will have to change the direction. Whenever we have to change the direction, we are going to use a reverse. If we use the reverse position, car's position is not going to change, but speed is going to become -1. Now because the speed is -1, let's try to add one more accelerate. If we add one more accelerate, basically the position is going to become 7 plus -1, so it's going to become 6, and our car is going to end up at value number 6. Now the speed is going to become -2 for the next iteration, but we don't care, and in this case the target value 6 has been achieved. If we see how many instructions it took us 5 instructions to get there. So in the answer we are going to return 5, that we need minimum 5 instructions to reach to target value number 6. And this is what the problem is asking us to solve. Now let's see that what are going to be the different approaches to solve this problem. Well, there are actually two ways to solve this problem. First way is to treat like every single value as nodes and use like a breadth first search to solve this problem, and treating this as a graph problem. The other way to solve this problem is treating this as a dynamic programming problem. And Google is actually huge in dynamic programming concern. Like they really love their dynamic programming concepts. And this is what I'm going to show you in this approach. So let me know in the comments if you want to see the BFS solution as well. I can show it to you maybe sometime in the future. So before we come up with the optimal solution, first let's try to understand that what are the moves of accelerate and how it works for every single instructions. Suppose, okay, initial position is going to be 0 and initial speed is going to be 1. We all know that. If we add one instruction of A, okay, our car is going to end up over here. This was the first position, right? If we add one more instruction of A, our car is going to end up over here. If we add one more instruction of A, our car is going to end up at position number 7, and if we add one more instruction of A, our car is going to end up at position number 15. Why this happens? Because speed gets multiplied by 2 with every single occurrence of A, and that is where we are doing like position addition, right? So is there a mathematical sense behind these values? And yes, there is. How can we define that? Suppose we define a parameter called x that refers to the number of accelerations we use. So in this case, currently we have used 4 accelerations. So currently x is going to be 4, right? We are just using some arbitrary variable to define a mathematical equation. Now in this case, if we directly want to know that what is going to be the position based on the number of x, can we directly know it? Yes. The equation is, if we do 2 to the power of x minus 1, then it will provide us that for any number of accelerations, what is going to be the position of the car. And this is a really important thing to find. Now, how can we define this theorem? So say for an example, if we are originally given only with 2 a's, so 2 times we are using this. So currently x is equal to 2. We know that when we provide 2 accelerations, the value we have is car is going to be position number 3. If we apply this formula, basically it's going to be 2 to the power of 2 minus 1. So 4 minus 1 is going to be 3, which is correct. Same way, if we try to apply x to be 4, in this case, the answer is going to be 2 to the power of 4 minus 1, which is going to be 16 minus 1, which is 15, and which is what we calculated. And why this is happening? Because every single time speed is being multiplied by 2. So we can actually see a relationship forming between the position of car by the value of A. And the important thing is, A is only being used to move the car. So car can move in this direction or this direction. That depends on the value of R. But the thing is, car is only going to move based on the value of A. Okay, now after knowing that what are going to be different possibilities of A, there can be three distinct possibilities for us to find the target value. Suppose the target value we are given, it is located someplace like this, right? Now, there can be three distinct possibilities, and currently we are only considering that we are only using accelerate function. We are not using reverse function for now. When we use it, I'll let you know. So first possibility is that we find some arbitrary value of accelerate that gets us somewhere over here, which means we are not at target value, but we are one value before that, that can, like, as further as we can get near the target value using only accelerate. Another possibility is that if we do one more accelerate, we go beyond the target value and we reach somewhere in this area. Now, the third possibility is that if we only use accelerate function, we directly hit the target value. If this is the case, this is going to be like the minimum number of effort we need to find the answer. And this is going to be the best case scenario, but that rarely happens. There can be infinite numbers and there are only so many numbers that can directly hit A. So now let's see that what would happen in each of these scenarios where either we are located before the target value or we are at after target value. What should be our approach in each scenario, right? So let's try to understand this logic with something important concepts. First concept is that, say for an example, we are in a scenario where our position is somewhere over here and this is the target value, and if we do one more direct acceleration, we are jumping away. So other logic is that we already know how much effort it took to get here, right? We have already those sets of instructions, so we won't bother doing anything. But now from this point, we can actually break down the problem in a smaller sub problem where we only need to check that how much effort it takes to make these moves, and we can actually do that. Why? Because at this position, whatever the speed is, say for example speed is 8, right? If we use a reverse in this case, speed is directly going to be -1, which means we have the ability to go like on this direction, and it could be beneficial to go in this direction for a bit and then come back directly towards the target direction, because we already have the equation that position is going to be 2 to the power of x minus 1, and using this we can do some pretty cool results, right? Now in this case, if we slow down over here, if we use a right over here, which means immediately we have two possibilities. Either we can use accelerate and go in this direction, or from here we can directly use one more reverse and then directly go to this T. Because if we slow down here, we definitely would have to use two different R's, because first R is going to make the direction go negative and second R is going to make the direction go positive, and then we would be able to reach to this target value. That is one logic. Second logic is, suppose we are in an opposite scenario where the target value we are given, it is located here, and the answer we are trying to find, or based on the accelerates we did, we end up somewhere over here. So if we have already gone beyond the target value, the basic logic is that we definitely will have to use the reverse gear, and after using the reverse gear, our speed is going to go in that direction. We only need to be concerned about finding this smaller path rather than finding the whole path. So we are only finding the difference between, say for example, this is the target value and this value we call it like I value. So we are only considering to finding that how many moves it takes for us to do like I minus T target value. And this is a smaller sub problem. And same way, in this scenario, suppose this is value I and this is value T. So in this case, we are finding a smaller sub problem T minus I to find that how many moves it takes to do this. And we keep on breaking this again and again and again until the point where we reach to a target position, and using acceleration we get to the same value and then we mark its moves. So this is the whole logic of the solution we are going to use. And for every single position there can be different options we can take, but basically this is how we are breaking a bigger problem and grinding down in the smaller sub problems to find the answer that we need. So basically we are using dynamic programming at its finest. So let's see that with some of the examples how we can actually solve this problem. And at the same time, we are also going to use some logic to our advantage. The logic we are going to use is that we are going to initialize a DP array. Now inside this DP array, we are actually going to mark the positions of accelerations using the formula we already established, that is 2 to the power of x minus 1. And over here we are going to mention the index values as the number of a's or the number of x in this case, and we are going to see that what position does it ends up at. So if this is 0, this is definitely 0. Then for the this is 1, this is going to be 3, and this is going to be 7, and this is going to be 15, right? These are the different possibilities we have. I have already drawn a number series over here as well. Now say for an example, the target value we are given, the target value is value number 7. If the target value is value number 7, do we need to do any calculations? No, right? Because we can directly see over here that this provides us the value of 7. Then basically it takes us 3 steps to reach to the value target number 7. So in the answer we can directly return 7 as the answer. And why we were able to do it? Because we only use acceleration to get there. So this is like the best case scenario. This is one of the examples. Say for an example, the given problem is not so simple. Suppose the given target we have is value number 9. What we are going to do in this case? Now things becomes a little bit tricky, right? We are trying to reach this target value. We already have our this DP array. So based on this, we already know that target falls between these two values. So it has to be playing around between these two numbers, right? So let's mark both of them down. So first, this is the first position that we can reach, and it takes us 3 steps to get there. So we already know that there is an effort of 3 steps to get to the value number 7, and our aim is to reach to the target value number 9, right? Also, there is another possibility that we can end up at value number 15, and it takes us like 4 steps to get to this value number 15. So now let's just mark down all the 3 steps that we took to get over here, and we are also marking down all the 4 steps that we get to reach to this value number 15. And now we will try to break the problem into a smaller sub problem. And the smaller sub problem is that what is missing over here? We need to recover these 2 steps. How we are going to recover these 2 steps, how many effort it takes us for each 2 steps. If we look at this DP array, we do not find a direct entry that can only be done using only accelerate values, right? But what we can do is, at this position number 7, we can add a reverse over here. If we add a reverse over here, what's gonna happen is that now speed at this position is going to become -1, and currently, okay, so position is 7 and speed became -1, right? Now what are some of the interesting things we can do? First interesting thing we can do is we can try to find that if we go in this direction and we are able to calculate some direct DP that we can make. So say for an example, if we take 1 step, now the position is going to become 6, the speed is going to become -2, and over here we took 1a, and currently this is the position. And now what is the difference between these 2 entries? The difference is actually 3. 3 we can directly make. So let's see that what is going to be the effort to make this answer viable, right? The effort is that now at this position we will have to do another reverse. So if we do another reverse, the value is going to become 1, and now we need to move 3 steps. So 3 steps means 2 accelerations, so we can do 2 accelerations. What is the cost of this one? The cost of this is 1 2 3 4 5 6 7 8. So in total it took us 8 steps to get here. Still have one more possibility, and that possibility is that we need to find the target value to be 9, and we have this 15. So let's see that how much effort it takes for us to get there. Okay, now currently we are at this position number 4, and currently we have 4 A's. Now we need to change the direction, so we hit a reverse, and now the distance we need to cover is 6. From the previous example, we already know that if we want to cover 6 direction, basically we need 5 steps. I'm not going to go in detail on showing all 5 steps, but that is how many number of steps we need. So let's see that what would be the effort in this case, because previously the best we could find is 8, But in this case, the effort is these many steps plus 5 steps. And notice we only have to use a single R over here, because once we change the direction, we don't need to change the direction again, because it's in our favor to keep the same direction. In this case, the answer is actually going to become 10 steps. So again, 8 is going to be the best number of steps we can do in order to find the target, what are the minimum values needed for target value number 9. And in this case, we are going to mark 8 as the answer. Let's do a quick recap on all the things we did. So the number of things we did is, okay, this was the target value. We choose what is the minimum A that gets us and what is the next A that gets us. And then we try to make this distance by comparing all the possibilities. So over here, we actually went backwards and then we went frontwards. But we were able to do it pretty quickly because we had this DP array setup. If we see time and space complexity, in this case, the time complexity is actually going to be big O of n log n, and space complexity is actually going to be big O of log n. Now, why we are dealing with a logarithmic time complexity? Because remember, with every single jump, we are actually jumping in 2 to the power of n. So we are eliminating lot of values with every single jump. And this is a very good time and space complexity. So I hope you would have liked this explanation. Now let's move on to the coding. So before we start implementing the racecar function, we are actually going to create a helper method. So let's initialize our recursive helper method. So after initializing our helper method, we are going to check for a condition that if the given value inside the dynamic programming array, if that is greater than or equal to 0, we are simply going to mark it as our successful case. If that is not the case, we are going to assign the current value of dp to be the maximum value possible. Now let's initialize our couple of variables. So first we are initializing our variable x, and that is going to be of the value 1. And we are also going to initialize a value called j, and that is going to help us to iterate over the smaller distance. Okay, now we are going to run our for loop, and inside the for loop we are going to utilize the function of like 2 to the power of x minus 1, and basically we are going to keep updating the value of j until we come to a position where we are just before the target value. And after doing that, inside we are also going to initialize a for loop to find the smallest distance between the two values. So all we will have to do is every single time we are going to calculate the value of dp of I, and for that we are going to compare that what is the minimum cost that is happening for us. So we are going to compare the value of the dp of I that we have already stored, or we are also going to compare the value of the given number of steps we need to take, so number of x, plus we will also have to add one more value, that is to take care of one reverse function, and we will also have to add one more value, that is to take care of the another reverse function, and we will also have to take care of the number of queues that we need to jump, and plus we will also have to call the recursive function and see how many steps does that takes in order for us to get there. So over here we are going to provide the value of the target minus the number of j minus p that we received. So this is the jump that we take, and we are also going to provide our dp array that we have created. And basically this is the whole logic behind our solution. And once that is done, basically we can get out of the loop, and now we can compare again the smallest result possible. So for this scenario, what we are going to do is we are actually going to again compare the two values, and inside the two values, first value is going to be the existing dp of I value that we have received from running this loop, and second value we are going to compare it is going to be this second scenario takes care where we are actually jumping one step above the given values, and in the end we simply need to return the smallest number that we have been able to find from our main function. We will have to make call to this one, and we will also have to initialize our dp array, also going to fill the value with all the negative values except the first one. And now we are going to call our function,
Okay, seems like our solution is working as expected. I put I in place of target at many places, so I just fixed that. And now let's try to submit the code. Okay, seems like our solution is working as expected, and it is reasonably faster than a lot of other solutions. And I know this was a very tough problem to understand. I hope you had a good chance to understand the explanation and also go through the code couple of times. I'm going to post this in the comments, and I also have my own GitHub repository where I have solved like a lot of different problems, and I'm going to put the code here as well. So it's up to you wherever you want to check the code from. uh, I hope you like the explanation. Now the next problem we are solving is called longest increasing subsequence. This problem actually has two optimal solutions. First optimal solution is a dynamic programming solution that can solve the problem in big O of n square time, and which I'm explaining in the first part of this video. Now for the same problem there is an even better solution which is very tough to understand, and that is something that is using a patient sort algorithm. So the thing is, if you are only considering and trying to learn dynamic programming, I think part one of the solution should be fine. If you also wants to learn the optimal approach for the same problem, you can also see the part two of the same question. So there are going to be two solutions for the same problem, and now let's start understanding the problem statement. Hello friends, we are still not employed by a FANG company, so let's not stop lead coding till we get there. Today we are going to do a very important lead code medium problem, longest increasing subsequence. And I have decided to break this video in two parts. In the first part, I'm going to discuss the brute force solution and an accepted solution for this problem. And in the second part, I'm going to show the optimal solution. But the thing is, the optimal solution is really difficult to achieve, and it's a little bit tricky to come up with. So let's understand the problem statement. Basically, we are given an array of numbers and we need to find the length of longest strictly increasing subsequence. So subsequence means that suppose we are given an input like this, 1 2 4 5. So we can say that the value 2 and 5 is actually a subsequence of this given initial problem. Let's try to understand that what is the input given. So we are given over here an 18, and this example, and if we take these numbers 2 3 7 and 101, this would be our longest increasing subsequence. So if we get rid of this value 5, this would be the longest subsequence we can make, where all the values are in increasing order, and the length of all the values would be 4, which is what we need to return as a part of this output. So once we know the problem statement, let's see that what could be the brute force approach. So in the brute force approach, we are simply going to take every single subsequence that we can possibly make, keep a parameter that tracks the length of any subsequence, and eventually at the end we should be able to find a subsequence with the maximum length. So let's take a small example and see that what are the possible subsequences we can make. So suppose our given input is 5, 3 and 8. I'm only taking 3 elements because I need to show that why this approach is bad and what are the possible subsequences we can make out of this. So let's start making all the possible subsequences. The possible subsequence would be 5, 5, 3, 5, 8, 3, 3, 8, 8 and 5, 3, 8. These are the possible subsequences we can make out of only these given three problems. And if we check the length of each of them, and if we find out the property that which one is a strictly increasing order, we found that this is the strictly increasing order and the maximum length we can achieve is 2. So this solution works, it works fine. The problem is that notice that we are only given 3 elements over here, and based on this 3 elements we were able to make almost 7 subsequences. Mathematically it's actually 2 to the power of 3 minus 1, and for any single given n, this is the number of subsequences we can make. So suppose we are given n values in the given input, the number of subsequences we would be able to make would be 2 to the power of n minus 1. So if we calculate the time complexity, we can just say that the time complexity is actually big O of 2 to the power of n, which is extremely horrendous time complexity, and this is exponential. So even with enough numbers, even NASA won't be able to solve this one. So let's move on to the next approach. Now we want to find the better approach, and we know that the way to do is to use dynamic programming. The thing is, how can we identify that we need to find the solution using dynamic programming? Also, what dynamic programming solution are we going to use? So I'll be discussing both the things in next portion. And first of all, let's take an example. We'll try to see how we are going to solve it. Then I'll show you how we can determine that we are using the dynamic programming, and after that we would be implying the result, and I would be showing you the coding example. Suppose our given input is, suppose this is the input given, and we need to find the longest increasing substring. So just by looking at the given example, we can determine that the longest increasing substring actually exists between 7, 8, 16 and 27. And now let's see that how can we come up with this solution. How do we determine that this is dynamic programming? Suppose we are just given an example like this. We are just given one value, that let's say the value is 7. If we are only given 7, what is the longest increasing substring we can make? Well, the answer is quite simple. We can simply make just one substring of length 1. So this actually becomes our base case, that if we are only given one value, we are guaranteed to have at least one substring that would be the longest increasing substring that we can make. So now let's see that how can we use this logic. Say that for all the given elements, basically there exists one substring at least that is the longest increasing substring. Let's just mark all the values as 1. We know that if we are only given the value 10, the longest increasing substring we can make would only be 1. But when it comes to the second value, now we have something to compare to. Suppose the 7 value, if this was greater than 10 and we only had 2 values, we can say that at the second position, the longest increasing substring that we would be able to make would actually be whatever we have made so far plus 1. So we would have been made 2, but over here that's not the case, and over here the value 7 is actually less than whatever we are given the value before that, which means that the longest substring we have at the value 7 would also be 1. So this would be true in this case. But now when we come to 8, we have two possibilities. What are the total substrings we can make up until this point, up until 8? Okay, so for this value 8, what is the one thing that we can determine? We can basically determine that there are 3 possibilities of the substrings we can have and we can compute. One possibility is we could have a substring like 10 and 8. Second one is we could have substring 7 and 8, and third one is we could have a substring 8 by itself in case if all the values before 8 are actually greater than 8. So in this scenario, from 10 to 8, we know that 10 is already greater than 8, so we cannot create a substring over here. So let's ignore this scenario. For the second scenario, 7 to 8, actually this is a valid increasing substring because 7 is less than 8 and it comes after it. So what we can determine is that the longest increasing substring we can make at value number 8 would be whatever the longest increasing substring we have made up until this point. So whatever the longest increasing substring we have made for the value number 7 plus 1, because 8 is coming after 7 and 8 is just one step after it. So we can say that longest increasing substring at value number 8 would actually be whatever we have found up until longest for the longest increasing substring of 7 plus 1. And this is how we can determine that this should be solved as a dynamic programming problem, because in dynamic programming, basically whatever calculations we make in the past, we keep track of them in some way, either through an array or storing them in variable somehow, and based on those results we actually use it in upcoming future calculations, so that we don't have to calculate everything from the scratch. So this is one way we can determine that this problem should be solved using dynamic programming, because if we just look at the problem, we understand that we need to find the longest increasing substring, which means that we need to keep track of whatever we have calculated so far in the past, and using those results we would make decisions that whether we want to keep this current value or we want to ignore this current value. So this is a very important thing to keep in mind, and this is basically the core concept of finding the pattern whenever you are given that whether the problem is dynamic problem or dynamic programming problem or not. Because in the interviewer is not going to tell you that hey, this is a dynamic programming problem and just go and solve in that manner. So now let's again continue with our example. So we can determine that currently the value at 8, the longest increasing substring we could make at value number 8 is 1, but we just found that from 7 to 8 we can actually make a substring as well. So this bit would become actually 2, and we can say that up until the point of 8 the longest increasing substring we can make is actually 2 and not 1. Now let's move forward. Now let's consider for value number 5. At value number 5, let's again compare from 10 to 5. We cannot do anything because 10 is already greater than 5, so there is no point of doing this conversation. Let's compare 7 to 5. From 7 to 5 we cannot do anything because 7 is greater than 5 and also 8 is greater than 5. So at value number 5 there are no values that are less than 5, so at value number 5 the longest increasing substring we can make is actually size 1, because there does not exist a smaller number before 5 in our given input. So we'll keep this 1 as it is because we have already made all the calculations. Now let's calculate for this value number 16. And actually for value number 16, if you notice that all the values are smaller, so this would be a very good point for us to understand that how everything works. So from 10 to 16 we notice that 10 is smaller than 16, so there is a possibility. And basically we can say that whatever the longest increasing substring we have found at 10, if we do it plus 1, that would become 16. So the longest increasing substring for 10 we have found is actually 1, so 1 plus 1 equals to 2. So let's just update the value 2 over here, and now let's move on with our calculation. So we are done with this 10. Let's calculate with 7. So if we do 7 to 16, actually again we will do 1 plus 1 because LIS of 7. So 1 plus 1 is again 2. We already have 2, so there is no point in updating the value. Let's ignore this. Let's do again with the value 8. So from 8 to 16 we know that the value of 8 is actually 2. So over here at value number 16 we can say that increasing substring at value number 8 plus 1, so it becomes 2 plus 1, and 2 plus 1, okay, I made a mistake. I think this is 1 that represents 5, and the value for 16 is actually over here, so I'll just write it down. So LIS of 8 plus 1 is actually 2 plus 1, which is 3, which is greater than whatever the longest increasing substring we have so far. So which means we can update this value. So over here the longest we have found so far is actually 3, and now we can also create one more substring from 5 to 16. If we calculate from 5 to 16, we found that the value is actually 1 plus 1 would be 2, which is not greater than whatever we have at 16. So we can say that up until this point 16, the longest substring out of all of these values we can make is actually 3 for the values up until the point of 16. And let's move forward with our calculation. So again, the next value is 27. 27 is greater than all the other values. So if we do 10 plus 20, 10 to 27, we would find the value as 2. We'll do 7 to 27, we will find the value as 1 plus 1, again 2. We will do 8 to 27, we would find the value 2 plus 1 as 3. Again we will do 5 to 27, the value we would find would be 2. And at the end we would do 16 to 27, and we know that the value at 16 is 3, so we would be able to find the value as 3 plus 1. And because we have calculated all these results, we don't have to do calculations all the way from beginning, and we are just able to use the results we have stored so far. So we know that the maximum value we can find is 3 plus 1. So we would update the value at longest increasing substring at value number 27 to 4. And then we come to our last value, 9. So, and again we will do the whole thing for 9. So 10 is greater than 9, so we cannot do anything. 7 is less than 9, so we can for this one we can have the value as 2. 8 is also less than 9, so from 8 to 9 value we can have would be 3. 5 is also less than 9, so from 5 to 9 the value we would have would be 1 plus 2, 2. From 16 to 9 we cannot do anything because 16 is greater than 9, and from 27 to 9 we cannot do anything because 27 is definitely greater than 9, which means that the maximum value we could have find so far over here for 9 is actually 3, and that comes from the 8 plus 1. So we will update the value over here as 3. And now we just need to find that what is the maximum value we have found in this array that we have created based on the calculation. So basically clearly we can see that this value 4 is the maximum value we have found, and that would be our answer. That is what we would be returning as longest increasing substring. The thing is, we actually don't need to iterate over the entire array again. We could have actually done this when we are calculating, or when we are making this array. We could have just keep track of one parameter called max, and we would compare it with whatever the value we calculate at each location. So whenever we find a new maximum value, we'll just store it in this value, and at the end of our loop, in this max parameter should have our final solution, and we can definitely return this, and this solution would work perfectly fine. Now let's calculate the time complexity. So basically the time complexity for this one would be big O of n square, and it's pretty simple to understand that, because for every single element we are basically taking all the elements before that and comparing it with whatever the element we have. We did the same for every single element. So for n element n, we might have to compare it with n minus 1 values, so the time complexity becomes big O of n square. And if we calculate the space complexity is also big O of n, because we need to create this additional array to store all the values. And this is a good time complexity and good space complexity compared to our brute force approach. Remember our brute force approach, the value we had was actually 2 to the power of n, which was way higher. This was almost exponential time complexity, and we have done significant improvements from this one, and we have actually moved to n square. So this solution would work perfectly fine in any interview. And I'll move on to coding, but the thing is, I would be making another video to explain that how can we solve the same problem using n log n complexity. And this is actually pretty ideal, and if you can achieve this in any interview, if you can come up with this time complexity right then and there in an interview, you can be guaranteed that you would be placed in any company you want. So let's move on to coding now. So first of all, we will create a new array called lis, and we would create the array of size, whatever the size we are given for the input nums. and we will initialize the array with value 1. We will also create a parameter called max that will keep track of the maximum longest increasing subsequence inside the loop, and we will initialize the value as 1. So now let's create our two loops. So first of all, we will create a loop that is starting at position number 1, not 0, because we need something to compare to, otherwise all the values would be just 1 before that. And we will run it till the length of the given array. Well, now this would be our inner loop, and we would start it from position 0, and we will run it all the way up to the position I. Now inside the loop, first we need to determine that whether our current I that is on the right side of the array is actually is actually greater value than whatever our j is. If that is the case, then only we would move forward with the calculation. So if I is greater than j, now we will do our calculation for the dynamic programming. So the value of I would actually be the maximum value we can achieve for whatever LIS of I we already have, or 1 plus whatever LIS of j we have achieved. And this would be our recurrence relation. I guess that is what it is called in dynamic programming. So this is just to keep in mind that yeah, if you mention that this is the recurrence relation, it sounds really good impression. It sounds cool as well. And also we check that whether the current LIS value is our max or not. So we'll just check the existing max value with the new LIS that we just created. And yeah, I think that's pretty much it. After this loop runs, we can simply return whatever we have found for the value max, and this should be our answer. Let's try to run the code. I think we made some silly mistake. Yeah, yeah, looks like our code is working. Let's try to submit it, and our submission works. But if you notice that our submission is not actually the best submission, it's only faster than 55.54% of the online submissions, and that is because our this solution is actually work in big O of n square time, so n to the power 2. But there is another solution that actually runs in big O of n log n time, and I would be creating a new video explaining that solution. And this is actually a pretty interesting solution. It's actually a sorting algorithm that we are going to use to achieve this. So hope you like the video. Let me know what do you think, and if you have any suggestions, just feel free to reach out to me. Our goal is to get employed in any FANG company, and until we get there, we are not gonna stop. So hope you like it. Thank you.
So basically the previously when I solved this problem, I mentioned in that video that I was solving it in big O of n square time, and this would be perfectly good and reasonable to expect from any candidate in an interview. But the thing is, if you want to be an exceptional candidate, if you want to make sure that you don't leave any gaps in your FANG journey and your so you need to know these things. So that's why I'm creating this video, and in this video we are going to solve this problem in actually big O of n log n time. And the way we are going to do is something called as patience sort. So let's take our custom example,
And as I have mentioned previously, that it is very important to make custom examples, because using those custom examples you can determine that you have the ability to think and make sure that how can you create your own test cases. So this is our example, and it's quite a long one, but the thing is I need to make sure that I go through all the possible aspects in the given example, and that's why I took so many integers, so it becomes absolutely clear in your mind that how we are going to achieve it. So basically, at any given location we can either have a null string, so a subsequence that has no entries, a subsequence that has just one entry, a subsequence that has two entries, so this is null, one entry, two entries, subsequence that has three entries, subsequence that has four entries, and so on. So, and our aim is to find out a longest increasing subsequence that we can achieve. So for this one we are going to use couple of arrays. We are going to put them in a different manner, and as you would have guessed that because the time complexity we get is actually n log n, somehow we are going to use binary sort over here. So uh, let's start the problem. First of all, we are going to create two arrays. First array is to keep track of the longest increasing subsequence that we have found, so whether it's value 1, of value 2, of value 3, whatnot. And second thing is we are going to store the last digit for any given longest increasing subsequence. So what I mean by this last digit is that suppose we find a an increasing subsequence over here, that the values 5, 16 and 27 is an increasing subsequence. So in the longest increasing subsequence array we are going to note an entry as 3, where because the length of values are 3, and the last entry we have in this subsequence is 27, and the combination of these two is going to allow us to create some pretty interesting things. So let me go over the example, and I would be explaining every single time what we are doing and how we are finding it, and at the end I'm going to show you that what could be the intuition behind this. So at first location 10, basically we don't have any substring so far. So the current substring we have found up until this point 10 is just a single value 10, and in this single value 10 in our LIS we can create an entry like 1, and the last digit we have for this entry 1 is 10. So we are good so far. Now let's move on to the next one. Now next entry is currently we only have a substring 10. Next entry we have is 7. Now we cannot create an increasing subsequence just by these two pairs, because obviously 10 is greater than 7. But the thing is we can replace this 10 with this 7, and how we can replace it is because up until this point 10 is a substring of length 1 and 7 is also a substring of length 1, so both of us are just same. But the thing is, whenever we move forward, all the values that are greater than 10 will also be greater than 7, which means that suppose we have value over here 11, 15, 18, something like this, and if we take it with 10 we would be able to create a longest increasing substring like 10, 11, 15, 18. But the thing is, same thing can be done for 7 as well, so it makes no difference that which entry we keep. But if we have a value that is between 7 and 10, 10 won't be able to do anything in that case. Suppose we have an entry like 8, 9, 11. So in this case, if we would have just considered 10, the longest substring we would be able to make is 10 to 11. That's it. But from 7, we can actually make 7 to 8, 8 to 9, and 9 to 11. This would be of size 4 and this would be only of size 2. So it is in our interest to keep 7 as our longest increasing substring and not 10, because value of 7 is actually less than it. So we will replace this 10 in this array we have created. So currently the last element we have becomes 7, and this 7 is also of just length 1. So we have only kept this one entry, and we have basically just discarded it. We have went over it and we didn't find anything good. Now at this point we only have a substring of 7. Now comes the value 8. Now 8 is greater than 7, and 8 is in itself a higher value. So we have two possibilities. Either we can keep 7 as it is as a longest increasing subsequence, or we can have a subsequence like 7 and 8, and we are not appending 8 behind this 7. We are creating that the longest increasing subsequence we have so far of value of size 1 is still 7, but this one is, we are creating a new subsequence that is of size 2, and we are appending this 7 behind 8. So which means we would be creating a new entry over here in our longest increasing subsequence of value 2, and the last element of this value is actually 8. But the thing is, meanwhile the first element is still 7, because we only, up until this point, if we consider a substring that is of only value that is to be only of size 1, the best element to choose for size 1 would be 7, because it is the smallest. And this is the main logic behind the patient sort. So let's move on to the next element. Again we go to value 5 now, and the substrings we have so far are 7, 7 and 8, and now we have this 5. So we cannot append this 5 over here, we cannot do anything with this. But the thing is, if we consider these 4 elements, and if we consider the substring of size 1, 5 would be the most ideal candidate and not 7, because 5 is actually less than 7. So it is in our interest to replace this entry 7 with the entry 5, and we will update in our array with entry 5. Let's clean this up a bit. Now due to space constraints, we are going to write down our subsequences over here. So far we have found 2 subsequences. One is just 5, that is of size 1, and second one is 7 and 8 that we have stored over here, and we are keeping track of the last digit that we have appended. Again let's consider 16. So now for this 16, and if we consider the last 2 elements, 16 is definitely greater than 5, but there is no point in appending 16 at 5. It is in our best interest to append 16 behind this 8. So our algorithm is basically, what we are doing is, we are taking the value from the input, we are checking in our last array to see that what is the best position to fit that value, and the best position to fit that value is to keep the increasing order intact, because notice that previously the value we had was 7 and 8, that was increasing order. Now the value we have is 5 and 8, that is also increasing order, and now the next value 16 comes. We can actually append it behind 8. So after 8 we can create a new entry, and we would do that. So we would create a new entry called 3, and why we were able to do a new entry is because this 7 and 8, we are not going to replace 8 by 16. We are actually going to leverage this 7 and 8 because they are already a subsequence, and our aim is to find the longest increasing subsequence. So why would we replace 8 with 16? It's actually in our favor to keep this 7 and 8 and create a new subsequence 7, 8 and 16, so that we can use, because suppose if all the values that come after 16 are like 9, 10, 11, 12, 13. And if we have created a subsequence called uh, 7 and 16, so these all values we would not be able to consider them as our longest increasing subsequence because we don't have this 8. But if we have this 7 and 8 over here, and if these values comes after 16 and we have created a separate entry like this one, 7, 8 and 16, so this is separate in itself, we can actually append all these 9, 10, 11, 12, 13 values behind this 7 and 8, and this would be our longest increasing subsequence. So I hope that this makes things more clear that why we are choosing to have a new 7, 8 and 16 as substring, and we would create a new entry in our array as well. So now these are the three substrings we have. Next value is 27. So 27 is again greater than this 16. So now we are going to create a new entry 7, 8, 16 and 27, and we are going to have a new entry in our LIS with value number 4, and we are going to add the last digit as 27 over here. I hope that what I'm doing is understandable, that why we are actually creating this new entry from the given input. The next value we have is 9. So let's see that where is the best place we can fit this 9. The best place we can fit this 9 is actually after 7 and 8. So like this 9. The thing is, we are not going to replace this 7 and 8 with 9, because up until this point, up until 9, if we see the best pair with 2 entries only, that with the least value is actually 7 and 8. There are multiple pairs that create the that are uh, creating the longest increasing subsequence of length 2, like 5 and 16, 16 and 27, 5 and 27. The thing is, they're all greater values. If we see the last element over here, 7 and 8, the last element is the perfect fit. So that is why we are going to keep the 7 and 8, and we would be creating a new entry at this place. So we are going to replace the 16 with value number 9. So let's update this in our array as well. So for the value 3, the best we can find is 9, and that would be the subsequence 7, 8 and 9. So far we are keeping track of all the subsequences that we have found with the values 1, 2, 3 and 4, and we are also keeping track of the last digit that we have calculated so far. And because all the values are in an increasing order, it becomes very easy for us that whenever we find any new value like this, it becomes pretty easy for us that where we are going to add it in this array, and which value we are going to update it. So this is the main logic behind patient sort. Now the next value is value number 1. So where in this array we can store value number 1? It's pretty simple. We can only store it at position 1. No other position we can store. And based on this, we can say that up until this point, if we only have to create a subsequence of length 1, it would be the most ideal to have the last digit as 1, because all the values after that would actually be in an increasing order, and we can replace this 5. In our list of subsequence, we will have entry 1 over here. Now let's consider this value number 13, where over here we can add this value number 13 so that it would give us the most value. And actually we should not be replacing this 9 with value number 13, because we are not trying to achieve a substring like this. Rather than having 7, 8 and 9, we are not trying to get 7, 8 and 13, because that is not in our favor. Because notice that this is already existing and 13 can be appended next to it. So what we can do is, actually we can replace this 4, what the subsequence with 4 entries, with this 7, 8, 9 and 13. So our new subsequence would become 7, 8, 9 and the 7, 8, 9 and 13. And why we are able to replace the 7, 8, 9 and 13 with previously 7, 8, 16 and 27? The reason is quite simple, because both generate the value 4, so that is okay. But the thing is, with this 9 and 13 we have higher odds of making longest increasing subsequences for the upcoming values, and which we are going to see right for with the next value. So we will update the value 13 over here, and so far these are the 4 subsequences we have. Now the next value is actually 15, and imagine that if we had kept this value as the substring of 4 values, we won't be able to insert 15 over here, because though both of these were same, 15 is easier to be appended over here, but it cannot be appended over here. So that is why in the previous step we actually replaced this value 4 with 13. So I hope this makes it more understandable. Now let's see that what we can do for this value number 15. So the logic is quite simple. We are simply going to append this value number 15 behind this 13. So the new substring, and we are going to keep the value number 7, 8, 9 and 13 as a 4 substring, as a substring of length 4, and we are going to create a new substring 7, 8, 9, 13 and 15, and this would be a new entry in our array. So we will have a substring of length 5, and the last digit for that would actually be 15, and this would be the end of our array. And since we have reached to the end, we just need to iterate over this one and find out that what is the biggest length we were able to find, and we just simply return this value. So this is as simple as it can be. And why we are able to achieve it? Because at every single location, for every single element, we are trying to see that where we can fit that element that best represents that position, and based on it we were keeping track of the longest increasing subsequence. So basically we were intellectually choosing our own longest increasing subsequence, and we are also keeping track of whatever we have calculated in the past. Because if we were to choose a value of 3, that what is the longest increasing subsequence up to the point of 3, we can easily say that hey, it's this one, and the last digit is actually 9. So if we find some better digit, it becomes pretty easy for us to calculate that where we are going to append that value. And I hope this makes things more understandable. Now let's calculate the time and space complexity for this one, and it's pretty simple, that at any given location we are iterating over the entire array, and for any single position we are checking that where we can store that position in this given new array that we are trying to create. But the thing is, this new array is already sorted, so because it is sorted, we can actually achieve that in log n time, and initially we have to iterate over this entire actual input once, so that will take n time. So basically we are calculating this whole approach in big O of n log n time, which is a very good time complexity. Because if you remember correctly, originally for the brute force approach, our time complexity was 2 to the power of n. For the second accepted approach that I completed in last video, our time complexity is actually n square. The thing is, n log n, this is a thing of beauty. Now let's move on to coding. And if you still don't understand the concept, I again ask you kindly to go over this example again, because if you can master this, sky's the limit for you. So let's do the coding now. Let's create a new array list. We can start by adding the first element, because the first element would actually be the first list of size 1. And and then we will initialize our loop to iterate over the entire input array, and again we will start the loop from second position, I equal to 1. Inside the loop we need to find that whether the given number is it actually greater than whatever the last value we have in this subsequence. If it is, we need to append it to the subsequence. So and we can just add it to the subsequence. If not, we'll need to run the binary search. So and over here we can just create a new function to run our binary search, and in input we will provide the substring and current ith value we have. And now let's create method for that. Inside the loop, first of all, we'll create a left and right variable. So left would be of size 0 and right would be of whatever the size we have for the integer for the given input substring. Now we will just run a condition that while left is less than right, we are going to calculate the mid pointer, and then if the mid pointer is already existing, we simply return that value. If not, we either move on the left side or right side. So we'll do left is equal to mid plus 1, else we can simply do right is equal to mid, and after the loop we can return the value of left. Now over here in the J we are receiving whatever the value of left we got, so we add the subset to our existing subsequence. That should be the logic. So after the return we after the end of the loop we just need to return the size of the list, and this should provide the longest increasing subsequence. Let's try to run this code. Looks like we put the values out of order. Yeah, looks like our solution is working. Let's try to submit it. And yeah, see, our solution is actually faster than a lot of other submissions, and that is because our runtime is actually n log n. And I'll be posting this solution in the comments, and I hope you like the video. Thank you. Hello friends, we are still not employed by a fine company, so let's not stop lead coding till we get there. Today we are going to do longest palindromic substring lead code problem, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like Amazon, Microsoft, Google, Adobe, Apple, Bloomberg, Goldman Sachs, TikTok, Uber, ByteDance, LinkedIn, Tesla, and eBay. So that's why I'm paying my utmost attention. I hope you also enjoy the video. This is a lead code medium problem and also one of the very well liked problems on lead code. Basically, we are given a string s and we need to return the longest palindromic substring that is present inside this original given string s. So in order to understand this problem, first of all, we'll have to identify that what is a palindromic string. And a palindromic string is basically, as the name suggests, any string that forms a palindrome. And we know that palindrome is any string where if you read it from left to right or right to left, the number of sequencing is same. So in this case, ABA is actually an example of a palindromic string. Also ABBA is also an example of palindromic string, because in either of these two cases, whatever side you decide to move along, the number of character occurrences remains the same. So that's why they are palindrome. And now our aim is to find the longest palindromic substring inside this given original string s. This is not a very good example to understand, so let me create a custom example. In this case, we need to find that what is the longest palindromic substring. So if we see the string s by itself, it's actually not a palindrome. But if we see these three values a, b, a, and we get rid of this b and d, we can actually create a palindrome, which means in this case, we can return the answer as a, b, a to be longest palindromic substring that is present inside this given string s, and this is exactly what we need to return. So now let's see that what would be the different approaches to solve this problem. In order to understand the brute force way, we'll have to identify that what is the thing we need. We need the longest palindromic substring that is present inside this original given string s. So the aim is that we need to find a substring. So why don't we just use the brute force method and we find every single possible substring that we can make out of this given example s. So we can make bunch of different substrings. Let me just draw some substrings over here. So these are some of the substrings that we are able to generate from this original given string s. Now our aim is to find that what is the palindromic substring. If the substring is palindromic, we will find its length and then we will try to find the longest palindromic substring in that way. So we can clearly see that in this case, this ABA is going to be the answer for this longest palindromic substring, and eventually we would be able to find the solution using the brute force method. But what is the issue with this? Like, issue is actually pretty evident that even for this 4-character string, we actually had to create bunch of different substrings, and out of all of those substrings, we will have to find some effort and resources to find that what is the longest palindromic substring. So that is just waste of time and energy. If we see the time complexity, in this case, the time complexity is actually going to be big O of n cube. Why m cube? Because it takes n square time just to create these substrings, and after doing that, we will also have to identify that whether those given strings are actually palindromic substrings or not, and which is the longest amongst all of them. So that also takes n time. So that's why the overall we can write it as big O of n cube time complexity. So let's see that what would be the better approach to solve this problem. Well, before we come to the optimal solution, first let's build some intuition behind achieving that optimal solution. The idea is that we need to find the longest palindromic substring. Now there are two possibilities. We could have an odd number of string that is a palindrome, or we could have an even number of string that is actually a palindrome. Now in each cases, the middle value is actually providing some interesting results, and the thing is that in both the cases, the palindromes are actually built around these middle values. How? Let me quickly show it to you. Well, if we just take this madam for an example, over here we can actually conclude this D to be a substring in its own, and because this is a single character substring, we can actually conclude this to be a palindrome as well, because if we read from this left direction or right direction, in each cases we are going to get the same result. Now if we add these two A's to this D, we will also get the substring that looks like this A, D, A. Now in each cases, this D remains common, but the left value and the right value, because they both are same, we can conclude this string to be a palindrome as well. Now again, if we repeat the same process and we add this M and M, again because they both are same and we are adding at the corners, so if we add them, we will get a value that looks like this. Now this D originally was a palindrome. After adding this AA, it remained palindrome because both character had the same value. And again after adding this MM, again the whole thing remained the palindrome because they both had the same value. Now in this case, if I extend and if I add a value that looks like X and Y over here, so this X and Y is actually not same. So this whole thing will not be a palindrome, but this middle portion will actually be a palindrome. And in this case, because we had odd number of characters that are forming a character, we actually have just one value that we can consider as middle value, and all the other values from this middle value are actually just a bunch of set of characters who both have same values. Let's take an example for this even number case. Now in this case, actually we have two middle values, and the two middle values are BB. Now if we were to consider this BB, this is actually a palindrome in itself, because again by definition, even if we go from left or right, in each cases we are reading the same value. Now again, this A both are same value, and they are actually same value that corners our original given middle values. So if we form a value that looks like this BB was already a palindrome, and the two values we added, they are also same. So because they are same, this whole thing actually becomes a palindrome. And again, just like this case, if we add an X and Y over here, this whole thing will not be a palindrome, only this ABBA would remain palindrome. So now after knowing this solution, actually it becomes really easy for us to identify that what would be the optimal solution. Suppose this is the example that we are given, and we are trying to find the optimal solution for that. So what we are going to do is we are actually going to expand on the corners, and we are trying to see that whether the left and right value of any middle value, if they are actually same or not. If they are same, we can consider the whole part to be part of any palindrome. If they are not same, then we will move on to the next value and start doing the same process. Now there could be two possibilities. We could have an odd length palindrome where we will only have one middle value, or we could have an even length palindrome where we will actually have two middle values. So in each cases we will have to take care of them. So I'll be showing you the odd example first, and then I'll show you the even example. And basically it's slightly different idea, and I'll just show you when we go there. So first of all, we are going to take this value X. Now we are going to expand upon the corners. So we are going to see that whether this X could be the middle of a longest palindromic substring. If that is the case, then we will expand upon this X. So we will try to see its left value and right value. The left value is actually null, and right value is actually M. Now this left and right, they are not same, and also this middle value is actually not same with this right value, and it's also not same with this left value, which means in each cases this X is actually not part of the middle of longest palindromic substring. So we will get rid of it, and we will move on to the next value. Now we are at this value number M. Again we try to see the what is the left and right value. Left is actually X, right is actually A. Again they both are not same, and none of them are same with this M. So which means that now we will move on to the next value. Next value is actually A. Again the left value is M, right value is D, nothing is same. So we will move on to the next value because this is also not a part of the palindrome. Now we are at this position number D. Now if we take the left and right value, the left value is actually A, and the right value is also actually A. So because this left and right value is same, this D could be a middle of any palindrome. We don't know if it is the longest palindromic substring or not. Now the longest palindromic substring that we have found so far is actually of length 1. Why length 1? Because any character in itself is also a palindrome, remember that. So that's why now we have this new substring that looks like this ABA. This is also a palindrome, and we will try to see that whether it is longer than whatever the existing palindrome we have, which is true that this ABA is actually longer. So we will have to update the value of this AB over here, saying that this is the longest palindrome we have found so far. We will keep on expanding on its corner. So far the values we have is ABA. Again we will move on a left and right pointer. So this is M, and this is also M. So because they both are same, again we can consider this to be a palindrome. And the previous longest palindromic substring we had was ABA, but this is actually greater than that. So we'll update its value, and now the longest palindromic substring we have found so far is Madam, MADAM. Now again we will go and repeat the same process. Over here we will have the value Y, and over here we will have the value X. So these two are not same. So because these two are not same, now we are no longer forming a palindrome. So we will have to get out of it. So we will just move on to the next value. And if we move on to the next value is actually A. So again this A, the left value is D and right value is M. So this is not a palindrome. We will go back to M. M is also not part of any middle of any palindrome, and this Y is also not part of any middle of the palindrome. So now we are done for our example so far. And in this case, whatever the answer we have found over here for the longest palindromic substring, which is MADAM, we will return this as our answer, and this solution would work as expected. Now this was the case of odd number of palindrome that is being the longest. Let's see the even number of palindrome. So in this case, again we are going to repeat the same process. First of all, we'll take this x, we take the left and right value. Again we don't find anything interesting, so we'll move on to the next value. Now next value is a. Again we check left and again we check right. We don't find anything, right? So we'll move on to the next value. Now again we are at this position number b. Now we are at this position number b. If we check the left value, we find a, but if we check the right value, we actually find another b. So because these two are same, actually the combination of these two b's could be the middle of the longest palindromic substring, and that is going to be true in this case. So we are going to expand on a little bit differently now. Now we are going to have this bb as the middle of the longest palindromic substring we have found so far, and we will repeat the same process. So we will try to find that whether what are the left and right values. So left value is a and right value is also a. So again this is a b b a, because these two are same, and this middle portion we are just consider it to be the middle. So this is also forming a palindrome, and the longest palindromic substring we had so far was only of length 1, and then when we found this bb, it become of length 2, and now we have this ABBA, so this is of length 4. So because this is of length 4, we will have to update the longest palindromic substring we have found so far to be ABBA. Now again we will repeat the same process. So if we again go left and right, this is actually x and this is y. So now these two are not same. Because these two are not same, so now we will just get out of it. We will again check with this a and y. We don't find any palindrome, and we would be done with this one. So in this case, we would return this ABBA as part of our answer, and that would be the final solution. So the time complexity in this case is actually going to be big O of n square. Now why n square? Because we will have to iterate over every single value to see that whether that is the middle of the longest palindromic substring or not. That takes n time, and if we will have to iterate over all the values on the left and right side to see that whether it's the longest palindromic substring or not, which means that in the worst case scenario, we might have to iterate over n square times to find the answer. In terms of space complexity, we might have to keep track of big O of n characters at any given moment, where n is the number of characters present inside the string. Now this is actually a much bigger improvement compared to our brute force approach, which had the time complexity of big O of n cube actually. And now let's move on to the coding. First of all, we are going to check some edge cases. If that is not the case, we are going to run a for loop across the given string. For the any value we are iterating over, we don't know that whether it is the middle of the longest palindromic substring of an even length or of an odd length. So at any given time, we are actually going to have two variables that call a function, where we are going to check that whether the odd length or even length palindromic substring, can it be the middle of any palindrome. And so first I'll create two variables and we'll name it as len1 and len2, and we are going to call a function called check palindrome. Inside this function, we are going to provide the value of given string s, current position of I, and we are considering this to be an odd length, so that's why we are considering I to be the middle element. Also, we are going to create a variable called length2. We are again going to call the check palindrome function. We are providing the value of string s, we are also providing the value of I, and we are also providing the value of I plus 1. Why plus 1? Because remember that in the even length palindrome, we actually have two middle entries, and that is how we are going to do it. And also we are going to have a variable called length, where we are going to keep track of the maximum length of palindrome we have found so far. Remember that amongst these len1 and len2, at any given moment, if we identify that there exists some valid palindrome and we have found the maximum value, we might have to update the value of the maximum variable. So we are going to check for that condition as well. For that, we actually need two pointers called left and right, and we are going to check that whether the given length we are getting, if that is greater than the left and right length we have already found so far. The thing is, we haven't declared these variables yet. So first of all, let me quickly declare these variables, and we are going to initialize their values as 0. We are going to update the value of the left pointer, and that will be decided based on the value of I. So we are going to do I minus whatever the value of current length we have found. We need to do it divide by 2. But thing is, we don't know that whether that length is odd or even. So we will subtract it by one value and then we will divide it by 2. So in any case, we will get the correct result for the left pointer. And for the right pointer, we are actually going to do I plus whatever the length we have found divided by 2. And this should give us left and right pointer to create the desired substring. And after we run out of the loop, we will simply return the substring. So now we are done with most of the logic in the main method. Now we'll just have to create this check palindrome method. So let's assign the value L and R for the ease of our use. Now we are going to run a while loop that until the point when we have a valid palindrome, we will keep on reducing the value of left and updating the value of right, and we will check that whether both values are same or not. We'll also take care of some edge cases. While the existing value is a valid palindrome, we will reduce the value of left pointer and we will update the value of right pointer. This while loop, we will return the whatever the length we have found so far. This should do it. Let's try to run this code. We will have to update the value of this right pointer by 1. Let's try to run the code again. Okay, seems like our solution is working. Let's submit the code. And our code works as expected. I would be posting this in the comments so you can check it out from there. Thank you. Hello friends, we are not employed by a fine company, so let's not stop lead coding till we get there. Today we are going to do palindromic substrings lead code problem, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like Facebook, Amazon, Twitter, Google, Microsoft, Uber, Goldman Sachs, Apple, Bloomberg and LinkedIn. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a lead code medium problem, and basically we are given a string s and we need to return the number of palindromic substrings that exist inside this given string s. Lucky for us, we are given the definition that what a palindrome is. Basically a palindrome is a string that reads the same from backwards and frontwards. So suppose we are given a string like this GG. If we read it from the backwards or frontwards, in both the cases the answer remains the same. Also one more example, ABA. This is also an example of palindrome because in either case we read it, the answer remains the same. Now a quick question for you guys, that whether this character B, is this an example of a palindrome or not? And the answer is yes, this is also a palindrome. Why? Because if we read it from the left and also read it from the right, we get the same result. But if we are given a string that looks like this AB, this is not a palindrome because if we read it from the left and from the right, the answer is not the same. So these are some of the examples of a palindrome. We are also given the definition of a substring, but I don't think that it is necessary to define. It is actually pretty trivial. Now let's try to understand this problem with an example. Suppose we are given a string S that looks like the CABA. Now in this case, we need to find that what are the number of palindromic substrings that exist. So we can clearly see that we have a palindromic substring that are these four characters are actually palindrome in itself, because as I mentioned earlier over here, that even a single character is also a palindrome in itself. So we already have four palindromic substrings so far. But if we notice over here, we also have one more palindrome, that is this ABA, and that is also a palindromic substrings, which means that in this case we need to return 5 as our answer, that we can actually make 5 palindromic substrings for this given string S, and this is what we need to return. So let's see that what would be the different approaches to solve this problem. Suppose this is the S we are given and we need to find that what would be the brute force solution for this problem. Well, we have to understand that we need to find all the existing palindromic substrings that are present inside this given string S, which means we need to find the substrings. So what we can do is we will make all the possible substrings that we can make from this given S, and then we will check that whether that substring is a palindrome or not, and simply we will get our desired answer. So if we see that in action, for this particular string, we can actually make substrings that looks like these. So these are all the substrings that we can make from this given string S. Now all we have to do is check that whether any given string is a palindrome or not, and in this case we will find that these 4 strings are palindromes, and also this string is a palindrome. All the other strings are not palindromes, and then in the end we can return 5 as the answer for this problem, and that would be a valid answer for this problem. But what is the issue with the brute force approach? Well, the issue with the brute force approach is that the time complexity in this case is actually going to be big O of n cube. Why n cube? Because it takes n square time just to make these substrings, and then it takes n time to check whether a substring is a palindrome or not. So cumulatively this is a very bad time complexity, and we will have to find a better approach. So before we move for the optimal solution, first of all we will have to build some intuition behind it, that how to identify a palindrome. Well, in the palindrome there could be two possibilities. The palindrome could be of odd length or it could be of even length. First let's see that what would be the scenario in the odd length. So suppose we are given this character O. This is a palindrome in itself. We have already identified that, because if we read it from left or right we get the same result, right? Now if I decide to add two more characters XOXX at the edges, this still remains the palindrome, which means that because both of these x's were same, and this middle value was a palindrome in itself, this whole thing actually became a palindrome. Again, if I take it even further, if I add two more characters BB, again this whole thing still remains a palindrome. And if I keep on adding same values, as long as they are same, this will always remain the palindrome. But the moment I add a value that likes A and B, now this whole thing is not a palindrome because these two values are different. But this portion is still a palindrome, and also the smaller portion still remains the palindrome, which means we can define that the palindromes are like an onion where the middle value remains the same, and because of the middle values, all the other subsequent values where the values are actually same, the palindromic property is sustained. Why I'm giving so much explanation for that is you will see it in the optimal solution. And in the odd cases we only have one value as the middle character, but inside the even character, suppose we are given a value like BB. So this is a palindrome in itself, and both values are same. Because both values are same, this is an even length and this is an even length palindrome. Now again I decide to add two more characters XX. Because they both are same, this still remains the palindrome. Again I add value AA, this is also a palindrome. But the moment I add a value that is different like X and Y, now this whole thing is not a palindrome, but this middle portion still remains a palindrome. So that is the important property, that in case of odd length we have a middle character of the palindrome that is a single character, and all the other characters has the same value. In case of the even length palindrome, we have two characters that are same. So that is important, two characters, they are both same, and then all the other characters, they are also same as well, and a smaller palindrome is forming a larger palindrome. And let's see that how can we use this property to find an optimal solution. So suppose this is the example we are given, and we need to find the optimal solution for that. The idea is that at any given character, we are actually going to see that whether could this be a middle of any palindrome. And if it is the middle of the palindrome, we are going to keep on expanding our palindromic search, and we are going to keep adding our answer result. First of all, let's see for this character number C, that can this C be part of any middle of the palindromic substring or not. Well, we already know that this C is a substring in itself, because if we read it from left or right, we get the same result. And we are also going to have a variable called answer. So initial value was 0. Now because the C is a palindrome in itself, we are going to add the value to our answer as well. Now we are going to see that whether the C is a middle of the palindrome or not, which is not. Why? Because if we see the left of the string and right of the C, this is actually a null value and this is A, which means both are not same. So because both are not same, this is not part of any middle of the substring. Now we are going to have this value A. Again we are going to repeat the same process. Well, A is a palindrome in itself, so we are going to add the value to our answer first of all. So this becomes 2. Now again we are going to check that whether this A is the middle of any palindrome or not. We also have to check for both the cases that could this be of odd length palindrome or an even length palindrome. So for odd length palindrome, like the both left and right value would be same, and for even length palindrome the value would be same with that itself. So first of all we are going to check with this A. So the left value is C and right value is actually B. So both are not same. Also they are not same of this A and B, which means this is not an odd length palindrome and even length palindrome. So we are good to go. Now we will move on to the next value B. Now this next value B is a palindrome in itself, so we will update the value inside our answer to 3. After doing that, we are going to check that could this be the middle of any palindrome or not. So we will check the left and right value. Left value is A and right value is also A. So because these two are same, we can define that this B is actually part of the middle of the palindrome, which is of odd length, and we are going to keep on expanding our palindrome. So now this B A B, so sorry, now this A B A is also a palindrome, so we will update our answer immediately. So answer becomes 4 now. Now again we will keep on expanding our palindrome. So if we do a left and right over here, the left value is C and right value is actually null. So these two are not same. Because these two are not same, we no longer have a palindrome, so we will break out of the loop. Now again we still have one more character left to check. So again we will check for this value number A. So A is a palindrome in itself. We will put the answer as 5. Then again we will check that whether this A is that a middle of any palindromic string or not. So we check left and right value. Left value is B and right value is actually null, which means these two are not same and they're not same of this A as well. So immediately we will break out of the loop and we can return, and the next value over here is actually null, which means we don't have anything. We have reached to the end of the string. So this is the answer we need to return in this case, that the 5 would be the answer, and we will return that. Let's see one more example S, where we will find the even length palindrome. So over here again we are going to repeat the same process. So first of all we'll take this character number C. Can this C be part of any middle of the substring or not? So this is not part of any middle of the substring, and we will have an answer variable. So first of all we'll initialize it to 1 because C is a substring in itself. Now we'll move on to the next value A. So A, where A, if we check the left and right pointer, left is C and right is B. So these two are not same. So immediately A is also not the middle of any new palindrome, but it is a palindrome in itself. So again we will update the value to 2. Now again we are at this position number B. Now at this position number B, if we compare left and right values, so left value is A and right value is B. So these two are not same, but these two are actually same. So we can define this BB to be a middle of a palindrome, and this is the property we are going to use, right? And by the way, for this B, first of all we'll update the value to 3, and now we have this BB, that is a middle of the palindrome. Now immediately we will check the left and right value. So left value is A, right value is also A. Again these two are same, so this is also palindrome, so we'll update our answer again. So this becomes 4. Now again we will check the left and right value over here. So left value is C and right value is actually null. So in this case these two are not same. Because these two are not same, we will break out of the loop and we will say that okay, so far we have found something decent. So right now again we are at this position number B. Now remember that this becomes a little bit tricky, that it becomes easy for us to, if we check over here, this left value is actually B and right value is A. So again these two are same, but we should not fall for this trap because we have already concluded this BB to be a middle of the palindrome. So we will not consider this one, and this is also not a palindrome, which means that the answer we will only update by 1, and that this value by itself is a palindrome. And at the end we will check for this value number A, and A is a palindrome in itself, so we will update the value to be 6. But in the left and right there is nothing, so we won't do anything with that, and in the end we will return this answer 6 to be the final answer. And this is the solution we are going to use to find all the palindromic substrings inside any given string S. This is the final optimal solution. If we see the time and space complexity, in this case the time complexity is actually going to be big O of n square. Why n square? Because it takes us n time to iterate over all the values, and for any single value we might have to iterate over all the remaining values. So that takes n square time, but this is still a big improvement compared to our brute force approach, which had the n cube. If we see the space complexity, in this case the space complexity is actually going to be big O of n, because at any given point we might have to store all the values of n. First of all, we are going to initialize a variable called answer, and we are going to assign the value as 0. Now we are going to create a for loop and iterate over the given input. Now we have two possibilities. Any single character inside this given string S could be the middle value of any odd length palindrome or an even length palindrome. So we are actually going to make two calls to our check palindrome method, where we are going to return a value that whether this given string is a palindrome or not, and we are going to add that value to our answer variable. And inside this method we are going to pass the value of our string S, and we are also going to pass the character position of the middle variable. So the odd length palindrome would have the same middle value, so we will pass on that, and for even length we are going to pass two values. So over here we will pass I, and we will also pass I plus 1 to be the middle characters. Basically after we get out of this loop, we should have our answer ready, so we can simply return that. Now let's create this check palindrome method, and we will initialize a variable called count to count the number of palindromes we encounter. Now we are going to run a while loop, that while the left and right pointer are in bounds and not out of bounds, and while their character positions are same, so which means they satisfy to be the palindrome. If that is the case, we will keep on updating their values and we will keep on adding our count variable, and in the end we will return the count variable. So let me quickly type that. So this condition defines that whether this given string is a valid palindrome or not. If that is the case, we will decrement the value of our left pointer, we will increment the value of our right pointer, and we will increment the value of our count variable. And once that is done, once we get out of this loop, we simply need to return the count variable, and that's it. So let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty efficiently, and I would be posting this solution in the comments so you can check it out from there. Thank you.
Hello friends, we are still not employed by a FANG company, so let's not stop till we get there. Today we are going to solve a lead code medium problem, a maximum product of subarrays. Let's hear the problem statement. We are given an array of integers and we need to find a continuous non-empty subarray whose product or multiplication of all the values in the continuous non-empty subarray is the maximum value for the given input. Let's try to understand this with a given example. Over here we can see that we are given the values 2, 3, -2 and 4. If we see in the example, we can clearly see that the maximum subarray we can get is for the first two elements, and if we do the product of it, we get the value 6. Now we cannot do anything regarding the other two values because we see a 1 minus value here. So even if we were to do the multiplication of all these values, we would receive -12, and if we do something like this, we would receive -8. So because we have a negative value, the maximum we can get is 6. Let's understand what could be the brute force approach to solve this problem. Suppose we are given an input array like this, and if we take every single subarray like this and we start doing the product of all the elements in the subarray, and we keep a variable called max value, and we continuously keep on updating the max value variable, eventually we would find a subarray whose value would be maximum. And in this example, it would be the entire input as our subarray because all the values are positive. So whenever we keep on multiplying the next value, our maximum value will always go up, and the total would be 120 for this scenario. Let's see what are the issues we can find with this brute force approach. The time complexity for brute force approach would be big O of n square, because say we are given an input array like -1, 2, -3, 4. We need to do a subarray, again a subarray, again a subarray, and then we would eliminate the first value and we would start doing the subarray from again. So for all the n elements in an array, we have to iterate over them n times, and overall time complexity becomes big O of n square, which is really horrendous, and we should try to find a better approach. Let's see what could be the better approach we can take here. Suppose we are given this input array. Now, if we want to calculate that what is the maximum value we can get in terms of continuous product, we can do something where we would use dynamic programming, and we are going to keep the results of whatever the subarray we have already calculated. Now let me explain what I'm trying to say. For the first value, if we see, we only have 1, so the maximum product would be 1. For the first two values, the maximum product we can achieve is +2. Now for the first three elements, 1, 2 and 3, the maximum product we can achieve would still remain plus 2 because the third value we have is actually a negative value. So the multiplication of all these three elements would become minus 6. And because we have minus 6, we still consider 2 to be our maximum value that we can achieve up until now. And when we try to go for the next value, we see that the next value is minus 4. And only keep our if we only keep multiplying with the maximum possible value we can find up until now, this is what we would try to do. We would try to see that, hey, until the first three elements, the maximum subarray I can find is 2. Let me try to multiply 2 by minus 4, and we would get a result of minus 8, which is again not a very good solution. Again, the value is low, so the maximum value we can find is still 2. But we are missing a key point here, that if we take this as minus 3, and if we see that what was the minimum value up until first three elements, we find that the minimum value is actually minus 6. And if we multiply minus 6 with minus 4, we actually get a result of plus 24, which is much higher than our current max product we had, which was 2. Let me clean this up a little bit and let me explain you better what I'm trying to mention, and we will try to see some examples for this. Now let's consider a different approach. Suppose for every single iteration we do, rather than keeping track of just the maximum product, what if we keep track of maximum and minimum product at the same time and see how well we can go ahead. Now let's apply this in our given example. So when we are at the first value, the maximum and minimum value we can achieve is always going to be just 1, so nothing special there. But when we are at the second value, the maximum value we can achieve from this subarray as multiplication is actually 2, and minimum is also 2 because both are positive integers. Now when we get to the third value, the maximum value we can achieve is going to be uh, 2 again, because the third value is negative, so it is in our best interest to keep the maximum as 2. But if we keep track of minimum value, we would find that the minimum we can get is actually minus 6. Now, when we get to the fourth value, we would try to see that what is the maximum we can get. And we don't have any condition that we are only going to multiply this minus 4 with previous max only. We would try to multiply minus 4 with previous max and previous min. So in this scenario, the maximum value we can find for minus 4 is actually going to be minus 6 times minus 4, which is going to be plus 24. So over here we would receive plus 24. And what is the minimum value we can find? So the minimum value we can find would actually be the multiplication of previous value, previous maximum value with minus 4, which would be minus 8. And when we get to the last value, 5, again we will do the same thing. So we will try to multiply 5 with the max and min the of up until previous subarray. So previous value was actually 24. So 24 times 5, we are going to get 120 over here. And the previous min value was actually, and so here we can clearly see that because we were keeping track of previous two elements in our given example, we were able to calculate that what would be the maximum values and what would be the minimum values at every single iteration. And let's see how we can use it. So suppose if at the beginning of array we create three elements, one is to keep track of maximum number, second one is to keep track of minimum number, third one is to keep track of results. Initially the value of result would be 1. For the during the second iteration, the value of result would become 2. For the third iteration, it will also remain 2. For the fourth iteration, it will actually come as 24, and finally we would get our answer as 120. And at the end, we can just simply return that the maximum product we can get for any subarray for the given example would be 120. So since we know that we only have to iterate through the given input array just once, and because we are keeping track of max value and min value, we are able to calculate result every time, and whenever we want, whenever we reach at the end of the loop, we can just simply return the response. So time complexity in this scenario would be big O of n, which is a big improvement compared to what we had for the brute force approach. And space complexity is actually going to be big O of 1, because we are only keeping track of two variables at once, and we don't have to create any additional data structure or pretty efficient approach. And now let's move on to coding. Now we'll start coding by creating three variables: min product, and we initialize it to 1; max product, we also initialize it to 1; and result, we initialize it to the first element in the input array. Now let's create a for loop to iterate over the input array. And now let's compare computing values for all three elements. So for max product, we need the maximum value out of the following three. We are going to check the current value we are on. We are also going to check that whether the maximum product of that we already have multiplied by current number, and also the minimum product that we already have multiplied by current number, because in case both values are negative, our max product will actually be updated in that scenario. Now comparing three elements in Java is a little bit tricky, so we are going to use the math.max function a little bit differently here, and we will create another math.max function to compare the other two values. And now we are going to find the minimum of these three elements to store it in the min product. Notice one thing, that we directly cannot use max product times number of I in our min product calculation, because max product is already updated in this line. So we are going to create a temporary variable to store the value of max product times number of I. Now we just need to update the result to see if we can find the maximum product. We are going to compare it with current result we have, and we are going to see that whether the max product or min product is the maximum value we can achieve. Once the iteration is done, the result should have the maximum value we can find, that would be the product of any subarray. So let's return that. Let's try to run our code. It looks like we don't have any bugs. Let's try submitting it. And our solution works pretty efficiently. And thank you for following the video, guys. Please let me know in the comments what kind of problems do you want me to do more, or if you have any suggestions on how can I improve my videos. It takes a lot of time to create these videos, and I would appreciate if you can just drop a like or subscribe. Thank you so much.
Hello friends, hope you are having a fantastic day today. So now we are going to solve an awesome lead code problem called partition equals subset sum. Now we can see that this one is a lead code medium problem and also an extremely well-liked problem. So let's understand the problem statement. Basically, we are given an integer array called nums. Now we need to return true if there can be a partition in the array such that the two subsets that we make with that partition has the sum that is equal of the sum of the elements in both the subsets, and if that is not the case, then we need to return false. Now I know that the wording of this problem is actually not the best way to put the problem statement, but let's try to understand in simple terms. We are given an integer array. Now we need to, if we can create two partitions such that sum of all the elements in this partition and sum of all the elements in this partition, if both are equal, then we need to return true. If that is not the case, then we need to return false. Now let's try to see some examples. If we see this first problem, we can see that there are four elements and we can create a sum like this, that is sum of 5 plus 5 plus 5. So this can be one partition, and second partition can be this value 11. And if we check the sum of both of them, they turn out to be 11. So in this case, we can return true, that we can create a partition such that the sum of all the elements in both the partitions are equal to each other. Let's try to take one more scenario, 4 3 6. Now in this case, we cannot create a partition where the sum is going to become even. If we create a partition like 4 and 3 and second partition is 6, then it doesn't work because this is going to be 7 and this is 6, and there are no other partitions that you can make. So in this case, you will need to return false because no such partition can be made. Next, let's see one more example. So in this case, we can create a partition like this, 1 2 and 3 as first partition and second partition as 6. If we do sum of like either partition, eventually we would get the value 6 as the answer, and this is what we need to return. Because we are seeing 6 partition being made, we need to return true in this case. Now if we see the brute force approach for this problem, it is quite straightforward. Brute force, or the most simple way to solve this problem, would be to check for every single possible partition. So we can start from the first element and we can try to start every single possible partition. So we can create a partition where one value only contains 5 and the other value contains these three values. Then we create a partition like this, then we can create a partition like this, and so on and so forth. So every single time we would try to create all the possible partitions, and then we will see that whether that approach works or not. But the thing is, this is not the most optimal approach. Why? Because we can clearly see that with the given number of elements, we can create multiple partitions. So this basically becomes like an exponential time complexity, because now we are dealing with all the permutations and combinations. So this is not a good way to move forward with this approach. We will have to find a better way to deal with this problem. So the brute force solution would not work. Let's try to see that what the optimal solution would look like. Now, before we start understanding optimal solution, let's make 2 or 3 very quick assumption that will help us eliminate lot of bad cases. Number one thing is, whenever we are able to make like two equal partitions, there has to be the total number of all the sum has to be even number. What do I mean by that? Well, if the sum is even, then only we can create two partitions that are going to be equal to each other. And we can understand it with this example. We have three values, 1 plus 2 plus 3. So total sum is going to be 6. And because this total sum is 6, we have the possibility of creating two partitions that becomes equal in value, that is going to be 3 and 3. If we had the total sum to become even number, let's say that this value is 1 2 and 4, something like this. If we have an input array like this, if we do total sum, this becomes 7. With 7, we can never create two partitions that are going to be equal to each other. Why? Because 7 divided by 2 is going to be 3.5, and we are only dealing with integer numbers. So we cannot have a partition that sums up to 3.5, which means we cannot generate the answer. This is the first assumption we can make, that the total sum of all the elements has to be an even number. Okay, after determining the even number, next assumption is that once again for the same example, we can see that the total sum is 6. Now the total sum is 6. We know for a fact we need to create two partitions, and both partitions has to be even. So both partitions has to be valued 3 and 3 in nature. So in this given input array, if we can find a partition that sums up to only value 3, then we don't have to find another partition. It has to exist inside the array. Why? Because we know that the total of all of these elements are 6, and if we already find a partition, let's say with these two values, that sums up to 3, then we must have another partition that is going to be 6 minus 3. So this is also going to be 3, so we can also find that answer. So basically we need to first check that whether the sum is even number, and second thing we need to check is that are we able to find a partition that can actually sum up to the total sum. So total sum divided by 2. If we are able to fulfill these two conditions, then we can return true immediately, and if we cannot fulfill these two conditions, then we can return false in the end or immediately. Okay, now let's try to see the solution I'm proposing. And for that, remember one thing, that the input we are currently given, we are actually depending on the previously calculated values that we already have so far. Which means, let's say that if this is the example we are given, we know that we can make a partition with these two values as partition 3, but this is useless information if we don't know that what other values are or what is the total sum. We know in this case that the total sum is going to be 14. So because total sum is going to be 14, we are striving to create a partition that sums up to value number 7, but with these two we can only create 3. So should we discard them from the partition? Yes, but we can have another partition like these 3 values that sums up to 7. But the thing is, creating partition depends on the previous elements that we already have calculated and the next future elements that might come into the picture. So our current calculation that we are doing for the current value is actually dependent on previously calculated values that we already have, on whether to include that inside our solution or not to include that. So we are going to use the most beautiful thing in the entire computer science, that is dynamic programming. And for dynamic programming, what is the approach I'm suggesting? Number one, we are going to create a new dynamic programming array. But for this array, we are not going to go to the full length of the total sum that we currently have. We are only going to go up until the total part, like the half of the total sum. So currently half of the total sum is value 7. So we are only going to have 7 entries inside our dynamic programming array. We can create a partition array like this. Now initially all of the values are currently going to be false because we cannot create any single partition so far, because we haven't checked for all the values except value 0. Why value 0? Because we can always create a partition that equals to 0 if we don't have any value in that partition. So the purpose of this dynamic programming array is that for every single element we will only mark it true if we can create a partition that sums up to this value. So let me just mark the initial value as 0 as true, because we can always create a partition with 0 entries in it. So now this one is currently true, and our aim is to check that by the end we are done with all the current numbers that we have. We simply have to check that whether the DP of 7 is true or not. If this is true, then we can always have a partition that sums up to 7, which means we can create two equal partitions that sums up to 7 because the total is 14. So I hope my explanation made sense. Now let's see the walkthrough of this problem. So first thing we are going to do is, now we currently have value number 1. The idea is we are going to be starting from value number 7 and we are going to go back to the value number 1. And currently our I value that we are dealing is going to be the current I that we are using to iterate over all of these values. And next thing is that for the number that we are currently using, so we are actually using value number 1 to go over. So all we need to do is that dynamic programming value of any particular number depends on the total number of position, like so I position I have minus the number value I have. So let me explain what I mean. So currently I minus num that we are going to check for any particular value. So let's say when initially the I is going to be 7. So if I have to update the value of 7, currently I have a DP of I minus num is going to be DP of 6. So DP of 6 is false. So I'm going to leave this false. Same way for DP of 6, I'm going to be checking DP of 5. This is also false. Then for this one, because currently the number is 1 that we are dealing with. Same way, this is false, this is false, this is false, except when we reach to this very first element, we can see that dynamic programming for 1 is going to be the value of I minus num. So the value of I is currently 1 and the value of num is also currently 1. So this is going to be dp of 0. So dp of 0 we know is true, which means we can also create a partition with that sums up to value number 1, and we can mark this as true. So let's just quickly do this one, and this is going to be turned into true. Now you understood what I did. I check for all the possible values, and I check that whether there can be a partition being made where I can include value number 1, and then I can make those partitions. So currently I don't have any values, so I can not check any other value apart from creating a partition that is 1. Now let's start to work with value number 2. Once again we are going to be repeating the same formula, that we are going to be checking of dp of I minus the current number that we are dealing with, and current number is 2. So for value number 7 I will have to check dp of 5. So this is false, so I'm going to leave it as it is. For 6 I'm going to check 4, this is also false. For 5 I'm going to check 3, this is also false. But now for 4 I'm going to check 2, this is also false. But for value number 3 I'm going to check dp of 1. I now notice that dp of 1 is true, so I can also mark this as true, because I can create a partition using value number 2 that sums up to value number 3. So I'm going to be marking this as true. Now for dp of 2 I'll have to check value of dp of 0. So this also becomes true, so I can also mark this one as true as well, because I can create a partition that sums up to 2 which only contains one value. Now you must have gotten the grip of what we are trying to do in this problem. So now let's just quickly walk through the remaining solution. For dp of 4, for value number 7 I will have to check the dp of 3. dp of 3 is true. So which means we can also create dp of 7 is equal to true as well. So I'm going to mark this one as true. Same way for dp of 6 we will have to check dp of 2. So this is also true, so we are going to be marking this as true as well. And now you understood, for dp of 5 this is also going to become true, and dp of 4 is also going to become true. So this entire array eventually became true, and we haven't checked the value 7, but we can also check for value 7 as well. No worries with this one, and this is also going to become true. So now logically all we need to check is the dp of 7, if that is true or not. Since this is true, so in the answer we can also return true, saying that we can create a partition that sums up to value number 7 using this dynamic programming approach, and this is what we need to return. So basically this is such a beautiful solution, and rewatch again if you did not understood, and let me know in the comments on how do you feel about my explanation. Now let's try to understand the time and space complexity. In this case, time complexity is going to be big O of n, because we are simply iterating the entire array, but we are doing it in total number of elements that are currently present inside the array. And if we see space complexity, so space complexity is going to be big O of n, because we are using an additional array to store this information. Now let's quickly see the coding solution for this one. So the coding solution is quite straightforward. First, we are going to initialize a variable called total sum, and we are going to iterate over the given input array nums and add all the elements inside the total sum. First thing we are checking is that if the given total sum is odd, then it is not possible to create equal partition, so we can simply return false. If that is not the case, we will first of all create the target value of which the partition number we are trying to achieve. Then we are going to initialize a boolean array called dynamic programming, and we are going to be marking the first value inside the dynamic programming array is true. Now notice that I added the value to be target plus 1, because if the target is 7, we need total 8 elements inside the array, where first element is going to be dp of 0. I hope you understood that. Now next thing is that we are going to have a for loop that is going to iterate over every single number that we have in the nums array. For each of the number, we are going to be checking that we are going to be starting from the target value, and we are going to go down to that particular number, and we are going to be reducing one element at a time. And every single location we are going to check inside the dynamic programming array that what is the value of j minus num, and if that value is true, then we can also define the dynamic programming of j to be true as well. And in the end, we simply need to return dynamic programming of the target value, or the very last element inside the given array. So this is the whole solution. Let's try to run the code. Seems like our solution is working beautifully. Let's try to submit this code. and our code beats 94% of all the other solutions in terms of time complexity and 87% of all the solution in terms of space complexity. This is one of the most accurate and beautiful solutions out there. So I would be posting this inside our GitHub repository. Feel free to go ahead and check it out. Thank you.
So if we see some of the popular companies who have already asked this question, there are companies like Microsoft, Amazon, Facebook, Google, Bloomberg, Adobe, Apple, Uber, Snapchat, Tesla, Goldman Sachs, and Airbnb. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a lead code hard problem and also a very well-liked problem. Basically, we are given two input strings. One is string S and the other one is pattern P. Now we need to implement a regular expression matching function that can support a dot character and a star character inside this pattern P as well. Now we are given the definition that what does a dot and a star represent. Basically, a dot can represent that it can match any single character, and the star represents that it can match 0 or more preceding elements. Now first let's try to understand both of these with examples. So suppose we are given a pattern P that looks like A, B and dot. Now dot by definition it can support any single character. Now inside our given string S, suppose we are given the values to be A, B, C. Now can we conclude these two to be matching strings? The answer is yes. Why? Because for this particular dot we can consider it to be C because it can match any character. Suppose if we are given an S that looks like A, B, X, is it true? Yes, this is also matching with this pattern P because for this time for this dot we are actually considering it to be X. But if we are given S that looks like A, X, is this matching? No. Why? Because the second character over here, this is A, meanwhile the second character inside our pattern is B. These two are not matching, so this is not a matching sequence. So basically this is what does a dot represents. Now let's try to see one example of what does a star represent. So basically suppose we are given a pattern P that looks like this, where the values are again A, B, star. Now what does this star is saying by definition? The star is saying that it can match 0 or more preceding elements. Now what is a preceding element of this X? The preceding element is B. So which means that now this particular pattern can match bunch of different other strings. So strings such as A, B, 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 B. Does this match this particular pattern? Yes. Why? Because if we see, okay, first character A is matching each other. Now for the second character B, we can have multiple B's over here because of this star value, because that is what is given in the definition. So based on the definition, we are now in this case considering the star to be all of these B's. Suppose we are given a string S that is only A. Is this matching with this pattern P? Yes, this is also matching. Why? Because this star can represent that we have 0 or more preceding elements. So in this case, we are considering that we have 0 B's in the pattern, which means that our given S is actually matching. And in this case, since both of these are matching, now let's try to take one more example. Suppose our given S is equal to like A, B, X. Is this matching? No, this is not matching. Why this is not matching? Because this AB portion, this is matching, that is good. But we do not have an X over here, and that is why this is not a match. Does this match? And pause the video for a second. Try to guess that whether this matches or not. Let me come up with the answer. The answer in this case is that this is actually a match. Believe it or not, this is a match. Why this is a match? Well, okay, first F is matching. This is good up until this point. Now, because we have a star with dot, which means we can have n number of occurrences of dot. And we know by definition that dot can represent any single character. So in this case, what we are going to have is, we are actually going to have 7 different dots. And these 7 different dots, they are going to represent each character that is missing in the remaining string. And then eventually when we reach to the end, we are going to declare this as a match and we will be able to return true in each of the cases. So I hope after so many examples, things would make sense and you would get the idea that what this problem is asking us to do. Basically, we need to return a Boolean answer, whether true or not, that whether any given two strings, do they match or not match. Okay, now before we come up with the solution, first let's see that what could be the different possibilities for our problem and what could be the different things we can do in the solution. Now I have drawn a table over here where I'm representing different like string values and pattern values, and we'll try to see that what happens in every single scenario and what are the actions we can take. Now I have noted that there could be like a C mentioned over here in this column file, and this means that it could be any character from A to Z, because in the string we can only strictly have A to Z characters. Meanwhile, for the pattern we could have definitely C, or we could also have a dot and a star. So that means different things, and if they are present we might have to do things a little bit differently. So first let's see the first scenario. In the first scenario, basically both the values we are given is like a simple character. So for S and P, suppose we are given the values like A, B, C and X, Y, Z. This is pretty simple to match, that whether the string matches the pattern or not. We simply need to judge character by character. In this case, we can simply see that whether they are matching or they are not matching. This is a very simple binary operation. Second option we can have is the most beautiful option, that whether we are given one character and we are given a dot value. This is also very straightforward. If there is a dot present, definitely it matches the character. We can simply return that there is a match for that particular character. Second scenario is that we could be given bunch of different characters, and we could be given like some characters at the beginning, and then we might be given like a dot and a star. In this possibility, basically what we need to check is that whether like a single character like this first character, and whether this first character, I mean this could this could represent like more characters. These could represent something like a and like a dot star, something like that, right? There could be like different matching things. I'm just noting down C. But this means that if like the before portion matches, everything at this position is definitely going to match. So in this case, if like the values before the dot and star matches, then everything is a match, right? If we take a look at this example, basically we are simply given dot and star. In this case, 100% there is going to be a match. Why? Because all the values that are present over here, we can take like 0, 1 or bunch of different dots, and all of these dots can represent all the characters that we have. Now comes the interesting part where we are dealing with a star. What could be different possibilities? So let me give you like one possibility. Suppose for this our string and P value, we are given the values like A, B, and over here we are given the values as A, B star. Question is this a match? Yes, this is a match. Why? Because this is the first value, this is a match in itself, and over here we only have one value of B. Now over here we have B star. So this B star could represent that we don't have any values, or we have one value of B, or we have two values of B, or we have infinite values of B all across like the board, whatever we want to choose. So in this case, we are definitely going to choose one value of B, which means this is a match. So in this case, what are we considering? Value before the like preceding value of star. So value before preceding value of star. If that is a match, definitely we can find a match, right? There could be another possibility. We could be given a string, we could be given a P, we could be given a bunch of different values like A, B, X, Y, Z, A, B, X, Y, Z. So far everything is a match over here. And then over here we are given something like 2, 3, 4, 5 Z's, right? And over here we are given like just a star value. In this case, how would you define that whether this is a match or not? Well, definitely this is a match. But the way you are going to define is that the values that this Z and star that we are considering, like these values, before that we are checking that whether all the values that are present before that, are they a match? If all of these values are match, definitely we can create this to be a match. So again, we are considering like all the values before the preceding value of star. I know I'm using a lot of abbreviations, but you just have to be with me. I'm not going to write all of them. And if that is a match, we can consider this to be a match. There is also one more possibility where we actually do not need to consider this like preceding value at all. What could be a scenario? Suppose we are given string as is equal to like a, b, c, d, and over here we are given some p is equal to a, y star, and then b, c, d. In this scenario, this is definitely a match. Why? Because for this y star, we are considering this to be 0. If this is being considered as 0 values, which means that this is a match, and then all the other values, they are match. So we will find a potential match over here. So again, we are considering like if the value before the preceding star, if that is a match, then we can consider this to be a match. So now we are just like dealing with lot of possibilities where every single time for value inside the pattern, we will have to keep track of the value, like two value before that whether that is a match or not. And in order to calculate any single calculation, we are always checking that whether the values before us, are they matching or not. So this is a very good candidate for a dynamic programming solution. Why a dynamic programming solution? Because first scenario, we are definitely like using whatever the results we have calculated to check that whether the current result we are at, if that is a good or not. Second, already calculated results are going to give us the ability to decide that what do we do in the current position, because we are not only dealing with like simple characters, we are also dealing with like a dot, and we are also dealing with a star. So this is going to be really helpful. And we can use something like recursion to solve this problem, but that is going to complicate things. We are actually going to use recursion with DP, and that is going to make things much more easier. So let's try to take one example over here. And the question is, for a dynamic programming, we are not only going, because we are dealing with two different like string and pattern, it would be better to create a 2D matrix. And inside the 2D matrix, for every single like string and every single pattern, we will try to see that whether the characters match or not. And based on their true and false values, we would be able to calculate some interesting results. So let's see that in action with an example, and that would make things more clear. Okay, so currently we have created an example for a string and a pattern, and we need to check that whether they match or not. Now also for this pattern, I have created a 2 by 2 matrix where inside every single row represents the string value we have, and every single column represents a character inside the pattern we have, and we will try to see that whether there is a match or not. Now remember, for the first row and column, I have kept it as empty. Why? Because these we are going to use to create our base case. Now our base case is that currently for the string, the first character we have is empty character, and also for the pattern, the first character we have is empty character. Now, because these two are empty characters, definitely empty characters are going to match for sure. So in this case, this value is always going to be true. Now we will try to see that whether there is a match over here or not. So in this case, because this is an empty character and we have some character over here, there is not going to be a match. So definitely we would always be able to like have all these values as false. So currently we are at this first position. This value is f, this value is f. Both of them are characters, both are same. And when both are same, we will also have to check that all the values before that, if they are also match or not. So currently the only values before that were two empty strings, and that represents this diagonal corner. So because this diagonal corner was true and we have matching set of characters, we are going to take the value that is diagonally present and put it at this position for this 1 1 box. Again, I'm repeating myself that because these two characters are same. So first we check, okay, these two characters are same. Then we check its diagonal value, because what this diagonal value is going to do is it is going to check that whether all the values before these two values, are they a match or not. And this will come in handy when we are at some position like this, because if over here we find this AA to be matching, which means this value is a true. But do we need to keep it as true? Because if this is false, which means if we are, say for an example, we have string to be FA and we have pattern to be PA. So in this case, though these two match, but this is not a match. Why? Because this F and P does not match. So we can break out immediately. And that is what we need to keep track of every single time. And that is why this is a dynamic programming problem. So in this case, as explained, this is going to be true. Okay, now again let's start filling up this all of these files. And what we are going to do is, okay, this one is true. Now we will have to check that, okay, currently we have FA and the value we are comparing it against is F. Is this a match? No, this is not a match. So this is going to be false. Again, currently the value is FA star and the only value we have is F. Is this a match? Yes, this is a match. Why? Because for this A star, we can actually consider this to be an empty string or zero values of A. And if we do that, then we will have no values over here. So in this case, this F and this F is match. And why this happened? Because we had a star value over here and we were dealing with the star value. So now again the new theorem comes that whenever we are dealing with a star value, we will have to check the value before its preceding value. Again, whenever we are dealing with a star value, we will have to check the value before its preceding value. And if that is true, then we can directly mark true over here. So we check, okay, this was true. So definitely we are going to put true over here. Awesome. Now we are at this position number n. Now currently what is the scenario we are comparing? We are comparing the values of F, A, star, N, and we are comparing it with F. So N and F, there is no match. So definitely we can mark false over here. Now we add a dot over here. Again, there is a no match. So we can mark false over here. And same way, this is also going to be false. Okay, now we are at this position. So now we actually have two values, FA. Now for this FA, if we only compare it with this value F, is this a match? No, this is not a match. So we can mark false over here. Okay, now after marking false over here, currently we add this positions. Okay, so FA, definitely there is a match. So because these AA matches, we will compare its diagonal value, and the diagonal value we get this result, and we will mark the value over here. So this is going to be true. Awesome. Now currently we are at this FA star. So FA star, is this a match with this FA? Again, now we have the star value. So we will have to check. First thing we will have to check is whether we can consider this to be just like an F and empty string, or we can consider this to be an FA, or we can consider this to be an FAA. I'm talking about this value, right? And if we see this FA is a perfect match. So now because we have a star value again over here, we are going to mark this as true. But this true, we are getting it from the value before. Because remember, in this case you must be wondering that, hey, for this particular position, this value is actually empty. Then why are we marking this to be true? We are marking this to be true because this one is true. Because we found a match of FA, and because this value is true, we will mark this as true. So let's do that. Awesome. Now currently the next value we have is like FAN, and this value we have is FA. So definitely there is no match. We will mark this as false, and if we add dot, we will again mark this as false, and blah blah blah. Right? These are all the values going to be false. Now currently we are at the position of FAA. Let me clean this up a bit. So currently we have FAA over here, and currently we only have F over here. So definitely this is going to be false. Again, this FA is also going to be false. Now again we are at the critical juncture. We have a star value. Now because we have a star value, you must be wondering that what will be the possibility. Well, the possibility is, again, over here for this FA star, we can consider it to be like only F or FA or FAA. In this case we are going to consider it to be FAA. Now you must be asking that, hey, previously when we were at this position, you mentioned that because this is true, we are marking this to be true. Then when we were at this position, you mentioned that though this was false, but because this was true, we were marking this to be true. Now we are at this position, this is also true, sorry, this is also false, this is also false. Then how come we are marking this as true? We are marking this as true because this value is true. Mind blown. Yes, this is like the most important point for this problem, that whenever there is a star present, we will have to check three different values. So whenever there is a star present, we were checking that whether the value before the preceding value, if that is true, we can mark this as true. If there is a star present, we will check that whether the value before this, if that is true, then also we can mark it true. And if there is a star present, we can check that whether the value above it, if that is true, then also we can mark it as true. Which means whenever we were at this position, if we don't want to get into all of these like calculations, all we need to do is that currently we are at this box, then we will have to check three different boxes. First box is the right, like before box. Second box is this one, like the box before box, and third box is a box above that box. So for this particular box, if either this or this, if any one of the value is true, we will need to mark that value over here. If all three are false, then only we will mark it as false. And why this happens? Because this was a star value and there could be bunch of different possibilities we can use over here. And this was the most difficult part of this problem, and congratulations, you understood it perfectly. And now because this was true, now currently we have this FAA, and now we have this like F. Now we are at the next value. So next value is FA star N, and this N is not a match, so this is going to be false, and then all the subsequent values are also going to be the false. Now this is a very easy problem to tackle, because now we are at this position N, so this is not a match, so this is going to be false, this is also going to be false, this is also going to be false. And now we are at this N and N, because these both of these are characters, so there is a match. Because there is a match, we are going to consider it's like diagonal value, so diagonal value is true, so this is also going to be true. Now this is a dot value and we only have values up until this point, so which means we are going to mark this one as false, and we are also going to mark this one as false. Now again we are at this value number G, so we all of these are going to be false up until this point. Now there is a dot over here and there is a G over here, which means there is a match. So if there is a match, we are going to compare its diagonal value. The diagonal value is T, so that is true. So because this one is true, this is also going to be true, and the last value is going to be false, because we only have value up until G up till this point, and we have this M over here. Now the last value is, okay, this is going to be false, 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 and this is also going to be false. Now we are at this last position. This M is a match with this M, so because this is a match, we are going to take its diagonal value, and the diagonal value in this case is true, so we are going to take this value as true. Now our dynamic programming table is complete, and all we need to do is we need to check this diagonal file, and we need to check this last value. Because this last value was true, we can return true in this case, and this would be the answer we need to return. And that is the whole logic behind this problem. And this was a very beautiful problem. If we were only dealing with the dot values, this would be much easy to solve, but because we were also dealing with the star value, it added a layer of complexity. Now if we see time complexity, in this case the time complexity is actually going to be big O of M cross N, where M is the length of a string and N is the length of the pattern. And if we see space complexity, because we are creating a 2 by 2 matrix, basically the space complexity is also going to be big O of M cross N. And this is a beautiful solution, like one of the best dynamic programming solutions I have seen so far. So I hope you would have enjoyed it. Now let's move on to the coding. First we will check for an edge case, that if both the values are null, we can simply return null. If that is not the case, we are going to initialize our dynamic programming 2D array, and for this 2D array, let's name it as DP, and we are going to assign the length of whatever the length of S is +1 and also length of P +1, and we are going to assign the base value of the 0 0 to be true. Okay, now let's populate the first row. So this should take care of the first column. Now let's start our loop. So we are going to iterate over I and j, which means we are going to do 2 for loops. Inside the loop, we are going to check for all 3 different possibilities. So first possibility is that the given characters, the p is actually a dot. If that is the case, which means it would be able to match any single character, we are marking like the dp of I plus 1 and j plus 1 to its diagonal value. Now you must be wondering, why am I dealing with like I plus 1 and j plus 1? Because for the first row and first column, remember, we mark their values as 0 and we actually started the value of s and p on the first position. So that is why every single time I'm going to updating like I plus 1 and j plus 1 values, because the ith and jth value is actually located at like 0 0 position. They don't have any values. So if there is a dot present, we simply check the diagonal value. Now the second possibility is that both of them are characters, and if both are characters and they both match, we can also mark their value as same as their diagonal value. Now we are at the third possibility, and the third possibility is that if the given character, if that is in the pattern a star, if that is a star, then we will have to do some additional calculations. So now for first we are at the value star. So there could be two possibility. We could have some value as like character and a star, or we could have some value as like a dot and a star. So if there is a dot and a star, we only need to check that whether all the values before that, if they are match or not. And if that is the case, we would be good. We can mark it as true. And so first let's take care of the scenario that if the given value is actually a dot star. Now we have done that check, and then we will check all of those 3 boxes I mentioned, that if either one of them is true, we will simply add that value over here. With this value, we are actually comparing all of those 3 boxes. So if any one of them is true, we can mark it as true. And in the end, this concludes all the possibilities we can do inside our loop. So basically we are done with our calculation. Now simply in the end, we need to return that what was the last value inside our dynamic programming diagonal. That should be it. Let's try to run this code. Okay, seems like our solution is working as expected. Let's try to run this code. And our code runs pretty fast compared to a lot of other solutions, and which is really good. And it's great in terms of time complexity and also in terms of space complexity. And I would be posting this solution in the comments so you can check it out from there. Thank you.